Hi everyone, so let's see what we are going to study in this lecture. So what we have already studied till now, we have studied diode. So what was diode? Diode was a two-terminal device. Diode was two-terminal device. Why two-terminal? Because this was the structure of diode. Two-terminal device, this is first one, this is second one. Diode was a two-terminal device. So in two-terminal device, we saw different application. First we saw clipper circuit. What was clipper circuit? Clipper circuit clips of the undesired part of the input signal. What does clamper circuit do? It sets a new DC level. That means it clamps up or clamps down the input signal. What does peak detector do? Detects the peak value, positive or negative. So in the output you are having some DC value. It can be plus Vm or minus Vm. In clamper you are having AC plus DC, but AC was not amplified. AC was remaining as it is. Vm sin omega t was there. Just the DC level was shifted, plus Vm or minus Vm. In clipper, the waveform was getting changed, but it was not being amplified. What was voltage multiplier? In voltage multiplier, the voltage was getting amplified, but your output was DC. Assume my input is Vm sin omega t, so at the output you can have 2 Vm, 3 Vm, 4 Vm, but the output was DC only, not AC. So these were the application we saw. So using the diode circuit, let's assume if this is my input Vm sin omega t, and if I want my output to be 2 Vm sin omega t, can you do that using diode circuit? Can you do that using diode circuit? No, right? We can't do that using diode circuit. We tried doing it. When we tried doing it, what happened? We tried doing it with the small signal analysis. When in small signal analysis, when diode is on, we replaced it with RD equals to neta Vt upon IDC. In the initial lectures, we saw that. And when it was off, we replaced the diode with open circuit. So let's assume, based on the DC analysis, if diode is on, if diode was on, if diode is on, what would be your output? Your output would simply be some DC output plus what would have happened to AC. For AC, this would have replaced with RD, so your output would be RD upon RD plus R into VAC. So this is not amplified, right? Let's assume RD is 2 and small RD is like small RD is 2 and capital R is 5. So it would be 2 upon 2 plus 5 into Vin. So 2 Vin is VAC actually. So 2 by 7 VAC. This is not amplified, right? You are not getting the amplification here. And if it was off, then what would have happened? If diode is off, what you would get? You would get simply V naught would be equals to VDC plus VAC. So again, it is not amplified. So you are not getting an amplified output, not getting amplified output from diode. We are actually moving to our 4-terminal device or 3-terminal device. So why do we need that device? This is what I am telling here. So not getting amplified output. So because of that, yeah, so this is what I have written here, Vm sin omega t. So using diode circuit, let's assume I want k Vm sin omega t, where k is greater than 1. So this is not possible. Mod of k is greater than 1, I would say, because it could be minus 2 Vm sin omega t as well. That is also amplified, just the phase is changed. So this is not possible. Not possible. I can put a cross mark. This is not possible. So you need a 3 or 4 terminal device now for the amplification of the input AC signal. So now we need a 2 terminal, not a 2 terminal, but a 3 or 4 terminal device. So let's assume this I am calling as terminal 1, terminal 1. This is terminal 2. This is terminal 3. And this is terminal 4. Terminal 4. Okay. And this terminal 1 will be the, one of the terminal would be the controlling one. So I am writing it as a controlling terminal. So one of the terminal will be controlling one. That it will control the current. One of the terminal will control the current. So what is a basic amplifier? What is a basic amplifier? In basic amplifier, what do we do? It can have some input resistance. So this is a basic amplifier. So in the amplifier is a black box. Okay, just assume it is a box. So in amplifier, what do? You give an input. This is your black box. This is your black box. Amplifier is a black box. It can have some output resistance as well. Amplifier can have some output resistance R0 as well. So you give some input. It amplifies the input. It can change it into current as well. It can change it into voltage as well. We are assuming it is changing our input voltage into current with some factor K. So it has changed our input voltage in current, and then at the load we are having some resistance RL. So what will be your output? So your output is K into RL into Vin and a negative sign. So basically your output is amplified by this. Now you have the control over RL, you have the control over K. So based on the control K and RL, you can have an amplified output. What did we do? This is an amplifier. This is an amplifier. In the amplifier, at one port we give the input. That input is amplified into a current. That voltage input is changed into a current, and that is going towards the output. So at the output we are having minus K into RL into Vin. You have the control over RL, you have the control over K. So from here you can get the amplified output. So here we can get amplification, and this is what we needed. So this kind of amplifier can be made using 3-terminal or 4-terminal devices. 3-terminal devices BJT, bipolar junction transistor, and 4-terminal devices JFET and MOSFET. MOSFET is metal oxide semiconductor field effect transistor. So we will study one by one. First we will study MOSFETs. So MOSFET is a 4-terminal device. So first we are going to study about field effect transistor. So in field effect transistor there can be other devices as well, JFET, MOSFET and other FET as well. But we have to study about MOSFET only, because this is the only important and most important part. We will study about MOSFETs. So what does MOSFET stand for? Metal oxide semiconductor, and FET stands for field effect transistor. We will understand the meaning of every term here. Why metal, why oxide, why semiconductor, why field effect transistor. We will understand the meaning of every single term. Before that, let's do the classification. So MOSFET are of two types. What are the two types? NMOS, PMOS? No. They are of two types, and these are depletion type MOSFET. Depletion type MOSFET. And the other one is enhancement type MOSFET. And these are classified into two further parts, that is N type and P type. So this can be N type, P type, N type, P type. So we will study one by one. First we will study N type depletion MOSFET. Okay, N type depletion MOSFET. This is what we are going to study. So first we will see a general structure of a MOS, which is of N type. So in N type, what we are having here, we are having N well. What did I say? N well. That means you are having N type of semiconductor here. This is what you can consider. This is N type. This is also N type. This particular node is known as source, and this particular node is known as drain. What does they do? Everything we are going to study. What are they going to do? Everything we will study. And then there is a N channel there. So in depletion type of MOSFET, the channel is already present. What I am going to write, the channel is already present. In depletion type MOSFET, channel is already present. The N channel is already there. So this is how a MOSFET looks. This photo I got from ResearchGate's website. So this is how a MOSFET looks. So this I have drawn source here, drain here. So this is the front view, and at the top what you will see, this layer, and then this layer, and then this box. This is what you will see from the top layer. So this one, this layer, this particular layer is the metal. Then you are having an oxide, and then you are having a semiconductor. This is a P type of substrate, so the P semiconductor is there. In P type of substrate, there are N plus, and N channel. So you had a P type of substrate, and there you put N plus, and N channel. Then on that particular substrate, you are having oxide and metal. This N plus you are calling source, then N plus you are calling drain, and over the metal you are calling that gate. Here you will pick one node that you are calling gate. Here you will pick one node that you are calling source. Here you will pick one node that you are calling drain. Understood? This much of concept you understood? This length is known as L. This is length, and if it is backward, it is width. Length and width. You can see it in the diagram, length and width. So this I don't need to show here. So everything is clear. Metal oxide semiconductor. That's why we call it MOS. Metal oxide semiconductor. Why it is called FATE, that we will also see. And this particular node is known as gate, drain, and source. Now what do they do? What are the definition of source, gate, and drain? Let's see that. Let's see that one by one. So what is the source? Okay, the screen is going black. Let's wait for a second. Yeah, it's fine now. So what is source? So source supplies the charge carrier to the channel. What does drain do? Drain collects the charge carrier from the channel. And what does gate do? Gate controls the flow of charge carrier. These are the three things. Okay, first thing is that it is 4-terminal device. So there are gate, source, and drain. There is this body terminal as well. What is the use of this body? We will see that. In the later part of the video, we will see that what is the use of this body. So there are 4 terminals: source, gate, and drain, and body. So source, drain, and gate. Source, from here you will get the charge carrier. It will travel through channel and it will be going out of drain. That's it. From N plus you will get the charge carrier. It will travel through the channel and will be going out of the drain. Let's understand it with the analogy. That is this analogy. So it is like a tap. In tap, if you turn it on, what happens? Water flows from some source. From some source, water comes and then it flows and gets out of the tap. So this particular space is source, from where water is coming. Then there is a channel for water to flow, and from the drain it will get out. And gate will control the flow of the water. So similarly, here the gate will control the flow of the charge carrier. If you increase the gate voltage, if you decrease the gate voltage, something can happen. If you increase it, your current can increase. If you decrease it, your current can decrease, or current can be zero as well. So based on the potential of gate, the flow of charge carrier is maintained. So did you understand all the point here? From source you are getting the charge carriers, then from channel it travels, and from drain it gets out. And gate controls the flow of the charge carrier. Now why it is called FET? Field effect transistor. Field effect transistor. So the flow of current is modulated because of the applied electrical field or applied voltage. So here you will apply some voltage at drain, at source you will apply some voltages. Because of that, the flow of current is modulated. That means because of the applied voltage only you are getting some current. So this particular transistor is running in the effect of a field, that is electrical field. So this particular transistor is running in the effect of the electric field. That's why it is called field effect transistor. So did you understand the complete meaning of MOSFET now? Metal oxide semiconductor, field effect transistor. Metal oxide semiconductor, and this particular transistor is running in the effect of electrical field. So that's why it is called field effect transistor. So MOSFET, metal oxide semiconductor, field effect transistor. So did you understand the meaning of MOSFET now? And what is the source, what is the gate, what is the drain, and what is the channel? So I hope you understood the meaning of MOSFET. Now we will see what is particularly N-type depletion MOSFET. So what does this define? Type. That means this defines the channel, that your channel will be of N-type. So here your channel is of n-type. So we will call it n-type depletion MOSFET. And if it is p-type, your channel will be of p channel, right? Your channel will be of p type. So here the channel is already framed. Now what we will do, we will apply some voltage on gate, drain and source. Then we will see what happens in this particular device. Okay, so first condition we are taking that my VGS is 0 and VDS is positive. Now I will tell you one thing. In the complete analogy, not analogy, in the complete lecture, what we will do, we will always take source as a reference. We will always take source as a reference. That means we will keep it grounded. If I am saying that I am applying VDS to be 4 volt, that means I am applying drain voltage to be 4 volt. It's not that I will apply 3 volt here and minus 1 volt here. This is you can do. But for better understanding what we are going to do, we will take source as a reference. Okay. We will always take source as a reference in the complete lecture. Source will be at reference. That means source will be shorted. So if I am saying that I am applying VDS to be positive, that means here I am applying positive supply. If I am saying VGS is negative, that means this is also shorted. And one more thing, until I explain you body effect, there is a phenomena that is known as body effect. So until I explain you body effect, till that time source and body will be shorted. Till that time source and body will be always shorted. If I forget to show it shorted, you have to assume it. Source and body will be always shorted until I explain you the phenomena named body effect. So source and body are shorted. So this is grounded, and since they are shorted, this will also be grounded. So this is also grounded. So source and body are grounded. Now here I am saying that VGS is 0. That's why I put a gate voltage also 0. And now I am saying that VDS is positive. That means at drain I am applying positive supply. Now what will happen if I apply positive supply at drain? If I apply positive supply at drain, what will happen? Let's check that. So yeah, before checking that, let's get the meaning of N plus. What do you mean by N plus? Plus means it is highly doped, and highly doped means more conductivity. By the way, what is N-type semiconductor? This is N-type semiconductor. I hope you remember it because in the initial lecture we have studied it. This is N-type, right? And what is P-type? P-type is this. In N-type we get electrons, and P-type we get holes. In the initial lecture only we have studied it in the diode circuit. So N plus means highly doped, that means more conductivity. More conductivity means lesser resistance. Less resistance. And N is lightly doped. Lightly doped means less conductivity. That means more resistance. So if I am saying that this is my source, this is my drain, this is my channel, this is N plus, this is also N plus, and this is N. So this particular region is having more resistance, right? This particular region is having more resistance, and N plus are having lesser resistance. So what I can do, I can replace, just as a analogy, what I can do, I can replace this something like this. This source, channel and drain, I am replacing it something like this. This I can call source resistance. This I can call channel resistance, and this I can call drain resistance. So here channel resistance is the maximum. Here channel resistance is more than drain and source resistance. Why so? Because it is less doped. Less doped means it is having less conductivity. That is, it is having more resistance. Now tell me one thing. What did I say? That I am applying positive voltage here. What did I say? I am applying positive voltage here. Let's assume if I apply 8 volt here. If I apply 8 voltage here, what will happen? For better understanding, I am assuming that this R channel is double of R drain and R source. This is my assumption. Assumption is that this R channel is double of R drain and double of R source. So if I am applying 8 volt here, what will happen? 2 volt will be coming here, 4 volt will be coming here, and 2 volt will be coming here. More voltage, sorry, more resistance, more voltage. If it is having more resistance, that means it will take up more voltage, although the R channel will be more than the double. So the point here is that if I apply some voltage here, let's assume I am applying 10 volt here, so most of the potential will be coming across the channel itself. Are you understanding this point? Since the channel is having lesser conductivity, that means it is having more resistance, so whatever the potential I am applying at the drain side, most part of that potential is coming across the channel only. Are you agreeing to this point? Say yes or no. And this potential is linearly divided, like here 8 volt, then here 6 volt, then here 2 volt, and here 0 volt. So 8 volt, 6 volt, then in between this resistance somewhere 5 volt, 4 volt, 3 volt, 2 volt, 1 volt, then 0 volt. So this is linearly divided. So 8 volt I am applying here, that 8 volt will be linearly divided in drain, channel, and source. If you have already studied this MOS physics, then you might not have studied it in this manner. I know, like most of the place, what I have seen, that they will say that here you are applying positive voltage, so positive will attract the electrons, so current will flow. This is not the region. Okay, in one of the short video you will find this region only, that how the current flows in n channel depletion type MOSFET. If you apply positive voltage, this electron will be attracted by this positive supply and current will flow. But that is not the correct region. Slowly we are moving towards the correct region. Okay, in the interview if you say these kind of things, they will reject you. So this we have understood. Now what we are doing, we are applying the positive voltage at drain terminal. So here we are applying positive voltage. Now see the structure of MOS. What you can see, this is P substrate, right? And these are N. P substrate and all are N. Can you assume a diode here? Look, diode is not practically there. It's not that diode is practically there, but we can assume a diode kind of structure. We can assume that a diode kind of structure, right? So basically, oh, not this P substrate. This I had to remove. Yeah. So I'm breaking this R channel. Okay, I'm breaking this R channel in two parts. This is my R channel only. This is R channel. This I have broken into two parts, and this is R drain. And here I am applying some positive voltage. Let's say that is 8 volt. Now at each side, what I am seeing, I will see a PN junction kind of structure. Here there will be again PN diode. These will be the PN diodes there. Now 8 volt is there. Now 8 volt will be linearly divided. What will come here? 6 volt. What will come here? 4 volt. What will come here? 2 volt. Now this potential, whatever the potential it is, it would be equal only, right? Let's assume everywhere the potential is X. Everywhere the potential is X only. And this 8 volt is linearly divided. So 8 volt, 6 volt, 4 volt, and 2 volt. Tell me one thing, which diode is having the maximum reverse bias? This one. Maximum reverse bias. And this is having the minimum reverse bias, right? So what did you understand by this point? in the MOSFET, if I am applying in the N channel MOSFET, if I am applying a positive supply at the drain side, then from drain to source, the reverse bias is getting decreased. If I am applying a positive potential at drain side, from drain to source, the reverse bias is getting decreased. So here this diode has the maximum reverse bias. And also most of the potential are there across these diodes only. So here in this region we are having the maximum reverse bias, but slowly the reverse bias is getting decreased. If reverse bias is getting decreased, that means the depletion region is also getting decreased. If you remember PN junction, that's why I said that PN junction is very important. So more the reverse bias, more the depletion region. If I increase the reverse bias, this region would have increased. So more the reverse bias, more the depletion region. So what I can write, from drain to source, reverse bias decreases. That means depletion width decreases. So at the drain side you will have the maximum depletion region, and at the source side you will have the minimum depletion region. So this is how your depletion region would look like, and this is I have drawn channel. So this is not a complete MOSFET. This is these two part only. These two part only I have drawn. Channel and the drain. This is the drain. This is the channel. So, and what is this? What is this? This negative, negative, negative. From where this negative is coming? That is P substrate. This is P substrate. P substrate. This is P substrate. So now what is happening? At the drain side we are having reverse bias. So there is this depletion region. Because of this depletion region, there is this electric field is generated. Because of this depletion region, electric field is generated. This you can't see. You can use green color pen. So because of this depletion region, plus and minus, there is electric field generated. Now this, what will this electric field do? This electric field will attract these electrons and will make them travel in the opposite direction of electric field. So these electrons will be swept away in the drain region and will get out of there. So this was the region. This was the actual region why the current flows. When I apply a positive bias at the drain side, what happens? Depletion region is formed. Because of this depletion region, there is high electric field there. Because of this electric field, the electrons in the free electrons in the channel feels the attraction in the electric field and it is swept to the drain terminal. The electron moves in the opposite direction of the electric field and swept away from the drain terminal and the current flows. Are you getting this point? So these electrons are getting swept away in this direction. So very crude way was that because of this positive supply, here there are electrons, they are getting swept. But what is the other reason is the actual reason is that this is the bias is framed, this electric field is framed, right? This electric field is framed because of the depletion region. This electric field is framed. Oh, sorry. Yeah, this electric field is framed which has this direction. And plus, wait a second. Just a minute. Yeah, electric field have this direction. Sorry. Yeah. So this electric field is framed. The direction is this. And since there are some free electrons here, because of this electric field, they are getting swept away in the drain side. Because electron will travel in the opposite direction of the electric field and they will be swept away from the drain terminal and the current flows. Are you understanding this point? Right? Well and good. So this is what is happening here. And one more thing is happening, that because of this positive supply, this here this is increasing. Look, this is p type and this is, sorry, this is n type and this is p type. If I am applying positive potential here, what is happening? Most of the positive potential is coming on this side. Because of that, this is n and here it is p. Because of that, this depletion region is increasing. What will happen if I keep on increasing VDS? If I keep on increasing VDS, what will happen? The depletion region will keep on increasing from drain side. From drain side, the depletion region will keep on increasing, because at the drain side maximum potential is there. Then slowly the potential is decreasing. So at the drain side you have the maximum potential, then lower potential, then lower, then lower, then more lower. So at the drain side, the depletion region will keep on increasing. So what will happen? If I keep on increasing VDS, what's going to happen? It will be somewhat like this, right? And the rest of the areas, this rest of the area will be plus only. Here if I am making this one, what do I mean? I mean this. But here only I am showing the electrons. So slowly, here this part, channel is getting depleted of charge carriers. If I am increasing VDS value, more positive potential will be coming on the channel. Because of that, the channel is getting depleted of charge carriers. Positive potential, that means reverse bias. Reverse bias means depletion region is increasing. So depletion width is increasing. If I increase more, what will happen? If I increase more, then depletion width will increase more. But what is happening? Since this positive potential at the drain, I am applying this positive potential, the electric field is getting strong. If I am increasing VDS, the electric field is getting strong. That will attract these electrons very fastly. So the current will increase. But that will happen initially only. Initially, I am increasing VDS. So what is happening? The depletion width is getting increased. If depletion width is getting increased, that means this particular electric field is getting strong. If this is getting strong, that means it is attracting those charge carriers very quickly. But at a certain time, at a certain VDS, what will happen? At a certain VDS, this channel will start getting depleted of charge carriers. Here the charge carriers will be very less. Although the field is very strong, but charge carrier is less only. So the current will saturate. Did you understand this point or not? My VGS is 0. I am not talking about VGS. What I am doing, I am increasing my drain potential. If I am increasing my drain potential, what did I get to know? That most of the potential will come across the channel itself. That means there will be a reverse bias. So because of the reverse bias, there will be a depletion region, and in the depletion region, there will be electric field. What this electric field will do? This electric field will attract these electrons, and if attract these electrons, the current will flow. If I keep on increasing the drain potential, what is going to happen? If I keep on increasing the drain potential, the electric field will be stronger and it will attract the electrons more. It will attract the electrons fastly and the current will increase. But at a certain VDS value, what's going to happen? In the channel, there will be very less charge carriers. Although the field is strong, although the electric field is very strong, but still there are lesser charge carriers, and because of that, the current saturates. So this is the complete concept of N-type, N-channel depletion type MOSFET. Did I write N-type there? When I showed the classification, I guess I write N-type. N-type. Oh, look, this should be N-channel. Shouldn't be N-type. N-channel. So this 30 minutes of this video was the most important part. If you are able to understand this 30 minutes, rest 2 hours or 2.5 hours will be very easy for you. This is the most important part only. So here I explained you what is MOSFET, why it is called MOSFET, metal oxide semiconductor field effect transistor. What is the meaning of the source, drain, gate and channel? What is the meaning of FET? then I showed you this analogy, then I told you what will happen if I apply positive potential at the drain. So what will happen? So first we understood this analogy that this can be replaced with the resistance. R channel is the higher resistance, R drain is the lower resistance. So if I am giving 8 volt here, the most of the potential will be coming towards the channel only. So because of that, here we can see that there is a PN diode there. So now all the diodes are reverse bias. Because of the reverse bias, there will be depletion region. Now if I am giving positive supply at the drain, that depletion region will induce an electric field. So because of that electric field, the electrons are swept away in that drain terminal and the current flows. If I keep on increasing the VDS value, what will happen? The electric field will be stronger and that will attract the electrons fastly and current will increase. But at a certain value of VDS, the channel will be, I will not say that channel will be depleted of charge carriers. I will say that in the channel there will be less charge carriers. Although the electric field is strong, but charge carriers are low only. So that is the reason why the current saturates. That's it. That's the complete concept. I hope you are able to understand. Now we are going to write everything that we have said. So what if I increase VDS? So now what first thing I should write is that VDS is positive, then uh, electric field E is generated. E will sweep away the electrons in drain terminal. And the current flows. What will be the direction of current? Electrons are going in this direction. From source they are coming from the channel and then they are going to drain. Electrons are going in this direction. Then what will be the direction of current? The direction of current will be from drain to source. Because the direction of current is always opposite to the motion of electrons. Electrons are moving from drain to source. Sorry, from source to drain. From source to drain. So the current will flow from drain to source. Now what if I increase VDS? If I keep on increasing the VDS, that electric field E will be stronger, electrons will travel fast and the current increases, right? But the current increases, but the saturation level I did not explain, no? So here I will explain the saturation level. So here the current will increase, but after a certain value of VDS, the current saturates. So here I will write about the saturation. But at a certain value of VDS, the channel will start having very less charge carriers. Although the field is although the electrical field is strong, but the charge carriers are less. Charge carriers are less, and because of that current saturates. that current saturates. Okay, and this all was happening at VGS equals to 0. So first it increases and then it saturates. So at this potential it saturates. This potential is known as VD set, VDS set. Okay, and this is known as IDSS, saturation voltage, saturation current. I generally write it as ID set. ID set. Well and good. Now we have seen the effect of VDS and increasing VDS. Now we will see the effect of VGS. What will happen if I apply VGS? So now VDS is positive, that is there, that I can call, that is fixed. Now I will vary my VGS from negative potential. I can vary my VGS from -5 to +5, and I will see how what happens. Initially there was no VGS, VGS was 0, but now I am varying my VGS from -5 to +5. So what happens, that I will see. So now my VGS is negative. So this is negative, and this I have made channel only. So this negative, this will repel the electrons. This will repel the electrons. Or for better understanding, I should make something like this. Why this is grounded? This shouldn't be grounded. This is channel only, right? So I am giving a negative supply. That means I can make a battery something like this. Now where will this node go? This node will go to body. I am connecting the supply here like this. This is what I am doing. I am connecting the supply like this. Understood? So what is happening? What this will do? This is the positive side. This is the positive side. So what this will do? This will supply holes. So this holes will first get into the substrate. Then it will go to the channel, right? Or what you can see that because of this positive supply, the holes in the substrate, this is the substrate, the holes in the substrate will be repelled by this positive supply. So they will go into the channel and will recombine with these holes. So these holes will be, recombine with the electrons, and these electrons will be eradicated from there. So if you are giving the negative supply at the gate terminal, what is happening? Your channel is getting depleted of charge carriers. What you can see, because of this negative supply, what you can see that these are getting repelled. This is one analogy. This is one way of understanding it. What can be the other way? Other way is that you are applying a battery. So from here, holes are going there, and you can say that positive supply is there, and in the substrate we are having p type. In the substrate we are having p type. So in the p type, these holes will feel the repulsion. So these holes will go into the channel and it will recombine with the holes. And because of that, the channel is getting depleted of charge carriers, and there are less charge carriers. That means there will be lesser current. So current is decreasing. Did you understand this point? Very simple. Negative potential is there. You can see that electrons are getting repelled. This is the one phenomena you can see. Or what can be the other phenomena? That because of the positive supply, the holes are getting repelled. Holes are getting repelled and they are going into the channel. And because of that, the electrons are getting recombined and channel is getting depleted of charge carriers. That's it. So what we can see that if Vg is going down, or I should write, if Vg is increasing in negative direction, what I can write, if Vg is increasing in negative direction. What do I mean by increasing in negative direction? Increasing in negative direction, this is the negative direction. So -1, -2, -3, you will understand, right? Vg is increasing in negative direction. So if Vg increases in negative direction, if Vg is increasing in negative direction, that means what is happening? Vg is increasing in negative direction. The channel is getting depleted of charge carrier. Getting depleted means the charge carriers are getting less. Getting depleted of charge carriers. And what does that means? Current will be decreasing. Current is decreasing. So if gate potential is negative, the current decreases. And what will happen if we keep on decreasing the VGS value? Keep on decreasing the VGS value, what do I mean? That gate potential is increasing in negative direction. That means -3, -4. At some potential, we are just decreasing the negative, we are just decreasing the VGS value. That means we are increasing in negative direction. So we keep on decreasing the VGS value. So if we keep on decreasing the VGS value, then at some negative VGS value, the channel will be depleted of charge carriers, and there will be a very high electric field in the vertical direction. This is the positive supply and this is the negative supply. So what will be the direction of electric field? Yeah, so there is an error in this one, that this should not be there, because to the substrate we are giving the holes, right? This is the supply. So what is the scene? That here we are having the oxide layer. Here we are having the oxide layer, and above that we are having the substrate. Not substrate, we are having the metal, sorry. And here we are giving the supply. So we are giving the supply like this. Negative supply we are giving, and positive supply will be given to the substrate. Here substrate. So we are actually delivering the holes. So this I made here, that is wrong. This should not be happening. So there will be electrical field, but which electric field? Here there is negative potential here. This is the negative potential. This is going towards body only. So let's just write body here. So this is the negative potential, and because of this negative potential, these are getting depleted of charge carriers. So there will be an electric field, that will be this. This will be electric field there. Metal, oxide, and semiconductor. At metal you are having negative, here you are having positive. So there will be this electric field. This electric field will be there. Now what will happen? This source will try to supply electrons. This source will try to supply electrons. The electrons, what will electron try to do? Electron will try to travel from the channel and go towards the drain. But there will be so much of high electric field that just as it enters the channel, it will travel in this direction. The electron wanted to go from source to drain side. The electron wanted to go from source to drain side. Electron came out of source side. Since there was very high electric field, this was the trajectory of electron. This was the trajectory of electrons. Electron wanted to go like this, from source to through channel to drain, but there was so much of high electric field that it goes like that. I will not say that my channel is depleted of charge carriers. At some place I have seen that they say that the channel is depleted of charge carriers, but channel is not depleted of charge carriers. In the channel, charge carriers are there. There can be some charge carriers, but there is so much of high electric field that the motion of electrons will be downward. So the reference of this thing I took from Kamesh sir. There is no harm in taking his name. So just the EDC concept, this is the concept of EDC. So that I took the reference from Kamesh sir. So there is no harm in taking his name. But the concept of analog electronics are mine only, that I framed. So I am not completely copying, I am not blindly copying. This reference I took from him. So the credit goes to him for this kind of concept, or this concept. Rest of the part is mine only. So I'm not just credit should be given to the teacher who has taught this. So I have been one of his students for EDC, not for analog. I haven't studied analog from him, but for EDC I have studied. So from there I am taking this reference. That electron comes and then there is an electric field. So trajectory of electrons will be downward. So the electron doesn't reach the drain terminal. So the current becomes 0. So this is what I have written. At some negative VGS value, the channel will be depleted of charge carriers. I haven't written completely depleted of charge carriers. The channel will be depleted of charge carriers, and the electric field is the electric field in vertical direction will be so strong that electron from source side will not be reaching towards the drain side. Electron from source side will not be reaching towards the drain side, and the current becomes zero. So even if you have applied positive potential, there is no meaning of this positive potential because electrons are not even reaching there. The positive potential will be useful if the electrons reach there and this positive supply can attract those electrons. But this is not even useful because electrons are not even reaching there because of this very high electric field. Did you understand this point? So if we are decreasing the VGS value, that means if we are increasing the negative supply at gate potential, the current will slowly start decreasing, and at some negative potential, the current will be zero. And this negative potential is known as pinch off. This negative potential is known as pinch off voltage. So this negative potential is known as pinch off voltage. So this is this is the reference that I have took from Kamesh sir, and rest all the content is mine only. Diode circuit, and further in most amplifiers you will study a lot of concepts that are mine only. So that is not taking although those reference I am taking some textbook, Rajavi's textbook I am following Cedra Smith, and I am also following other textbook as well. So from those textbook I am taking those reference. For a particular teacher I took this reference from Kamesh sir only. So that's why I took his name. Okay. Yeah. So negative potential is known as this pinch of voltage. Well and good. Now, what if I am increasing the VGS value now? That means I am giving positive supply to VG. If I am giving positive supply, what will happen? This will attract the electrons, right? It will attract the electrons, and the channel will be, in the channel there will be more charge carriers, and if there is more charge carriers, that means there will be more current flow. Or how you can understand it? You are giving positive supply, and then there will be this body terminal. So from here electron will go, right? Electrons, and they will be going into P substrate, and from P substrate what are there? In P substrate these are there. So first these electrons will recombine with these holes. First these electrons will recombine with these holes. After that some of the electrons will reach here and will enhance the channel. Will enhance the channel with electrons, with free electrons. So in the channel we will have more electrons, and if there are more electrons, that means there will be more current. So from the negative supply, electrons are going there. Some are recombining with the holes, and some are going into the channel, and because of that we are having more electrons in the channel, and the current increases. So what do we say? If Vg is increasing, that means there will be more electrons in channel, and that means the current will increase. If you just understand one device, that means n channel depletion type MOSFET, if you understand, then it will take minimum effort in understanding p channel depletion type, n channel enhancement type, p channel enhancement type. So within 1 hour you will be able to understand everything. Just this part is typical. After that everything will be cakewalk, and I guess I have explained it that much of nicely that you are able to understand. This doesn't seem typical to you. I hope this is not typical to you now. Every concept is crystal clear to you, right? So let's move on to the graph now. This is the characteristics. So first we draw for VGS equals to 0 volt. That first it increases and then saturates. If my VGS is negative, that means the current will be decreasing, and if it is my positive, then that means the current will be increasing. So I could have made this graph, then it would be for VGS equals to 2 volt, right? But we are not making it, just telling you. If I have made this graph, this would have been for VGS equals to minus 2 volt, and at VGS equals to VP, what is happening? The current is 0. At VGS equals to VP, the current is 0, because there will be so much of negative potential that the channel will be depleted of charge carriers, and electron from source side cannot go towards the drain side. So the current will be 0. Did you understand this complete concept? This curve you understood, right? Initially the current increases and then saturated based on VDS value. This is ID versus VDS curve. So if we keep on increasing VDS, it doesn't mean the current will keep on increasing. Why it saturates? Because the channel will have lesser charge carriers. There will be high electric field, but the charge carriers are less, so the current saturates. And if we are increasing VGS value, then what will happen? The current is increasing, right? Let's draw the ID versus VGS curve. So how will the ID versus VGS curve look like? For this potential, for VGS equals to VP, the current is 0. After that, the current keeps on increasing, right? This is for, let's just say this is for one particular VDS value. Let's call this as VDS1. Now I will make 2 more graphs, and you have to tell me the relation between VDS1, VDS2 and VDS3. This is VDS2 and this is VDS3. So tell me, what is the relation between VDS1, VDS2 and VDS3? VDS3 is more than VDS2. Okay. This should be VDS2 and this should be VDS1. VDS2 and this I can call VDS1. So VDS3 is greater than VDS2 is greater than VDS1. Why so? If you increase VDS, what happens? The current increases, at least till this region. So here one thing I should write, that VDS value is not that much large that the current is saturating. The current is not saturating. The VDS value is such that the current is not saturating. Here VDS1, VDS2 and VDS3 are such that the current is not saturating. So this potential of VGS, at a particular potential of VGS, which current is higher? Let's just assume I am applying VGS equals to 1 volt. This is VGS equals to 1 volt. At VGS equals to 1 volt only, in this curve you are getting this much of current. Let's say this is 5 ampere. In this curve you are getting 3 ampere. In this curve you are getting 1 ampere. So you are getting maximum current in VDS3. That means VDS is highest. Because if you increase VDS, the current increases. At least the current never decreases. If you are increasing VDS, the current is never decreasing. So if at the same potential at 1 volt only, if you are getting more current, that means VDS is higher. Did you understand this? This is simple mathematics. This is the question of mathematics, not the analog electronics or electronic devices. Did you understand it? At the same VGS potential, VGS is same. At that same potential, one of the curve is giving me more current and one of the curve is giving me lesser current. So the curve which is giving me more current, that means there is high VDS. If there is high VDS, that means there will be high depletion region, that means there will be more current. So VDS3 is higher than VDS2 is higher than VDS1. Well and good. So this we have studied completely N-channel depletion type MOSFET. Just by seeing this structure, are you able to comment on the complete N-channel depletion type MOSFET? So in one go only I will comment on complete depletion type of MOSFET. So what happens? First I apply VDS equals to positive voltage. If I apply VDS positive voltage, most of the potential will be going towards the channel only, and the potential will be equally distributed from drain to source. At the drain side you will be having the maximum potential. If you are having the maximum potential, that means there will be the maximum reverse bias between N and P. If there is maximum reverse bias, that means there will be highest depletion region, and the region will keep on decreasing with the moving towards drain to source. And if there is very high depletion region, that means there is very high electric field. So the electrons that are present in the N channel, they feel very high electric field and swept away in the drain terminal. That's why the current increases. If you keep on increasing the drain potential, what will happen? The reverse bias will increase more. That means depletion region will increase more. There will be more electric field and the current will increase. But if you further keep on increasing VDS value, what will happen? The electric field will be so strong, but the channel will be depleted of charge carriers. In the channel, we will have less charge carriers, and because of this less charge carriers, although the field is strong, but the charge carriers are less, so the current saturates. The current will be saturated. So ID versus VDS curve will look something like that. That if we are increasing VDS, the current will increase, but after that the current saturates. Now what about VGS? Now my VD is positive potential, that is fixed. Now I am applying VGS potential. If VGS was 0, even though there was no VGS, still there was some current. Now I am applying VG value to be negative. If I am applying VG value to be negative, what it will do? It will supply the holes to P substrate, and these holes will go towards the channel as well. That will recombine with the electrons. Those holes will recombine with the electrons, and in the channel we will have lesser electrons now. In the channel we are having lesser electrons. So that means our charge carrier is less. Here what is our charge carrier? In this N channel, what is our charge carrier? Charge carriers are electrons. Charge carriers are electrons, not holes. Because electrons travel from like this. Charge carriers are electrons. So charge carrier will be less, and because of that the current is decreasing. So if you keep on decreasing the value of Vg, that means in the negative direction, if you are increasing the Vg potential, that means more negative Vg, lesser current. So if Vg is more negative, that means the current is lesser. If Vg is more positive, that means it will provide electrons to P substrate, and that will come into the channel. So that will increase our charge carriers, and because of that the current increases. So this is the complete concept of N channel depletion type MOSFET. Crystal clear? Now you can comment on P channel depletion type MOSFET on your own. Tell me one thing, what will be the charge carrier in P type, in P channel depletion type MOSFET? What will be the charge carriers? Holes, right? Holes will be coming out of here and it will travel like this. What should be the potential at drain? In the N channel, what was the potential at drain? Positive. The potential at drain was positive. Source will always be shorted, and source will always be grounded, and source and body will always be shorted. So what should be the potential at drain? Negative or positive? What is the diode here? Diode is this. What do you need? You need depletion region. If you need depletion region, that means you need to apply negative potential. So at drain you need to apply negative potential. So if you apply negative potential, what will happen? The depletion region will increase. What will be the direction? Direction of electric field will be this. The direction of electric field will be this. Why it will be this? Because here you are having negative and here you are having positive. So the direction of electric field will be this. This will be the direction of electric field. And there are holes available here. If there are holes available here, so in the direction of electric field, they will be swept away. So the holes are traveling like this. If the holes are traveling like this, that means what will be the direction of current? So the direction of current will be from source to drain, because the current direction is same as the direction of holes. The holes are traveling from source to drain. Because the electric field is this, that means in the direction of electric fields only holes travel. Do you know these things? The first thing is that electron travels in the opposite direction of electric field. Electron travels in the opposite direction of electric field. And the current direction is opposite to the motion of electrons. If electrons are traveling here, that means the current will be here. One more statement. Holes travel in the direction of electric field. If the electric field is this, that means hole will also travel here. And current flows in the direction of the motion of holes. If the holes are flowing here, that means the current will be here as well. So these statements we have understood in the first chapter only, basics of semiconductor physics, when we studied diode. So there we understood it. So just making you remember it. Okay. So if the holes are traveling from source to drain, that means the current will be from source to drain as well. So what will be the current direction? Current direction will be source to drain. Source to drain. Current direction is source to drain, right? Now what will happen if you keep on increasing the VDS value? If you keep on decreasing the VDS value, that means if you keep on increasing the negative supply, if drain is becoming more negative, what will happen? There will be more reverse bias. More reverse bias, that means more depletion region. More depletion region, that means current will increase. But at a certain negative value of VDS, the current saturates, because even though electric field is strong, but the channel will have lesser charge carriers. Because of that, the current saturates. Did you understand this point? Can you draw the graph now? What is the ID direction? ID direction is source to drain. Source to drain. What was the ID direction in N channel? In N channel, what was the ID direction? The electrons were moving from source to drain. So the direction would be drain to source. Whether it is P channel or N channel, always the charge carrier will move from source to drain. If the charge carrier are holes, that means if holes are moving from source to drain, that means the direction of current will be source to drain. If charge carriers are electrons, that means electrons are moving from source to drain, that means the direction of current will be from drain to source. Very easy, very straightforward. Here your VDS is negative and you are increasing the VDS value in negative direction. So your graph will be something like this. Say yes or no. You are increasing the VDS value in negative direction. So your graph will be something like this. And at some point it will saturate. Did you understand it? Right? It is the same as N channel depletion type MOSFET only. Okay. And since we are about to complete this depletion type MOSFET, so I want to tell you one thing, that depletion type MOSFET is not important that much. No one there is very rare chance that they will ask you question from depletion type MOSFET, because depletion type MOSFET are not used for amplification. I will tell you the reason why it is not used for amplification. But till now, can you guess why it is not used for amplification? Why depletion type MOSFET is not used for amplification? Can you guess? What did I say? We are designing an amplifier. In an amplifier, what did we say? That the current that we are having, that should be depending on the input voltage. That should be depending on the input controlling voltage. What is our controlling voltage? Gate. Gate is our controlling one. Tap. Gate is our controlling one. Even if I am not applying any gate voltage, when VG was 0, still there was some current. In the depletion type of MOSFET, the channel was already there. Because of that, even if I am applying VG, even if I am not applying any VG potential, VG is 0, I am not applying anything there. Even with the bias only, just with the bias, just with the drain potential, I am getting some current. And because of that, I will have some output. So your current is not depending on the VG value. Even if there is no VG, still you are having the current. And this is not what I want. I want my current to depend on the VG value. So that's why you can't use depletion type of MOSFET. Did you understand it? We will write it in later on, and I will explain you once more, but here only I explained it. So just now we are about to complete it, so that's why I am telling it. It's not that much of important, but to understand the now if you have understood the depletion type of MOSFET, the enhancement type of MOSFET will be a cakewalk for you. You will understand it very quickly. Otherwise, you would have got confused in enhancement type MOSFET. But now the path is crystal clear to you. What is depletion type and what will change in enhancement type, that we will see in next lecture. Okay, so this will be VD set. VDS set. Well and good. This is ID set. And what about this curve? ID versus VGS curve. So let's talk about VG. So what potential should I apply here? If I apply positive potential, what will happen? There are holes here. So because of this positive potential, they will be repelled. Or what you can think, if you are applying positive potential here, that means electrons will be coming here. From the negative side of battery, electrons will be coming here and they will be recombining with the holes. And if they are recombining with the holes, in the channel, there will be lesser charge carriers. And if there is lesser charge carriers, that means there will be lesser current. So if gate is positive, that means there is less current. And if I keep on increasing the positive voltage, that means if I keep on increasing the VG value, at some positive voltage, what will happen? The channel will be depleted of charge carriers and there will be very high electric field in this direction. There will be very high electric field in this direction. So if a hole comes here, it will follow this path because of this electric field. And if it is following this path because of this electric field, it will not reach through to the drain side and there will be no current. So at some positive potential of Vg, there will be no current in the transistor. Well and good, understood? Just the opposite of that. We don't need to write it all, just the opposite of that. So this will be Vp. So when the gate is positive, if you keep on increasing the positive potential, what will happen? The channel will have very less charge carriers. Also, there will be very high electric field from down to up, and because of that, the holes which are coming from source, they will not reach the drain side and there will be zero current, and that potential is known as pinch off voltage. This is the pinch off voltage. And if you increase it in negative direction, if you increase it in negative direction, if you apply Vg to be negative, what will happen? This here there will be positive supply, so this positive supply will deliver holes. Some will recombine with this and some will reach to the channel. So some holes will reach to the channel and some will recombine, and those electrons, those holes will reach to the channel and our charge carriers will be more. If there is more charge carriers, that means there will be more current. That's it. Understood? So I'm not writing it all. I hope you have already understood because we have spent a lot of time in understanding N-channel depletion type MOSFET. This is just the opposite of that, nothing else. Right? So this is the N-channel, this is P-channel depletion type MOSFET. So if you increase the Vg in the negative direction, the current will increase. And what is the direction of current? Direction of current is from source to drain. Understood? All clear? So in this lecture, we have studied about depletion type of MOSFET. One more note will be there, that will be in depletion type of MOSFET. This I already explained, that in depletion type of MOSFET, the channel was already present. Even if I don't apply any potential at the gate, that means even if my VGS is 0, still there is some current. Look, here my VGS is 0, still there is some current. Even if my VGS is 0, there is some current. In the previous curve also we have seen, even if my VGS is 0, there is still some current. So my output current is not depending on the controlling voltage. This output current is not depending on the controlling voltage. Even if there is no controlling voltage, still there is some current. So that's why you can't use it as an amplifier, because as an amplifier, what did I need? I showed you. As an amplifier, what do I need? As an amplifier, I need a current which is depending on current or voltage, whatever it can be. I need a dependent source which is depending on my input, and which is not happening in our case. Understood? Although this R naught I should have shown in parallel, not in series. If I am making the current source, it should be in parallel. We will learn it. Here, this is a mistake. It should be in parallel. Yeah. So this requirement is not fulfilled by depletion type of MOSFET. So this requirement will be fulfilled by enhancement type of MOSFET, and how it will be fulfilled, that we will see in the next lecture. Okay, so this is written here, how it will be filled. So here there is no channel present. So we will have to make the channel by our own. By how? How we will make the channel? By applying the supply here. So now my current will be depending on the supply that I am giving to the gate. So my current will depend on that, and I will fulfill my requirement of an amplifier. So this question is a lot of time asked in the interview, that why you can't use depletion type of MOSFET for amplification and why you use enhancement type of MOSFET for amplification. So this is the reason. So in the next lecture, we will study about enhancement type of MOSFET. Okay, thank you. Hi everyone. So continuing our previous lecture, in this lecture we are going to study about N-channel enhancement type MOSFET. Previously we studied about depletion type MOSFET. So now what is the major difference between enhancement and depletion type MOSFET? In depletion type MOSFET, the channel was already present. Here there is no channel. There is no channel. In depletion type of MOSFET, there was this N channel present, but now there is no channel. So no initial channel. No initial channel. So here you will have to frame the channel by your own by applying some gate potential. No initial channel. So if my gate potential is 0, no matter whatever you applied at the drain, what we will do, we will always keep source as a reference, and source and body will always be shorted. Now if my VGS is 0, no matter whatever you apply at VDS, there will be no current, right? If my gate is 0, no matter whatever you apply at the gate, there will be no current. Let's see the condition one by one. Let's take the first condition. When VGS and VDS both are 0, absolutely nothing is there. So certainly there will be 0 ampere current, no current is there. VGS is 0 and VDS is negative. Here you are applying negative potential. Negative potential. This is the scene here, right? N and P. You are applying negative potential. You are making it forward bias. The depletion width is small. The electric field is less. You are applying negative potential here. The electric field is less. The depletion width is low. The electric field is less. And here, what is happening? Here, this P-type substrate is there. This is P-type substrate. So, what can you expect? That this will be positive and this will be negative. But since you are applying negative potential, there will be very less electric field. The electric field will be in this direction. Now, this can attract the holes. Still, there is very less electric field. Still, we are thinking, what if it attracts the hole? If it will attract the hole and will give the motion in this direction. It is not getting out of the drain. The motion will be from drain to source only. So that is irrelevant. That is needless. If you are applying negative potential, there is no meaning that you will get some current. So we can't apply negative potential. At least we will have to apply positive potential. At least we will have to apply positive potential. So at the negative potential, you will have 0 current. This will be 0 current. Now still my VGS is 0. I am applying positive potential now. So if I am applying positive potential, what will happen? This will be reverse bias. So because of that, there will be high electric field. But whom will this high electric field attract? Are there any electrons? If there was any electrons, they would have gone here. Now these electrons cannot be attracted by this electric field. Why so? Why so? Because there is no channel. Even if this electron is attracted by this electric field, what will happen? In the channel, what is there? In the channel, there is this P-type substrate. So even if this electron is attracted, what will happen? This will be recombining with this hole. So there is no chance that they will be reaching towards the drain and current will flow. So even if you have applied positive drain voltage, still there is no current. Because the gate potential is 0. You have to frame the channel. That's the main task. How will you frame the channel? Now that is the problem. So tell me, what potential you will apply to frame the channel? Positive gate potential or negative gate potential? What do you think? I should apply positive gate potential or negative gate potential? Take your time and think about it. I should apply positive gate potential. Why so? Because if I apply positive gate potential, what will happen? There will be negative node here. If I am applying positive here, positive to gate, so there will be negative node here. So this will supply electrons. This will supply electrons here. And some of the electrons will reach here. Some of the electrons may reach here. Some of the electrons will recombine with these holes, and then if you keep on increasing the VG potential, what will happen? Some of the electrons will reach here, and then it will frame the N channel, and then the current can flow. So we have to apply positive potential. At least this thing we got to know. If you apply negative potential, it will not work. So we have to apply at least positive potential. So here also the current will be 0. Now what I am doing, I will apply some positive potential at the gate. So here I am applying some positive potential and drain is also at positive. But the positive potential that I have applied, that is very less. That is very less, not much. So what will happen? This is the positive potential I am applying, this is the negative potential. So electrons are being supplied. Electrons are being supplied here. Right? And here what is there? This is the condition here. Also the same condition is here. Now electrons are reaching there, and some electrons are recombining with these holes, and some electrons are recombining with these holes. So you have to keep on increasing the Vg value. You have to keep on increasing the Vg value. More Vg value means more electrons. So now more electrons will recombine with the holes. So when they recombine with the holes, what will happen? Look, Vg is positive. That means electrons will come into substrate. Come into substrate. They come into substrate, and what they do? They recombine with the holes. Now my Vg is that enough that these electrons, no, what I shouldn't say these electrons, these holes have been recombined. So in the channel, what do you have? I'm saying that in the p substrate, these holes are recombined. These holes have been recombined. These holes have been recombined. So what you will have? You will have this. Now will there be any current? Can you say these are electrons? Will they conduct any current? No, they will not conduct any current. Why so? Because they are mobile ions. What they are? They are mobile ions. Mobile ions which cannot conduct current. Cannot current conduct. Cannot conduct current. So my Vg value is such that these holes have been recombined. These holes have been recombined, but still they cannot conduct current. To conduct the current, you have to apply more Vg potential. So still ID is 0. That means I have to increase Vg potential. I have to increase Vg potential. At some positive potential of Vg. At some positive potential of Vg, the channel will be framed. The channel will be framed. What do I mean by that? Now what is happening? These holes have already been recombined, right? These holes have been recombined. Now further more electrons will be coming now. More electrons will be coming. More electrons will be coming here. More electrons will be coming here. Now these electrons will go and stabilize here. Are you understanding this point? Now they don't. Now these electrons have no work. They are not going to recombine with the holes. Those holes have been recombined. Now these electrons can go and stay here. It's not exactly over this. Okay, just anywhere they can be. Anywhere they can be. They can be here. They can be here. They can be here. They can be here. And this frames the n channel. Because what is n channel? If you forget about this mobile ion, in the n channel there is these electrons. So this will frame the n channel. And our substrate was P. Our given substrate was P. But in this P substrate, we have made the N channel. That means we have inverted the P substrate. In P substrate, we have made the N channel. So we have inverted the P substrate. So that's why it is known as inversion layer. Are you getting this point? So more and more electrons are supplied. And because of that, what is happening? A channel will be framed. That will have electrons. This channel will have electrons. And this layer is known as inversion layer. Why it is known as inversion layer? Because in P channel, in P substrate I should say, in P substrate we have framed N channel. So we have inverted the P substrate. So that's why it is known as inversion layer. So now at some positive potential of Vg, the channel is framed and the current flows. And now since the channel is present now, since the channel is present or present, since the channel is present now, So the current ID flows. Now the current ID will be finite. Okay, so how the current will flow? The same thing, because at drain side you are having positive potential, that means you are having high reverse bias. If there is high reverse bias, that means there is high depletion region. If there is high depletion region, that means they will attract the electrons. If they will attract the electrons, they will attract the electrons in this direction. That means what will be the direction of current? The direction of current will be this. So the current will flow from drain to source. This I don't need to write, that depletion region, attraction, that we have already studied in depletion type of MOSFET. So the same phenomena is happening here. So the current flows, the direction of current is from drain to source. From drain to source. Just one thing, always keep on revising this device physics, whether it is basic semiconductor physics or MOS physics or BJT physics. Always keep on revising the device physics, otherwise you will forget it. Even the teachers have to revisit the concept when they are going to teach. Device physics is something which can be very forgettable. Okay, it's something very forgettable. It's like Gautam Gambhir. Okay, forget it. So, so direction of current is from drain to source, because the direction of charge carriers, which are electron, are moving from source to drain. Charge carriers are moving from source to drain, so the current will be from drain to source. Current will be from drain to source. Now at some positive potential of Vg, so at some positive potential of Vg, this thing is happening. So the potential, so the gate potential at which the current flows, that potential is known as threshold voltage. Did you understand it? At some positive potential of Vg that is happening. So the value of VGS, the value of VGS at which the current flows is known as threshold voltage. So that potential is known as threshold voltage. Threshold voltage, which we show by VT. VT. This is not thermal voltage. This is threshold voltage. This is shown by VT. This threshold voltage. Well and good. So now, if my VDS is positive and if I apply VGS greater than VT, if I am applying VGS greater than VT, that means now the current will flow. ID flows. How it flows? Because VDS is positive, that means, and VGS is greater than VT, that means here the channel is framed. The channel is framed, and secondly, VD is positive, that means there is this high electric field. There is high electric field. This is the high electric field. So because of this high electric field, these electrons will travel. I should use different color of pen. These electrons will travel in this direction, in the opposite direction, and will get out of the drain, and the current will flow. Well and good. Electrons will travel in this direction, will get out of the drain, and the current will flow. The current flows. This is the same phenomena as the depletion type of MOSFET. Our target was to frame the channel, and how it is framed? By applying the positive potential at gate. And this we are studying for what? N-channel enhancement type of MOSFET, and the other name of this MOSFET is NMOS. You call it NMOS as well. By N you will get to know that it is N-channel. So substrate will be of P, the channel is N, that means we will frame the channel N. So in NMOS you need to apply VG to be positive and drain also to be positive. Both you need to be positive. So in NMOS you need both drain and source to be positive. So this is the first condition where the current flows. This is the condition where the current flows. So ID flows from drain to source. So in NMOS the current flows from drain to source. And these are shorted only. Both are grounded. Well and good. Now what do we need to see? We will see at that after VTH, if I am increasing VGS, what will happen? If I increase VGS, what should happen? If I increase VGS, that means more and more electrons will be coming here. VGS is positive. So from here, negative side of battery, electrons are coming. Electrons are coming. So more and more electrons will come. More and more electrons will come. That means in the channel we will have more charge carriers. Electrons will increase. In the channel, electrons will increase. That means if more electrons are there, that means there is more current. So if we are increasing VGS, there will be more electrons in the channel. And if there are more electrons, that means there will be more current. So ID will increase. So until VT was some positive potential. So till this point, there was no current. Till this point, there was no current. And then suddenly the current rises. And the current rises in a square law manner. Why it is square law? No one will ask you. The current rises in square law manner. Why it is square law? We have to derive it. And no one is going to ask you the derivation. Intuitively, you can't tell why it increases in square law manner. We have to derive it with taking some approximation and all. So we will just see the relation. We will just see the expression. What is the expression? So it increases like this. Well and good. Not necessarily it will be square law. It depends on the region, linear region and saturation region, that we will see. So till this time there was no current. So this region is known as cutoff region. Cutoff. Why it is cutoff? Because there is no current. And this curve is very, very important. This curve is very, very important. Well and good. Now condition 6 is, now my VGS is greater than VT, which is fixed. That means I have given enough gate voltage to conduct the current. Now my VDS is also positive, but VDS is increasing. That means I am increasing my VDS voltage. So I guess I can simply copy this one. I am increasing my drain voltage. So what will happen? If I increase my drain voltage, initially the current will increase, but later on it will saturate. The same thing that we studied in depletion type of MOSFET. What will happen? If VDS is increasing, then depletion width increases. Instead of that, I should directly write electric field. E field will increase. If E field increases, that means electron gets more force. If electron gets more force, that means there will be more current. More current. But at some value of VDS, at some value of VDS, what happens? At some value of VDS, let's draw the channel. So at some value of VDS, what happens? The channel is getting depleted of charge carriers. Although the electric field is strong. This is N channel, no? Yeah. Although the electric field is strong here. Okay, I don't need to make the plus minus ions. If I am increasing VDS, what is happening? The channel is getting depleted of charge carriers. So from here to here, VDS is increasing. To go from down to up, your VDS is increasing. So if VDS is increasing in the channel, this is the channel is getting depleted of charge carriers. Initially this much of charge carriers were there, but slowly the channel is getting depleted of charge carriers. Although there is strong electrical field, but still the charge carriers are less, so the current will saturate. At some value of VDS, I will directly write the current will saturate, because you know the region. What is the region? At some value of VDS, the current will saturate. Why it will saturate? You know the region. The current will saturate. So initially it increases linearly, then at some point it saturates. After that it saturates. So yeah, I forgot to tell one thing. This region. So here it is saturating now. Here. So this region is known as linear region. This is linear region because here the current is increasing linearly, and the further region is known as saturation region. Here the current is saturated. So in the previous graphs as well, where we drew it, in these graphs as well, you can show that these are linear region and this is saturation region. This is the enhancement type graph. Okay, these are the previous graphs where I forgot to write. And one more thing, in depletion type region, this mode is known as enhancement mode and this mode is known as depletion mode, because here the current is decreasing and if VGS is high, their current is increasing. This is not important, no one will ask you about it, but still just for information, this mode is known as enhancement mode and this mode is known as depletion mode. This is for depletion type of MOSFET, which I forgot to write in the previous lecture. Yeah. So where we were? So here we have drawn the characteristics, right? Now we can draw the final characteristics which I have already drawn. Now you need to tell me the relation between VDS3, VDS2 and VDS1. Tell me which one will be the highest one. At a particular VGS, in one curve you are getting highest current, in one curve you are getting medium current, and in one curve you are getting lesser current. That means in one of the MOSFET, in one of the condition VDS3, in this condition there is the maximum current. That means here the drain voltage is at highest. Drain voltage is at highest. Drain voltage is positive, very positive. It is very positive. So it is very positive. So there will be high electric field. If there is high electric field, that means it can sweep up more electrons. If it can sweep away more electrons, that means there will be more current. So VDS3 is higher than VDS2 is higher than VDS1. You don't need to mug it up. You need to understand the logic. What is the logic? Tell me what will be the logic here. Which will be higher, VGS3 or VGS2 or VGS1? Here your VDS is same. VDS is the same. VDS is constant. Now you are increasing the VGS value. If you increase the VGS value, what will happen? If VDS is same, if you are increasing VGS value, that means you are increasing positive potential at gate. If you are increasing positive potential at gate, that means electrons will be supplied. If electrons is supplied, that means in the channel you will have more electrons. If you are having more electrons, that means more current. So if you increase positive potential at gate, that means the current will increase. So here, which is the maximum current? This is the maximum current. That means this VGS is the maximum. So VGS3 is greater than VGS2 is greater than VGS1. Are you able to connect? If you are listening to me with your full concentration, then only you will be able to understand. You should have full concentration here. What did I say? More VGS, that means more current. More VGS, that means higher positive voltage, that means more electrons are supplied. If more electrons are supplied, that means in the channel we are having more electrons, so more current. So more VGS, that means more current. More VDS, that means more current. So VDS3 is higher than VDS2, higher than VDS1, and here this is the relation. So this was our N-channel enhancement type MOSFET. So what did we do here? If here VGS is 0, if there is no VGS, we are not having any current. So we have to give some threshold voltage. We have to apply some minimum voltage to get the current, right? So this can work as an amplifier. Now my current is depending on my VGS voltage. At that time, although my current was depending on VGS voltage, but even if I haven't applied any VGS, still I was getting some current. So that is undesirable, right? Now we are getting a desirable thing, that is, if there is no VGS, the current is 0. So for the current to flow, VGS should be greater than VT. For the current to flow, VGS should be greater than VT and VDS should be positive. Now, here the current saturates in this region, the current saturates. So at what potential of VDS the current saturates? This potential is known as VD set. Here the current is saturating, right? VD set. So what is that potential? That potential is applied VGS. This curve is there for some particular VGS value, right? Applied VGS minus VT. This curve is there for a particular VGS value, right? So for this curve, what will be the threshold voltage? Tell me, for this curve. For this blue curve, what will be the threshold? What will be the saturation voltage? Not threshold voltage. What will be the saturation voltage? For this blue curve, the saturation voltage would be VDS1. I can write, what would be my VDS1? That VDS1 would be saturation voltage. I am writing saturation voltages. So that would be VGS1 minus VT. So that would be the saturation voltage. What will be the saturation voltage for the second curve? VDS2. That would be VGS2 minus VT. And what will be the saturation voltage for the third curve? That would be VGS3 minus VT. So this particular expression is important. What is the saturation voltage? When the current saturates, but what is the value of that? That is VGS minus VT. So if your VDS value is higher than VGS minus VT, that means your current will saturate. If your VDS value is lesser than VGS minus VT, that means you are working in linear region. Are you getting this point? Here, if I write your VDS is, where should I write? Here I can write. If your VDS is higher than VGS minus VT, that means you are in saturation region. The current is saturated. And if your VDS is lower than VGS minus VT, but it should be at least greater than 0. VDS has to be greater than 0 always. Should be greater than 0. Then if VDS is less than 0, that means it is in cutoff. If VDS is less than 0, that means it is in cutoff. If VDS is less than 0, that means there will be no current. Here there will be no current. If VDS is less than 0, that means this will be cut off. So if VDS is less than 0, it will be cut off. If VDS is less than VGS minus VT, it will be in linear. And if VDS is greater than VGS minus VT, that means it will be in saturation region. Well and good. So now we will see the MOSFET current equation. Okay. So what this I have drawn, this is the channel. This is the channel. Channel I have drawn. But channel in 3D. In 3D. Till now we were watching the channel something like this. This is how we were watching the channel. But now we are seeing it in 3D. So this will be my channel. So this particular thing. So here I will not write channel. I will just show it that this is my channel. So now this particular length is known as L. This is the channel length, and this behind this one, this is known as width. So here it is difficult to show, but I will show it somehow. This is my width. In this diagram it is more clearer. Length and width. Got it? So what will be the current equation in linear region? What is the linear region? When VDS is lesser than VGS minus VT. You will remember the graph. Okay, VDS is lesser than VGS minus VT. That means that is the linear region. Now I will write the expression of current. From where the formula came, no one will ask you the derivation. So just the simple formula, that is mu n cox w by L VGS minus VT into VDS minus VDS square by 2. This formula you will have to remember, but you will use it so much of time that you will always remember it. Now what is mu n here? That is mobility of electrons. Mobility of electrons. WL you know, right? L is channel length, and W is channel width. Now what is this COX? So let's see it. At the upper side, what you are having, this is the channel. Above channel, what you are having, above channel you are having oxide layer, right? Look, this is my channel. Below it there is channel, right? Above it, what you are having, oxide. Above oxide, what you are having, metal, metal, oxide, and after that you are having your channel, or you can say semiconductor. After that you are having your semiconductor. Metal, oxide, and semiconductor. Now if you are giving some supply here, some positive supply, let's assume, so because of that there was electrons coming, so basically negative supply was coming here, right? If we are giving positive supply here, so because of that negative supply was coming, so isn't it acting like a two plate of capacitor? Isn't it acting like two plates of capacitor? Two plates of capacitor are there, and in between there is some oxide, so it will give rise to some capacitance. What is the formula of capacitance? That is epsilon by width. This width is TOX. This width of the oxide, that is TOX, and epsilon is simply permittivity. This is TOX and this is permittivity of the this is oxide layer. What is oxide layer? SiO2. We will talk about it, why oxide layer is used, what is the use of oxide layer, we will talk about it. So permittivity, this is permittivity of oxide layer, and then TOX is the length, right? And metal, oxide, semiconductor, so COX is this. So this you need to know. Okay, this is COX. So WIL we know, mu n we know, VGS we know, applied VGS, VT we know. What is VT? Threshold voltage. And instead of VT we should write VTN, threshold voltage of NMOS. So VTN, threshold voltage of NMOS, threshold voltage. Okay, one more interesting thing we will see here, that in the NMOS, what is the scene? The drain is at positive potential. The drain is at positive potential and source is at lower potential. So the drain is at higher potential and source is at lower potential. In case of NMOS, drain is positive and source is negative. Source is zero actually, because we are taking that as a reference. So drain is positive, that means drain is at higher potential. So in case of NMOS, the potential which is at higher potential, sorry, the node which is at higher potential, that is known as drain, and the node which is at lower potential, that is known as source. Now I will tell you one interesting thing. Just see the structure of a MOS. Just see this structure. Isn't it symmetrical? Isn't it symmetrical about this? Like if it is in front of you and you don't know what is source, what is drain, so how will you decide what is source and what is drain? Because it is symmetrical only, no? If someone is seeing from this side, he will say this is drain and this is source. If someone is seeing from this side, he can say this is drain, this is source, because this is symmetrical. But in case of NMOS, what did we find? If there is a substrate given to me, I will see that is P substrate. So it has to be NMOS. And in NMOS, drain is at higher potential. So I will check the potential of these two nodes. So the node which is having higher potential, I will call that as drain, and which is having lower potential, that will be my source. And gate will be surely the controlling one, it will be in between. So the confusion will be between drain and source, because the structure is symmetrical. So in case of NMOS, the node which is at higher potential, that is drain, and the node which is at lower potential, that is source. Are you getting this point? In case of NMOS, the node which is at higher potential, that is drain, and the node which is at lower potential, that is source. So we have written the current expression for linear region. We have to write the current expression for saturation region as well, that we will write. But before that, let's write a note. What is the note? In case of NMOS, higher potential node is drain and lower potential node is source. And what is the direction of current flow? The electrons were going from source to drain. That means the direction of current flow is from drain to source. And current flow is from drain to source. From drain to source. That means from higher potential node to lower potential node. Here I did not write opposite, right? ID flows from drain to source. I did not write from drain to source. Okay. So the electrons are going from source to drain. So the direction of current will be drain to source. And which was at higher potential? The drain was at higher potential. Drain was at higher potential and source was at lower potential. So if I am given a MOS, first I will identify if it is NMOS or PMOS. I identify it is NMOS. So if it is NMOS, that means the one which is at higher potential, that will be drain, the lower potential will be source. So I will also know the direction of current, that it will flow from high potential node to low potential node, from drain to source. Are you getting this point? Now I will write the current in the saturation region. So for the saturation region, tell me one thing. Whatever the current is here, the same current will be here, right? The current is constant. So what current will be there at this region? At this region. What did we say? That previously it was following the linear manner. This manner it was following. Previously it was following the linear manner. This manner it was following. Suddenly it has changed. Suddenly it is saturated. So if I put in case of VDS, if I put VGS minus VT, that will give me saturation current, because this node is VDS minus VT, right? This node is VDS minus VT. This node is VDS minus VT. So if I put VDS minus VT in that linear current expression, if in this expression, in case of VDS, if I put VGS minus VT, I will get my saturation current. Are you able to understand? Because at if I put VDS equals to VGS minus VT, I will get the current here. Now the same current is the saturation current. The same current is the saturation current. So if in the expression, in place of VDS, I am putting VGS minus VT. So if I put VGS minus VT here, what will be happening? It will be VGS minus VT square. It will be VGS minus VT square. This will be VGS minus VT square, because in place of VDS, I am putting VGS minus VT. And this will be, in place of VDS, you are putting VGS minus VT square. And by 2. So this complete expression will be made VGS minus VT whole square by 2. So what will be your formula? Mu n Cux W by 12 VGS minus VT square. The formula will become mu n Cux W by 12 VGS minus VT square. So this is also very important. In the end, I will give you a conclusion that what you all need to remember from all this lecture, from the complete lecture, what you all need to remember for analog electronics. That I will give you the conclusion in the end of this part. That means in the end of the next video, I will give you the conclusion. So for now, we are writing the important points. So what is the point? I am just putting in place of VDS, I am putting VGS minus VT. So what I will get? यार ये बार बार टेढ़ा हो जाता है यहाँ पे ये राइटिंग पैड. म्यू एन सी एक्स डब्ल्यू बाई 12 VGS minus VT, VTN we can write VTN square. That will be my current in saturation region, right, which is constant. Understood? Well and good. So is there anything do I need to write, or is that it? That's it, right? MOSFET is a symmetrical structure. So till now what we have studied the working of NMOS. So what is the working of NMOS? You have to apply some positive potential at drain and also some positive potential at gate, but that small potential is not enough. You have to apply higher than a particular potential so that the channel is framed. If the channel is framed, then positive potential at the drain will attract the electrons and the current will flow. So to frame the channel, you have to apply a positive potential at gate, and when it is framed, the current will flow. Now the current is flowing and electrons are moving from source to drain. That means the current will be from drain to source. Now which will be drain, which will be source? The one which is at higher potential, that will be drain, and one which is at lower potential, that will be source in case of NMOS. So this we saw in case of NMOS. Now we are going to analyze PMOS. PMOS means P channel enhancement type MOSFET. So this you can analyze on your own, right? You can analyze on your own. So try making the transfer characteristics, ID versus VGS curve and ID versus VDS curve by your own, and then recheck if you are making it clearly or not. So tell me, what potential you should apply here? Negative or positive? Or positive? Which potential you should apply? Negative. Why so? Because if you apply negative, then only depletion region will be found, because this will go into reverse bias when you apply negative potential. So you have to apply negative potential. And at gate, what you need to apply? Negative or positive? Or positive? You need to apply negative, because if you apply negative, what will happen? If you apply negative, then from here holes will be supplied. If holes are supplied, they will reach here, and that will frame the channel. So negative potential here and negative potential at the drain. So here the channel is framed, and now this drain will attract the holes and the current will flow. So what will be the direction of current? The direction of current will be from source to drain, because holes are moving from source to drain. If the holes are moving from source to drain, so the direction of current will be from source to drain. Now drain is at a negative potential. Drain is at negative potential and source is grounded. So which one is higher potential? Drain is negative and source is grounded. Which one is higher? Source is higher. So in case of PMOS, higher potential is source and lower potential is drain. So this is all we need to see, and we will make the transfer characteristics. Also write down the current equation, which will be same as NMOS only. So tell me, what will be the current here? Both 0, 0 current. VGS is 0, still the current will be 0, because no channel will be framed. Here what will be the current? VGS is 0, whatever you apply, the current will still be 0. Here what will be? VGS you have applied negative, but still very less. That means channel is not framed. Channel is not framed. You have to apply more negative potential. You have to apply more negative potential. You need to apply more negative potential. If you are applying more negative potential, what will happen? The channel will start framing. Channel will start framing and the current will flow. So basically, let's assume that first I am applying -1, then I have to apply -2, and let's assume if VG is -3, my current flows. So what I will write? That my VGS value should be lesser than VT for the current to flow. This is my VT, because here the current flows. This I can call VTP. So for lesser value than this, if VG is -4, if VG is -5, the current will flow. So I will write that my VGS should be lesser than VTP. At that point my current will flow, because gate potential is negative. Are you getting this point? What will be my VTP? VTP will be my -3. Now gate potential is negative, source is at grounded. This is grounded. This is also grounded. Source is at grounded and this is also grounded. Now I am applying negative potential. That means I will apply VG to be -4 or -5. So I am decreasing the potential. So if my VGS is lesser than VT, that means if my VGS is less than -3, it can be -4, it can be -5, it can be -6. So if my VGS is less than -3, that means my current can flow. Are you able to understand this point? Say yes or no. So when VGS is less than VTP, the current will flow. So like that I can make a line so that you will be able to understand it. So this I will say -1, -2, -3. You are applying VG in this direction. VG you are keep on decreasing. VG. Let's assume this is your VTP. So if my VGS is less than VTP, then my current flows. First thing is that you have to apply negative potential at gate, but also the negative potential should be so less that it should cross the VT value, and then only the current will flow. And if drain is negative, that means what is happening? It is framing the depletion region. It is framing the depletion region. That means it is giving you a high electric field that can attract the holes. I hope you are able to connect now. So when VGS is less than VTP, then your channel will be framed. This will be your channel where holes will be there. This is your channel. Now there is a chances that current can flow. So, okay, before moving on to the next condition, I will tell you one important thing, that is this, that now you have to remember two conditions. No, in case of NMOS, you will have to remember that VGS is greater than VTN. Sorry, in case of NMOS, let's move on to the next page. So in case of NMOS, you will have to remember that VGS is greater than VTN. This is in case of NMOS. Then in case of PMOS, you will have to remember that VGS is less than VTP. And this is also negative, and this potential is also negative. So it will create confusion, right? So what is the simplest way to remember that this is you are remembering? So what you will do in case of from NMOS to PMOS, if you are going, what you will do, you will just interchange gate and source. So what you will write, that your VSG should be greater than mod of VTP. I am saying that my VGS is -4, my VTP is -3, and my VGS is -4. This I am talking about PMOS. VTP is -3 and VGS is -4. That means here I am. That means my current will flow, right? Current will flow. ID will flow. If my VGS is -4, what I can write? My VSG is 4. So if my VSG is greater than mod of VTP, then my current flows. That means 4 is greater than 3. So my current will flow. What I can write, that my VGS is less than VTP. This I can write if I am not using mode. But if I am using mode, so I can write my VSG is greater than VTP. So in the examination, you are not going to think that much. What you are going to remember? You are going to remember only NMOS. You are going to remember only NMOS part. So in the NMOS part, you have remembered 3 things. What are those things? First thing is that your VGS should be greater than VT for the current to flow. Your VGS should be greater than VT for the current to flow. So for PMOS, if you need to write VTN, so for PMOS, if you are writing, what you will do, VGS would be replaced with VSG should be greater than mod of VTP. These signs will not change. Greater than, lesser than. These signs will not change. These sign will remain as it is. Mod of VTP. What is the other thing you remember? Saturation voltage. What is the saturation voltage? VD sat was that if your VDS is less than VGS minus VT, if your VDS is less than VGS minus VT, you are working in linear region, right? If your VDS is less than VGS minus VT, you are working in linear region. That is for NMOS. So what will be the case for PMOS? VDS VSD is less than VSG minus VTP. So basically, you are replacing your VGS with VSG, you are replacing your VDS with VSD, and you are replacing your VT and with mode of VTP. That's it. No sign of arrow and all these will change. Because if these keep on changing, you will be confused. So this is just my shortcut, or this is how I solve the problem, that I remember for NMOS. I just remember the graph. Okay, VDS is greater than VGS minus VT, I will be moving to saturation region. VDS is less than VGS minus VT, I am in linear region. If VGS is greater than VT, that means I have cleared the cutoff. Now my current can flow. So these things I remember. Now for writing for PMOS, I just have to interchange the source gate and source drain. So what will be my condition for PMOS? To overcome cutoff, what should be the condition? That my VSG should be greater than mod of VTP. Now for saturation, what will be the condition? That for linear region, my VDS should be less than VGS minus VT. That means my VSD should be less than VSG minus mod of VTP. And what should be the condition for saturation region? The saturation region condition would be my VSD should be greater than VSG minus mod of VTP. That's it. No sign of arrow, only one sign of arrow I am remembering, and then I keep on interchanging. Are you getting this point? So by that, we can solve the problems more quickly rather than thinking all that. So when we are doing the circuit analysis, we can't think that much, right? But if the question is on EDC, you can think that much. But if you are doing the circuit analysis, you don't need to think that much. So from going from NMOS to PMOS, VGS should be replaced with VSG, VDS should be replaced with VSD, and VTN should be replaced with VTP. So what was the cutoff region in NMOS? That was your VGS should be less than VTN. That was the region. So here it will be VSG should be less than mode of VTP. That is the cutoff. What will be the on region? That your VGS should be greater than VTN. Here what it will be? VSG should be greater than mode of VTP. Once you start solving the problems, it will be very easy for you. What was the condition for linear region? That your VDS should be less than VGS minus VTN. What will be the condition for linear region here? Your VSD should be less than VSG minus mode of VTP. What will be the condition for saturation region here? What was the condition? Your VDS should be greater than VGS minus VT. Here VSD should be greater than VSG minus VT. In case of NMOS, which was at higher potential? Drain. So here we are always writing drain first and source later on. And in case of PMOS, which is at higher potential? Drain is at negative and source is at ground. So source is at higher potential. That's why we are always writing source first. Are you getting this point? So one which is at higher potential, that we are writing initially. So these things you need to keep in mind. This is the this is all you need to keep in mind. After that, you can write down the current equation and everything. Now we are left with one condition, that is this, that my VGS is less than VT and my VDS is negative. So what will happen? I can write this, or what I can write, or what I can write, that my VSG is greater than mode of VTP. VGS is less than VTP. That means here I am applying more negative potential. That means my VSG is greater than mode of VTP. This I can write. And here I am writing that my VDS is negative. VDS is negative. That means here I am applying negative potential. If I am applying negative potential here, so what I can write? Negative here and grounded here. This is grounded. This is grounded. And at drain I am applying negative potential. So what I can write? My VSD is positive. So what will happen? ID flows. Tell me the direction of ID. What will be the direction of ID? Holes are moving from source to drain. So the ID direction will be source to drain only. Source to drain. In the direction of movement of holes, that will be the direction of ID only. So holes are moving from source to drain. So ID current will also move from source to drain. Now we will draw the transfer characteristics. So ID versus VGS we are drawing. ID versus VGS, not VSG. ID versus VGS, right? The current direction it is asking, that is from source to drain. Source to drain. ID versus VGS. VGS, that means source is grounded, VG potential. VG potential you have to apply negative. So till a particular negative voltage, you are not getting any current. Till a particular negative voltage, you are not getting any current. After this negative potential, you will get some current. Right? Now let's do the same for VSG. ID versus VSG curve. Now your source is at ground, but gate is negative. Basically, what is the condition? That your VSG should be greater than mode of VTP for the current to flow. So this is your VTP. Here you don't need to think, right? This is mode of VTP I will write. Because for PMOS threshold voltage is negative and for NMOS threshold voltage is positive. And this is how it will go, right? Condition 6, ये कौन सी condition है? अच्छा, now if we keep on increasing VDS, what will happen? Negative supply is increasing. If I am increasing negative supply, basically here I am increasing the, this was my NMOS, so here I am increasing the negative supply. What will happen? The reverse bias here will increase. So the current will increase. So if I am increasing VDS in negative direction, that means if I am increasing negative supply, what will happen? The reverse bias will increase. If the reverse bias increasing, depletion region will increase, more electric field, more current, right? But at a particular VDS value, the current will saturate. Why it will saturate? Because in that channel we are having less charge carriers now. There will be less holes. Although the electric field is very high, but still there are less holes, so the current will saturate. So just the final answer we will write. What is that? Current initially increases linearly and then saturates. So ID versus VDS you are drawing. That means the drain is at negative potential. So for negative graph you will draw. At first it is increases and then it saturates. Increases and then saturates. And ID versus VSD if you are drawing, what will be this potential? Tell me. That will be VGS minus mode of VTP. Because VGS is also negative. Source is 0, VG is negative. So negative, no, not mode of VTP. It should be mode of VTP or only VTP. बताओ भाई, mode of VTP or only VTP? VSG minus VTP. VSG is already higher. Yeah, it should be directly VTP, not mode of VTP. VSG minus VTP. But now we are writing VSD. So here you don't need to think. What you know? What will be my VSD set? VSD set. That will be VSG minus mode of VTP. That's it. Look, you have to think something like if I keep on telling, you will not be able to understand everything. I have given the enough concept. I have given you enough tricks to remember the things. Now it's up to you how much can you think. I told you one simple thing that you remember for NMOS. If you are writing for PMOS, just interchange VDS with VSD, VGS with VSG. The arrow sign will remain the same. Look, the graph is also same. This graph is also same now. There is no change in the graph. That's why people call EDC complex, but these things are necessary for understanding MOSFET circuits. And also for interview, it is very, very important. So this is VSG minus mode of VTP. And this current is ID set, we already know. So this much of region is linear and this is saturation. Now you are able to connect the dot. So now we will see the final characteristics that I have drawn. I need the relation between VSD1, VSD2, VSD3. So these curves we will remember. We will remember by this, not these curves. These curves we draw now. These one we are not going to remember. These curves we are not going to remember. We are going to remember in the positive direction only. So here VSG is there, here VSD is there. So tell me which one is higher? VSD1 is higher, VSD2 is higher, or VSD3 is higher? VSD1 is higher than VSD2 is higher than VSD3. If I am saying VSD is higher, VSD is higher, VSD is higher, that means drain is more negative. If drain is more negative, that means more reverse bias, more depletion region, more current. So VSD is higher, that means drain is more negative, and if I am applying more negative, that means more current will be there. So VSD is higher. Here tell me what is higher? VSG1 is higher than VSG2 is higher than VSG3. If I am saying VSG is higher, that means this gate is more negative. This gate is more negative. If I am saying VSG is higher, that means gate is more negative. If gate is more negative, that means more holes will be supplied. If more holes are supplied, that means in the channel we will have more holes. And if more holes are there, more current will be there. So here we are having more current. So VSG1 is higher than VSG2 is higher than VSG3. Well and good. Let's write down the current equations. So while writing the current equation, what you will do? Same, VGS should be greater than VSG, VDS should be greater than VSD, and VTN should be, sorry, VGS will be replaced with VSG, VDS will be replaced with VSD, and VTN will be replaced with VT. So linear region, what is the condition? Without turning on the pages, you have to write the condition. What is the condition for linear region? That your VSD should be greater than VSG minus mode of VTP. By remembering the which condition? By remembering the condition of NMOS, I can directly write the PMOS condition. So what will be my ID? My ID will be mu n COX W by L VSG minus VT into VSD minus VSD square by 2. Very easily, wait. VSG minus mode of VT I will write here. VSG minus mode of VTP into VSD minus VSD square by 2. What will be my saturation region? That will be VSD is, oh sorry. This should be lesser. Sorry for that. Big error from my side. People would have got confused and wasted their time there. VSD is lesser than VSG minus VTP. Here VSD is greater than VSG minus VTP. So what will be my current? Here one more error is there. I am really sorry. It should be mu P COX W by 2L VSG minus VT, VSG minus mode of VTP whole square. Are you able to do it? Okay, we will take up an example so that you don't get confused. We can take up an example to find the current. Okay, to find the current and all. Yeah, one note I will write. What is that note? In PMOS, higher potential is, what is higher potential? Source, because drain is negative. In case of PMOS, higher potential is source and lower potential is drain. And what was the direction of current? Source to drain. We can write the same thing for NMOS as well, although we have already written, but still for comparison we are writing. In NMOS, what was the higher potential? Higher potential was drain. Drain was positive there. Higher potential was drain. If you have remember the pictures in your mind, it will be very easy. What will be lower potential? Lower potential was source. And what is the direction of current? Direction of current will be drain to source. These things you need to know, direction of current and all those, because electrons are moving from source to drain, so direction of current was drain to source. These things you need to know. You need to know these equations, you need to know these conditions. Okay, so this note is very important. These two equations are very important. These two curves are very important. And then these conditions are very important. Cutoff on linear saturation. These conditions are very important. Then coming to this equation, very important. The equation, and for this curve are very important. So in these 2 hours, whatever we have studied, 2.5 hours, whatever it takes. So these things are important in that. That will be used for circuit analysis, but you should be conceptually sound that how current is coming, what is the region of current coming, which potential I should apply. In case of PMOS, drain and source should be positive. Okay, so these things you should know. Okay, and one more thing is left that I did not write. Why we use enhancement type of MOSFET for amplification? So in enhancement type of MOSFET, what is happening? For zero potential, there is no current. So your current is depending on the controlling voltage. If there is no controlling voltage, there is no current and no output. Now, if I am increasing my controlling voltage, so after a certain controlling voltage, I can get some output. So enhancement type of MOSFETs are used for amplification. So that I can write in next lecture. In next lecture, we will write the enhancement type MOSFET are used for amplification. The reason we will write. Then we will see equation. One numerical we will see, finding drain current. We can see that. Very simple numerical we will see. And then we will see some important definition that why oxide is used. These kind of question we will see. Then we will see two important concepts, that is known as short channel effect. So that is channel length modulation and body effect. These two things we will see, channel length modulation and body effect. So that will conclude our MOS physics. So that is the part which is important for MOS physics. Well and good. I hope you are enjoying the lectures. So okay, let's meet in the next lecture. Thank you. Hi everyone. So let's see the MOSFET circuit symbol now. So what do you mean by circuit symbol? Like we have studied diode. So diode was, in physics we studied like this. This was our diode. But in the circuit analysis we were using it like this. Similarly, we have studied MOSFET like this. This is our MOSFET, but in the circuit analysis we will use it differently. So how we will use it? Like this. So first let's see about depletion type of MOSFET. So this is our depletion type of MOSFET. So these are for NMOS. These all are for NMOS. Depletion, enhancement and common for both, like for depletion as well and for enhancement as well. And these are for PMOS, P channel. These are for P channel. These are for PMOS. So how do you denote it for depletion type? There are two solid lines. These are the solid lines. This is the solid line, and then this kind of structure. Now this potential will be drain, this potential will be source, and this potential will be body. Now there will be a sign of arrow. So how that arrow will look like? So when we study N channel, this is the P substrate and then there is N plus, right? This is our N channel MOSFET, right? P substrate and N plus. So how does the diode look like? Diode looks like this. So the arrow of diode is from, this is our body and this is our other terminal, you can say source or anything. So from body to, this is the arrow, no? Diode, arrow of diode, it is getting outward from body. So this will be the direction. And in case of PMOS, this will be the direction. This will be body, this will be source, and this will be drain. Drain. Here it is shown that source and body are shorted. Here it is shown that source and body are shorted. Because in both PMOS and NMOS, we are keeping source and body shorted. So here it is shown source and body are shorted. You can actually make it like this as well. Like it is not shorted. In that manner also you can make, but generally we make source and body are shorted. So generally you will find it like that. So drain, source, gate, body, like that. What will be the arrow direction? How do we define the arrow? The arrow is, you will, in the mind you will think, okay, my body is, my substrate is, this is my body, my substrate was P type, substrate was P type and channel was N type, channel was N type. So from P to N, this will be the diode. So arrow will be from body to inside, getting out of body. So that will be the direction of arrow. So this is how you make the arrow. And in case of PMOS, it will be opposite, because here the substrate was N. If the substrate was N, this would be the direction of arrow. So the arrow is getting into the body, the arrow is getting into the body. Well and good. Again, here similar structure is there. This will be drain, this will be source, this will be body. What will be the arrow? Same direction, inside, here outside. This will be source, this will be drain, and this will be body. But the lines are dashed. Here dashed line is used, this is dashed, and here solid line is used. What is the reason? Solid line shows that the channel is already present, and dashed line shows that the channel is not there, you have to make the channel. Solid line shows that the channel is already present. So in depletion type of MOSFET, channel was already present. In enhancement type, we made the channel by applying gate potential. So that's why dashed line is used in enhancement type and solid line is used in depletion type. Got the point? Now, by this arrow, you will recognize whether it is NMOS or PMOS. If arrow is inward, that means it is NMOS. But arrow from body terminal, here the arrow will change. That we will talk about. So arrow from body terminal, if the arrow from body terminal is inward, that means it is what? NMOS. If the arrow is outward, it is PMOS. Now, how will you define the source and drain? It's not that the upper one will be source and lower one will be drain, and here upper one will be drain, lower one will be source. Now, generally it is shown like this. But this is not the case always. So the one which is at higher potential will be drain and one which is at lower potential will be source in case of NMOS. I told you, remember the last lecture. In NMOS, which one is at higher potential? In NMOS, you apply positive bias at drain. So in NMOS, which one is at higher potential? Drain is at higher potential. So one which is at higher potential, in case of NMOS, that will be drain and lower potential will be source. So if any particular circuitry is given, any particular MOS is given, they haven't shown drain and source, you don't know that. But you know the absolute potential of two nodes. You know the potential of this node is 6 volt. You know the potential of this node is 4 volt. So first you will see the arrow. Arrow is inward. From body, arrow is inward. That means it is NMOS. And if it is NMOS, that means higher potential will be drain and lower potential will be source. So wherever you see high potential, that will be drain, and wherever you see lower potential, that will be source. Well and good. And in case of PMOS, what will happen? The source is at higher potential, because in case of PMOS, what do? We apply negative potential at drain. Negative potential at gate. So source is at higher potential. So here I will write higher potential. I will just write HP, higher potential. And here I am writing lower potential. This is higher potential and this is lower potential. So I am also writing the shortcut. Higher potential. And what do you mean by LP? Lower potential. And generally it is shown like in case of NMOS, we show drain upward and source downward. Why drain upward? Because drain is at higher potential. Always higher potential is shown upward and lower potential is shown downward. Like let's assume you make this kind of structure, no? Sometimes this is ground, this is resistance R, this is 5 volt battery. So higher potential is always upward, lower potential is always downward. You won't see circuits like this. Like you can make it like this, but generally it is shown like this: 5 volt resistance and then ground. So 5 volt device and ground. So higher potential is upward, lower potential is downward. Here what is higher potential? Higher potential is source and lower potential is drain. So higher potential upward. So generally it is shown like this, but by the direction of arrow you will get to know. If from the body arrow is outward, that means that is NMOS. If the from body the arrow is inward in the body, that means that will be PMOS. Now here, if the arrow is outward, that will be what? NMOS. And if the arrow is inward, that will be PMOS. And the one which is at higher potential, that will be drain, and one which is at lower potential, that will be source. Yeah, this will be source, this will be drain. Although this shows the direction of arrow, although this shows the direction of current, this arrow shows the direction of current. In case of NMOS, what is the direction of current? Remember it. In case of NMOS, what is the direction of current? Electrons travel from source to drain. That means direction of current is from drain to source. So this is the direction of current in case of NMOS. So this is the most general circuit. In 99.95% cases, this will be used. You will see this kind of circuit in 99.95% cases. And here, this is the higher potential. This will be the lower potential. If you know the absolute potential of drain and source, then you can make drain and source by your own. If you don't know the absolute potential, let's assume there is some circuitry given like this. And some resistance R is there, some 5 volt is there. This is some resistance R, this is some V. Do you know the potential of drain here? No. Do you know the potential of this node? I'm not saying this is drain. Do you know the potential of this node here? No, you don't know. And this node is grounded. Let's assume this is also resistance R. Do you know the potential of this node? No. So by default, you will consider this as drain and this as source. And you will consider the direction of current like this, from drain to source. But if you know the absolute potential, like let's assume this structure is given, whatever it is, it can be anything. Let's assume this is 6 volt and this is 4 volt. So you know the absolute potential now, that this is 6 volt. That means first what you will see the arrow is outward. That means it is certainly NMOS. It is NMOS. So it is NMOS. Now the one which is at higher potential, that will be drain, and this will be source. Well and good. And here the one which is at higher potential, that will be source, and one which is at lower potential, that will be drain. And what is the direction of current in case of PMOS? Holes travel from source to drain. So the direction of current will also be from source to drain. So this is the direction of current. And this is higher potential. This is lower potential. Actually, most of the time when we study, people say that, okay, this is NMOS, just remember it. And this is PMOS, just remember it. But this is not the case. This is NMOS, this is PMOS, that's for sure. But you can't say that always this will be drain and always this will be source. No. The structure of MOS is symmetrical. Drain and source can be interchanged based on their potentials. Understood this point? Based on their potential, the source and drain can be interchanged. And this is general kind of structure. This will be based on, let's assume this is higher potential and this is lower potential. This is how I am making. So this is our NMOS. Here there is no arrow, nothing. Just the difference is there is this bubble there. This bubble is there. This small bubble is there. In case of PMOS, this small bubble is there. So this will be source, this will be drain. This is at higher potential, this is at lower potential. Well and good. Understood this concept? So these are the symbols. These are the most important one. These are used in digital circuitry. In analog, this symbol will be used. Somewhere you can see this symbol as well, but most generally this symbol will be used. So like that, arrow is outward, that means that is NMOS. Arrow is inward, that means that is PMOS. But also the higher potential will be source and lower potential will be drain in case of PMOS, and higher potential will be drain and lower potential will be source in case of NMOS. Let's see a question and that will clear your concept now. You have to mark source, drain and the current direction. This is what you need to mark. Which one is source, which one is drain, and what will be the direction of current. So what you will do, this particular structure is given. You see this is the arrow. That means this is NMOS. First thing I got to know is that this is NMOS. Now I know one thing. What is that? That in case of NMOS, the one which is at higher potential, that is drain. So this will be drain and this will be source. And what will be the direction in case of NMOS? What is the direction of current in case of NMOS? The direction of current in case of NMOS is drain to source. So this will be the direction of current. That is ID. If you see this structure, you will see that arrow is inward. That means this is PMOS. This is PMOS. Now in PMOS, I know one thing. What is that? The one which is at higher potential, that is source. The one which is at higher potential, that is source. That means this will be source and this will be drain. What is the other thing do I know? The other thing I know is that in case of PMOS, the current always flows from source to drain. Current always flows from source to drain. So this will be the direction of ID. Let's see this. I see this structure. What do I get to know? That this is an NMOS. Just as I see this structure, I get to know that this is an NMOS because the arrow is outward. One thing I know that in case of NMOS, the one which is at higher potential, that will be drain. So now this will be the drain. And this will be source. And what is the direction of current from drain to source? So this will be the direction of current. Now a lot of people will say, like I'm saying 99% of GATE aspirants who haven't studied analog electronics deeply, if this question is given in front of them and I say that my gate potential is 5 volt And if I ask them what is the operating condition of a MOSFET, whether it is on or off, so what they will say? They will say that, sir, 5 minus 6, your VGS is minus 1 volt. That means VGS is less than 0, so diode is off. This is what they will say. But this is not VGS, this is drain. Because mostly what is taught is that wherever you see this arrow, that means this is source. This is wrong. Arrow doesn't mean this is source. If the arrow is outward, that means this is NMOS. That's it. Nothing else. If arrow is outward, that means it is NMOS, nothing else. Understood the point? But when you study amplifiers, you just get habitual that this will be source only, this will be drain only, because amplifier are biased in a way that always higher potential will be upward only and lower potential will be downward only. They are biased in that way. Like with the supply, we make sure that the upper potential is drain and lower potential is source by the supply only. So in case of amplifier, you can say that, okay, sir, this will be drain, this will be source. But here I am talking about DC biasing. DC biasing. I have fixed my potential. The upper one is 4 volt, the lower one is 6 volt. That means the one which is having higher potential. Now the arrow doesn't define the direction of current. What arrow is saying? Arrow is saying that direction should be like this. This is what arrow is saying. But actually the direction is from drain to source, from down to up. Are you getting this point? And 6 volt, one which is higher potential, that is drain, and one which is lower potential, that is source. Now I see this arrow, the arrow is inward. So first thing that I got to know is that this is PMOS. This is the first thing I got to know. This is PMOS. Now if this is PMOS, what do I know? That one which is at higher potential, that is source. In case of PMOS, one which is at higher potential, that is source. So which one is higher potential? This is the higher potential. So that is source. And one which is at lower potential, that will be drain. So this will be drain. What will be the direction of current? This will be the direction of current from source to drain. Are you understanding this point? So this was a very important concept which usually aspirants ignore, but now you understood it. Okay. But in case of amplifier, you will not have to think that much that, okay, sir, which will be drain, which will be source, because they will be biased in a way that this will be drain only, this will be source only. And in case of PMOS, this will be source only and this will be drain only in the amplifiers. But here I am talking about DC biasing. In DC biasing, I can interchange anytime. Let's move on to the next concept. Before moving on to the next concept, we will solve a simple problem. So it is given that mu p, that means mobility of holes, is 0.4 times of mobility of electrons. I don't need to write it in statement, right? You will understand. The mobility of holes is 0.4 times of mobility of electrons. What must be relative width of n channel and p channel devices of relative width of n channel and p channel devices, that means NMOS and PMOS, if they are to have, that means if they are having equal drain currents when operated in saturation mode with on drive voltage of the same magnitude. What is on drive voltage? Overdrive voltage, sorry, not on drive, sorry, overdrive. What is overdrive voltage? Overdrive voltage. Overdrive voltage means VOV, we should show it, and that is VGS minus VT only. Basically, I told no that VGS is greater than VGS minus VT. If VDS is greater than VGS minus VT, it will be in saturation region. So this potential is known as V overdrive. V overdrive is VGS minus VT only. Okay. So this term I forgot to introduce you. So V overdrive is VGS minus VT. Always remember it. Arey wah. V overdrive is VGS minus VT. This is V overdrive. Both are operating in saturation mode. Both are operating in saturation mode. And they are having equal drain currents. The current is equal. So the current of PMOS is equals to current of NMOS. So what is the formula? For PMOS it will be mu P COX W by 2L. Both are in saturation mode. So that's why I am applying P by 2L. Yeah, this V overdrive is VGS minus VT. Also it can be. This is for NMOS. And what it will be for PMOS? For PMOS, if we know one thing, for NMOS, if we know one thing, what we can do? We just need to interchange. VGS will be interchanged by VSG. And VT will be replaced by mode of VTP. So this is for PMOS. Here I can write VTN. This is for PMOS. Now mu n cu x w by 2L VGS minus VT, okay, sorry, this is we are writing for PMOS. So we will write VSG minus VTP whole square. And what we will write for NMOS? Mu n COX W by L relative widths if they are having equal drain current when operated in such a manner with the same magnitude of this, and even this COX is equal. This is what should be written, that this oxide capacitance is also equal. Oxide capacitance you will consider equal because there is no information given about it, so we are considering it equal only. So here what will be the relation? Mu n COX W by 2L VGS minus VTN square. Now what is this? VOV. And what is this? VOV only. Both are equal. But here W by L is not equal. Because they are asking, what they are asking? The relation between the width of N channel and P channel. So this W by L is not equal. So I should write W by L for PMOS. So mu n COX W by L for PMOS divided by 2. This will be the formula. Mu n COX W by L by 2 VSG minus VTB whole square. And here what will be the formula? Here the formula will be mu n COX W by L N by 2. Right? This COX and COX can be cancelled. This 2 and 2 can be cancelled. And overdrive voltage are same with overdrive voltage of same magnitude. That means this complete term is same. So what you are left with? You are left with mu P W by L P is equals to mu N W by L N. So we have to find that mu P is equals to 0.4 mu N. Mu P is equals to 0.4 mu N. Right? 0.4 mu N. So basically this mu N and mu N will get cancelled. So this I can replace with 0.4. What did I do? In case of mu P, I put 0.4 mu N. So mu N to mu N got cancelled and only 0.4 is left here. So what will be the relation between W by L of P should be 10 by 1 by 0.4. 1 by 0.4 is 2.5. Should be 2.5 of W by L of N. So if the mobility of holes are 0.4 times of mobility of electrons, then to have the same current, the width of PMOS should be 2.5 times of width of NMOS. Did you understand this point? Mobility is lower. For PMOS, mobility is lower. So to have the same current, you have to increase the width. Understood? Mobility is lower. So to have the same current, width should be increased. Right? So width should be 2.5 times of N. Very easy question. Let's move on to the next one. For a N channel MOSFET, if the conduction parameter, look, this Kn is written there. Now, what is Kn, this conduction parameter? So sometimes Kn can be mu n COX W by L, and sometimes this Kn can be mu n COX W by 2L. In the examination, certainly it will be written in bracket it will be written that Kn is mu n COX W by L or 2L, whatever they mean. If they mean W by L, they will write it. If they mean W by 2L, they will also write it. Okay. So in the examination, it will be written. So here also it is written. This is given. This is given. Given in the question. It will be given in the question that Kn means mu n COX W by L or mu n COX W by 2L. तो कौन सा भी हो सकता है, वो डिपेंड करेगा एग्जामिनेशन में, एग्जामिनर क्या चाहता है. So it would be given. Sometimes they take mu n COX W by 2L. Sometimes they take mu n COX W by L. So it will be given for this question. Kn is mu n COX W by 2L. Right? Now what is given? So value of mu n COX W by 2L is given. That is 0.249 milliampere volt square. The value of VGS is given, that is 2 VT. The value of VT is given as 0.75 volt. So basically this will be 1.5 volt. The value of VDS is given as 0.4 volt. You have to find the drain current. So what will be your first step? You have to find the drain current. What will be the first step? The first step will be to determine the region of operation, whether it is in saturation or it is in linear. So how will you determine it? Whether it is in saturation or linear? You will determine with the value of VDS, VGS and VT. So what is V overdrive? V overdrive is VGS minus VT, and that is equals to 0.75 volt here. What is the value of VDS? VDS is 0.4 volt, right? VDS is 0.4 volt. So here what do you see? That your VDS is lesser than V overdrive, or you can say your VDS is lesser than VGS minus VT. That means it is in linear region. So your MOS is working in linear region. Did you understand this? What did you do? We have VGS value, VT value and VDS value. So we determined the V overdrive voltage. V overdrive voltage was VGS minus VT, that is 0.75. Then we saw VDS value. VDS value is 0.4 only. If VDS is 0.4, so it shows that VDS is lesser than VGS minus VT. So VDS is lesser than VGS minus VT. VDS is lesser than VGS minus VT. That means it is working in what? It is working in linear region. MOS is working in linear region. What is the current in linear region? The current in linear region would be mu n COX W by L VGS minus VT into VDS minus VDS square by 2. So what is the value of mu n COX W by L? Value of mu n COX W by L will be 2 times of 0.249. 2 into 0.249. What is the value of VGS minus VT? VGS minus VT is 0.75. What is the value of VDS? That is 0.4, right? It is 0.4 minus 0.4 square by 2. You just need to solve it and you will get the value of IT. Okay, let me solve it and I will write down the final answer. Yeah, so you are getting 0.109. So tell me, it will be ampere or milliampere? Milliampere. Why so? Because this is milliampere by volt square and this complete unit is volt square only. This complete unit will be volt square only because this is voltage square, this is also voltage square. So this complete unit will be volt square. So volt square to volt square got cancelled, milliampere is left. The current will be milliampere. ID is 0.109 milliampere. Well and good. Okay. Let's move on to the next concept. It's not concept, there will be a small questions. Then there will be two concepts, channel length modulation and body effect, that we will see. So first question is, how many charge carriers are there in a MOS? What is the answer? How many charge carriers are there? Only one. Only one. What is that? In case of PMOS, what is the charge carrier? Holes. And in case of NMOS, what is the charge carrier? Electrons. When we studied PN junction, how many charge carriers were there? Two. Because of holes as well, the current was generated. Because of electrons as well, the current was generated. Because of both. But here, in case of NMOS, the current is generated because of electrons only. There is no role of holes in the generation of current in case of NMOS. The current is generated because of electrons only, because N plus and N channel. So because of electrons only. So the current is generated because of electrons only. And in case of PMOS, current is generated because of holes only. But when we studied PN junction diode, the current was generated because of both. Holes were going here and these were going here. So the current was generated because of both. But here the current is generated because of electrons and holes only. So here there is only one charge carrier. And in case of PN junction diode, there are two charge carriers, both electrons and holes. What is the need of oxide layer in MOS? So when we studied MOSFET circuit, what did we study? Metal, oxide, semiconductor. So this was our MOS, metal, then oxide, and then there was this semiconductor or channel, you can say. Here we will be framing the channel. So why there is this oxide layer? What is the use of that? Okay, here there was gate potential, right? Let's assume this I am talking about NMOS. Let's assume I am talking about NMOS. Let's assume I am giving positive potential here. If I give positive potential here, what happens? Here negative potential is induced. First negative is induced, then inversion layer is formed. Why negative is induced? Because here there is positive potential, so electrons will be coming inside. And there are this negative charge and a hole. So this will recombine with the hole. So only negative charge will be left. So this negative charge will be there. So when we apply a small positive potential, what happens? A small negative potential are there across the semiconductor. Now what if this oxide layer was not there? If this oxide layer was not there, what would have happened? These negative charge would have reached to this plate, this metal plate, and would have neutralized it. If the negative charge were reaching this metal plate, then there is no chance that there will be a inversion layer here. Because what would have happened? That battery is supplying electrons, and then all the electrons would have reached to this metal plate. They wouldn't accumulate near the semiconductor. They wouldn't accumulate in the channel. They would have reached to metal. Are you understanding this point? But since there is oxide layer, there will be no electron that will be reaching the metal. So there will be no current. So this gate current will be 0. And since there will be no current, that means in the vertical direction there will be no current. In this direction there is current. Because of this positive supply here, in this direction there is current, but in the vertical direction there will be no current. So because of this oxide layer, these negative potential or electron are not reaching the metal plate. And if they are not reaching the metal plate, we can make the inversion layer. And if the inversion layer is framed, then we can have the current in the NMOS. The drain current would be there. If this oxide layer was not there, then these electrons would have reached to the metal plate, and then gate current only would have been there. There would be no drain current. But we want the drain current. We want the output current. It's not that I am applying a battery and from there I am getting a current. No. So in case of NMOS and in case of PMOS as well, the gate current is always 0. Why so? Because of this oxide layer. If this oxide layer is there, that is preventing these electrons and the negative charge to reach to the metal plate. And that will frame our inversion layer and we get the drain current. So that's why oxide layer is important. So this I will write in the theory. So I will pause the video and write it down because it will just waste your time. Yeah, so this is what I wrote. Because of this oxide layer only, the electron and the negative charge near the semiconductor is not reaching the metal plate and we are able to frame the channel. And this channel helps in generating the drain current. Understood? Now the third question, why do we use MOSFET in enhancement mode of operation for amplification? That I have already explained you. Because what did we need as an amplifier? That I apply a certain input voltage and then I get a output that is depending on the input voltage. So in depletion type of MOSFET, the channel was already present. Even if you don't apply any input, you get some output, you get some drain current, and that is not desirable. Like even if I am not applying any input, still I am getting some output, that is not desirable. So here in enhancement type of MOSFET, the MOSFET doesn't conduct for 0 input voltage. For conduction, your VGS should be greater than VT, and the drain current depends on the applied input voltage only. So applied on VGS voltage only, my drain current depends. here I will apply some VGS voltage. Let's assume this is VG, this is VS, or I should write this is gate potential and this is drain potential. This is gate potential, this is source potential, then this is drain potential and this is source potential. So from drain to source there is a current, and if I am applying some VGS voltage here, from drain to source I will get some current and that will go to my output. Well and good. There will be a R node resistance as well, which I haven't shown. From where this R node resistance will come, that we will check. I am saying that there will be one R node resistance as well. And from where that will come, let's check that. So now our next concept will be channel length modulation. So ideally what we have studied? We have studied this graph of, okay, I will not show this. So ideally we have studied this, that for increasing VDS, the current will increase linearly and then it saturates. This is what we have studied. So what we have studied, for VDS greater than VD sat, the current saturates. Current saturates. But practically what happens, when you increase VDS, it increases linearly, then it nearly saturates. That means it will rise a bit. It is not saturated. Saturated would have been like this, but it will rise slightly. So even after the saturation voltage, the current doesn't saturate. It rises slightly, very low. So this I will write. Practically, for VDS greater than VD sat, current rises slightly. So this was our channel. So initially, when you, what should I color? Yeah. So initially, let's assume this is our channel. This is our channel. When you keep increasing VDS voltage, what happens? The channel start getting trapezoidal like this, and at one point the channel becomes something like this. So the time when the channel becomes something like this is our saturation voltage only. This is our VD set. So the drain to source potential or the drain potential, when the channel is depleted of charge carriers from drain side. The VDS potential, when the channel is depleted of charge carriers from drain side. From drain side, it is completely depleted. So that potential only is known as VD set. And then what did we say? That I further increase VDS. If I further increase VDS, what will happen? My channel will be something like this. So now my reverse bias is getting increased, but the number of charge carriers are getting less. The number of charge carriers are getting less, but my reverse bias is getting increased. So reverse bias is strong, but charge carriers are less. So eventually I will have a saturated current. So there is one phenomena. One phenomena is saying that the electric field is strong, so the current should increase. But the other phenomena is saying that there are less charge carriers, so the current should decrease. One is saying more electric field, current should increase. One is saying there are less charge carriers, the current should decrease. So what happens? The current saturates. But in practical sense, what happens? The electric field is more dominating. In practical sense, the electric field is more dominating. They are saying that the electric field is strong, so it will increase the current, but very slightly, not linearly, very slightly. Like if this was the linear waveform increasing, and if this was the linear waveform, then this would be the practical waveform. If this was, sorry, this was the ideal waveform, then this would be the practical waveform. So what is the reason? The reason is the same. Why it is happening? The reason is the same, that when you keep on increasing VDS, what happens is that the electric field is very strong. So because of that very strong electric field, the current slightly increases. Previously I was saying that the electric field is strong, but the number of charge carriers are less, so the current saturates. But when I see the practical scenario, I observe that even if after the saturation voltage, even if I am increasing the VDS, still my current is increasing, but very slowly. This is what I observe when I do the practical things. So this I can write, and this here I will show as well, that this depletion width is getting increased. When VDS is greater than VD sat, the depletion width is getting increased. If it is getting increased, then there will be strong electric field, and this strong electric field will increase the current slightly, increases the current slightly. Okay, so this was the practical scene, and this was the ideal, this is the practical. Actually, I have shown this slope to be high. This slope is high. This is just to show you, but in actual the slope will be very, very low. It will be like this only. But this is just to show you the difference between ideal and practical graph. I am showing the slope to be very high, but actually it will be very low. And if you increase the graph, if you increase this graph in negative direction, what will happen at some potential? If you increase the graph like this, at some potential, the current will be 0. This potential is known as early voltage. We will derive the formula. We will see what do I mean by early voltage. But before that, let's write down the condition for ideal case. What is the current for ideal case in saturation mode? Linear mode we are not talking about. Now we are talking about only saturation mode. So what is the current in saturation mode for ideal case? The current is mu n cox w by 2l VGS minus VT square. That is a constant for fixed VGS. Constant for fixed VGS. Here also VGS are fixed for both of the cases. For both the cases, VGS is fixed. Constant for fixed VGS, independent of VDS. Independent of VDS. That means even if you increase VDS, my current will be constant. This is the ideal case. This is the ideal case. Now there is a term called drain source on resistance. Drain source on resistance. There is a term called drain source on resistance. So from here you are applying VDS voltage, and here you are, let's assume this is a black box. This is a black box. So you have two nodes. At this port you can apply VGS, at this port you can have VDS, and from the VDS you can have your output current ID. If you are not able to understand, this is my MOS, right? MOS is there in a black box. It is kept closed in a black box. This is my gate. This will be my source, right? This will be my source only. This will be my drain, and this will be my also my source. Gate source, drain source. This is my black box, right? VGS, VDS, and there is this black box. So if I apply VDS, I will get some current IDS, ID. This is what I am talking about in saturation region. So I keep the value of VGS and VDS and VT such that my MOSFET is working in saturation region. Now I am taking the ideal case. In ideal case, what do I observe? If I keep on increasing VDS value, there is no change in ID. What is the formula of resistance? R ohm that I am talking about. I shouldn't write R ohm, it should be RDS only. Drain to source ohm resistance in saturation. In saturation. So what will be that RDS value? That RDS value will be del VDS. Okay, this is written wrong actually. Del ID upon del VDS. No. This will be 1 upon RDS. 1 upon RDS. So what will be my RDS? The change in VDS voltage and the change in ID voltage. Even if I change it, even if I change this, the current is constant. The current is constant. So del ID is 0. Whatever the change I make in del VDS, let's assume I make the change in del VDS, that is X. But the change in current ID is 0. That means the resistance would be infinity. Are you getting this point? So in case of saturation region, the drain to source own resistance, or you can say output resistance. You can say output resistance. So in case of saturation region, for ideal case, output resistance is infinity. So del ID by del VDS is 0, or you can say that here the slope is 0. That means del ID by del VDS will be 0. The slope is 0. That shows that the resistance is infinity. But that is the case when there is no channel length modulation. That means when the case is ideal, for ideal case. But let's check for practical case. So practically what is happening? So this was our source, and then this is our channel. This is happening at VDS equals to VD set. Now if you further increase VDS, what happens? Your effective channel is getting reduced. Initially the channel length was L. You can say that in my complete channel there are some charge carriers. Now your effective channel is reduced. Here I showed you. Your effective channel will keep on reducing. So now your effective channel is reduced. Let's assume it is reduced by delta L. Your effective channel is reduced by delta L. Right? Now what will be your current equation? The current equation will be mu n Cox W by 2L. But instead of L, I will write L minus delta L. Why will I write L minus delta L? Because your effective length is reduced. That's why I will write L minus delta L. And then the same VGS minus VT whole square. So I will write down this equation again here because we are doing the derivation. So what is the current? That is mu n Cox W by 2. The length is reduced, L minus delta L, and VGS minus VT square, that is same. If I keep this L out, what will happen? Mu n Cox W by 2L 1 minus delta L by L into VGS minus VT whole square. Mu n Cox W by 2L VGS minus VT whole square. What do I do with this? 1 minus delta L by L. I can write it like this: 1 minus delta L by L inverse power. Are you agreeing with this point? 1 minus delta L by L inverse power. Well and good. I can write it in this manner. Now what is this? This is ID sat in ideal case. Mu n Cox W by 2L VGS minus VT whole square. So this is ID sat in ideal case. ID sat ideal. Now look, this channel length is reduced, but this delta L is very less. I am saying that the channel length is reduced, but delta is not that much large. This delta is very less. So this complete portion will also be very less. So one approximation, you know, that 1 minus x to the power minus 1 can be approximated to 1 plus x, right? If x is very low, it can be approximated to 1 plus x. So similarly you can do, that is delta L by L. So this is, I am getting ID set when there is channel length modulation. Why it is called channel length modulation? Because here the channel length is getting changed. That is channel length modulation. Now there is one thing. This delta L by L is proportional to VDS. Are you agreeing with this point? As much more positive voltage you apply, if you increase VDS, what will happen? Your channel will be more depleted. If you increase VDS, your channel will be more depleted. Your delta L will increase. If you increase VDS, your channel will be more depleted. That means your delta L will increase. So delta L by L is proportional to VDS. If you remove the proportionality constant, you get delta L by L is equals to lambda VDS. Delta L by L is equals to lambda VDS. This is equation 1. This is equation 2. So here delta L by L you can put here. I am adding a page. So what will be your ID set when there is channel length modulation? That will be equals to ID set for ideal case ID set for ideal case and 1 plus delta L by L will be replaced with lambda VDS. Lambda VDS. This will be the formula. So ideal current only, but here it is linearly depending on VDS. 1 plus lambda VDS. What is lambda? Lambda is known as process technology parameter. Lambda is some process technology parameter. Technology parameter. What will be the unit of lambda? What is the unit of 1? Unitless. So if this is unitless, something in addition will also be unitless. So this also has to be unitless. So what should be the unit of lambda? Voltage inverse. Because voltage inverse into voltage, that will make it unitless. So lambda should be voltage inverse. So unit of lambda is voltage inverse. So this is what this is what you understand, that this is the expression. So this is only you need to remember. Even if you don't remember the derivation, it is fine. But derivation is very simple. Effective length is reduced, so L you can take outside, then 1 plus delta L is there. Delta L by L is proportional to lambda VDS. So 1 plus lambda VDS you can simply put. Lambda is the process technology parameter. Understood? Now there is a term called, okay, we will go to early voltage later on, but first let's check this drain to source on resistance for saturation region. Drain to source on resistance for saturation region. One more condition is there, channel length modulation is present. Now the channel length modulation is present. What is the formula of RDS? RDS is 1 by del ID upon del VDS, right? Or you can write del VDS upon del ID, or I can write 1 by del ID upon del VDS. You have to differentiate it with respect to VDS. What do you get? You have to differentiate it with respect to VDS. What you will get? This is a constant quantity. So that will come as it is, ID set ideal. If you differentiate this, what you will get? 1 is constant, it will be 0. 0 plus lambda is constant, it will come outside. VDS, differentiation of VDS with respect to VDS, 1. So here you will get 1. So if you del ID upon del VDS is lambda ID set. So what you will get? 1 upon lambda ID set here. Simple differentiation is there. ID set will come outside, and differentiation of VDS with respect to ID. Sorry, del ID upon del VDS. Differentiation of ID with respect to VDS will give you lambda here. That will be 1 upon lambda ID set. This is for ideal case. So if they are asking you RDS value, if they are asking you the output resistance in saturation region, if they are asking you the output resistance of MOS, what you will do? 1 upon lambda IDS. That's it. And if lambda is 0, that means no channel length modulation. Lambda 0 shows no channel length modulation. Then your R naught will be infinity. So basically this is the ideal case only. This I am talking about ideal case. So in ideal case, lambda will be 0. This was ideal case. This complete was ideal case. So in ideal case, your lambda will be 0. There will be no channel length modulation and your R naught will be infinity. Well and good. Let's move on to one more concept, that is early voltage. What is early voltage? What is your ID? ID set when there is CLM present. That is equals to ID set ideal into 1 plus lambda VDS. This is your ID set, right, in channel length modulation. When will this current be 0? To put this current equals to 0, put this current equals to 0, ID set in channel length modulation. To put this current equals to 0, what should happen? 1 plus lambda VDS should be 0. VDS will be minus 1 by lambda. So the value of VDS, at which the drain current becomes 0, that is known as early voltage. Early voltage. So your early voltage is 1 by lambda. And in the graph I showed you, what did I show you in the graph? If you increase it in previous, this early voltage will be. Conceptually it will never be used. Conceptually early voltage will never be used. But sometimes in the question what they can do, they can give you the value of VA. That they will say that your early voltage is some 200 volts. Early voltage is some 200 volt. Then what you will think, okay, my lambda will be 1 by 200. So lambda is there. From there I can find the value of R naught. That will be 1 by lambda ID set. So 1 by lambda is basically 200 by ID set. ID set in ideal case. In ideal case I can find ID set. Let's assume that is 0.02. So your R will be some 10 to the power 4. R naught will be some 10 to the power 4. So in the question it will be sometimes used. So they can give you the early voltage. That early voltage is some 200 volt. So from there you can find the value of lambda, and from there you can find the value of R naught. So in questions it can be used. So that's why I told you here. So what is early voltage? The negative value of VDS at which the drain current becomes 0 when channel length modulation is present. Well and good, that is early voltage. Now one last concept is left, that is body effect. So when we were studying MOSFET, what did I tell you? What did I tell you? I told you that source I am taking as reference, and I told you that I am shorting source and body. I told you that my source and body are always shorted. This is what I told you when we were studying MOS physics. Now, what if my source and body are not shorted? I am taking again source as reference. Now, what if I put body to be negative? What if I put body to be positive? And what if both are shorted? What will happen in the circuit? Sorry, not in the circuit. What will happen in the device? So that we will see. But before that, I will take a break of 1 minute. Then we will start. So if I put some bias on body, whether it is positive or negative, it will change my VT voltage. It will change my threshold voltage. So let's check that. If my VSB is 0, what happens? There is no change in threshold voltage. No change in threshold voltage. In threshold voltage. Now, what do I mean by that? Let's assume I go to a market and I say that, sir, I need an NMOS. So he will give me an NMOS. Okay, so I am having an NMOS. Now he will say that the NMOS that you are having, that has the threshold voltage of 0.7 volt. I went to market, I asked for an NMOS, he gave me an NMOS. He is saying that the NMOS that you are having, that has the threshold voltage of 0.7 volt. What does he mean by that? He means that if your source and body are shorted, if there is no potential between source and body, then your threshold voltage is 0.7 volt. This is what he means. If he is saying the threshold voltage is 0.7 volt, if I am saying the threshold voltage of my NMOS is 0.7 volt, that means my source and body are shorted, then this threshold voltage is there. If I apply some negative bias or positive bias on body, the threshold voltage will change. So that is the scene. So there is a formula which you don't need to remember, but I am just writing it. Vt equals to Vt naught plus gamma 2 phi f plus Vsb minus root 2 phi f. Threshold voltage of NMOS. Of NMOS. What is this Vt naught? That Vt naught is that 0.7. If I am saying my Vsb is 0, if I put Vsb here equals to 0, so I will get Vt equals to Vt naught. What is this phi f? That is work function. Sorry, not work function. This is surface potential. Phi f is surface potential. Phi f is surface potential. So you don't need to think about it much. Let's move on to our concept. We will come back to that formula later on, but let's move on to our concept. Now I am saying my Vsb is positive. What do I mean Vsb positive? That means my base potential is negative, because again I am taking source as a reference. So my base potential is negative. According to that formula, what should happen? The threshold voltage should increase, and it will increase. Why so? That I will tell you. This is source which is at 0, body is at negative now. There is a diode. This is P substrate and this is N, so diode is something like that. Here you are having negative potential and here you are having 0. Negative and 0. What you are doing, if you are applying negative potential at base, what you are doing? You are increasing the forward bias. Increasing the forward bias. Right? Okay, I am sorry for that. Just brainwashed. Increasing the reverse bias. What you are doing? Increasing the reverse bias. If you increase the reverse bias, at the source side, if you are increasing the reverse bias, what is happening? The depletion width here will increase. If the depletion width is increasing, that means there will be strong electric field in this direction. Now there are electrons. What does the source do? What is the work of source? To provide the electrons to the channel and it will get out of the drain. The work of source is to provide the electrons to the channel and it will get out of the drain. Now you are increasing the reverse bias. Because of that, the depletion width is getting increased, and because of that, there is high electric field. Now this electron will try to move here in the channel, but there is this high electric field that will give the force to electron in the opposite direction. Applied negative reverse bias, depletion width increased, electric field increased in this direction. Now there are electrons who wants to move in this direction, but since there is very strong electric field, the electrons are not going here, the electrons are pushed back into the source only, in this n plus only. In n plus only, the electrons are pushed back, so electrons are not even reaching towards the drain. So less electrons are reaching towards the drain. So to get more electrons now, what do you need to do? You have to increase the Vg potential. That means you have to increase the threshold voltage. Previously, when Vg was equals to Vt only, you were getting some current. But now the electrons are not even reaching there. So you have to increase the Vg potential so that the electron supply can be done from the battery, and electrons reach here, and there will be electrons in the channel. Now, what is happening? Since the reverse bias is so strong and the electric field is so strong, the electrons are not even reaching there. So for that, you have to apply a higher VGS value. That means you have your VT will increase. So if base is at negative, sorry, not base, if body is at negative potential, that means your VT will increase. Now, one doubt people can get. What is that doubt? That doubt is, sir, you are saying that here the reverse bias is getting increased. This is what you are saying. But sir, one thing is also happening, that I can make a diode here as well, and this side you are applying negative potential here, and at the drain we already apply positive potential. That means the reverse bias is getting decreased at drain side as well. So if reverse bias is getting decreased at drain side, that means there will be higher electric field that will attract the electrons, because the electric field will be in this direction. The electric field will be in this direction. This I have already explained in MOS physics. So this electric field will be in this direction. So the reverse bias at drain side is also getting increased. So high electric field, that means that will attract the electrons very fastly, and the current should increase. That means the VT value should decrease. This is what you can think. But here the electrons are not even getting out. The electrons are not even getting out of source terminal. Then what is the point of this high electric field towards the drain? I admit there will be high electric field towards drain, but electrons are not even getting out. So what is the point of that high electric field? So first the electrons has to get out of the source, then this electric field will be useful. If the electrons are not even getting out, what is the use of this electric field? No use of this electric field, right? So here, what is more dominating? The dominating part is this electric field. This is the dominating part, because this is not even letting the electrons get out of the source terminal. I gave you the example of that tap. Your hole of water, that tap was there, no? That tap. Let's assume this hole is very large. मान लो ये बहुत बड़ा होल है यहाँ से पानी आने का. That hole is very large. But if there is no supply, what is the use of this hole? What is the use of this hole? जब पानी आ ही नहीं रहा है तो कितना ही बड़ा होल कर लो, कितना ज्यादा पानी आ जाएगा, नहीं आएगा. But we need water. We need the supply of electron. The supply of electron is reduced. So for that we have to apply higher VG potential, and then that will increase the VT value. Understood this concept? Even if you are having doubt, that is also clear. So this doubt is clear. And also in the formula you can see, if VSB is increased, then this factor will be increased. High factor minus low factor, that means the overall factor is positive, so the VT value will increase. So in the interviewer, this is the favorite question of interviewers, that I can keep it like this. I can make a few more things here. So when there was VSB was 0, let's assume this much was the depletion region. This much was the depletion region when VSB was 0. Why this much was the depletion region? Sir, there is no supply. Why there is depletion region? In PN junction, even if there is no supply, there is depletion region, right? Even if there is no supply, the depletion region is always present. If there is positive supply, the depletion region will be reduced. If there is negative supply, the depletion region will increase. So even if there is no VSB, still there is this depletion region. Now if you are applying VSB to be positive or VB to be negative, then this depletion region is getting increased, right? Because you are increasing the reverse bias here. Also the reverse bias is getting increased here as well, but that is not dominating. Dominating is this part, because you are not even getting the supply of electron. So this depletion region is increased. Depletion region is increased. So this is the case for VB negative, or you can say VSB equals to positive. VB negative or VSB equals to positive. And this was the case for VSB equals to 0. So let's write it down. So when VB equals to negative, what you are doing? Reverse bias at source side is getting increased. Reverse bias at source side is getting increased. What will happen? Electrons from source will feel high electric field, pushing them back into the source terminal. Pushing them back into the source terminal. And for that you need a higher VG. Yeah, so electrons will feel a high electric field, so that will push them back into the source terminal. So you need high VG. Higher VG required. Higher VG required. And because of that, what will happen? VT is increased. VT is increased. Well and good. Okay. Now we will check for VSB equals to negative. Third case is when VSB is equals to negative. VSB is negative, that means your VB is positive now. VB is positive. So now if VB is positive, as per the formula, what should happen? Here VB is positive. If VB is positive, what should happen? VB is positive, that means VSB is negative. So this factor will be less. So less minus high, that means this factor will be negative. So VT should decrease. And this is what happens. The threshold voltage decreases. So if VB is positive or VSB is negative, the threshold voltage will decrease. Why so? Because here you are having source, this is N and this is P plus, this is negative and this is 0. So 0 and negative. Sorry, VB is now positive. VB is positive. Sorry, VB is positive. So 0 and positive. So what you are doing? You are increasing the forward bias now. You are increasing the forward bias. So this depletion width will be very small. And since this depletion width is very small, the electron can get out of this very quickly. So you need to apply lesser VG voltage. Very easy, just the opposite of this. Depletion width is very small, so electron can get out of this depletion width very easily. So the current will increase. That means at lower VG value only you will get more current. So this source can supply more electrons now. You don't need gate potential for the supply of electrons. You have the source to supply the electrons. So this source can supply more electrons now. Right? Now the source can supply more electrons. Yeah, so this is what I have wrote. Forward bias towards source side is increasing. Source can supply more electrons at lower VG and then VT will reduce. Now people will have one more doubt. They will say that, sir, here also you are decreasing the reverse bias. If you are decreasing the reverse bias, there will be less electric field, there will be less depletion region. That means there will be less electric field and electron will feel less force. So if electron feels less force, then there will be less current. This doubt you can have. But again, there is this explanation that this side is dominating. The source to body size is dominating now. Why it is so? Because even if there is less electric field, but still there are so much of electron. There's so much of electrons are being supplied that even this less electric field can pull these electrons and there will be current. Or you can understand this with the analogy of tap as well. That in the tap, this hole is small, but so much of water is coming. So much of water is coming. So much of water is coming. So there will be large water only. There will be large current only. So at low VGS only, at low VG potential only, you will have large current. The hole is small, but still there are a lot of water is coming. So there will be large water flow. So that means there will be more current. So at lower Vg only you will get more current. So Vt is decreased here, and when Vb was negative, the Vt got increased. So this was the concept, and we can draw it here. This Vb is positive. So here the depletion width is getting reduced, but there will so if it is reduced, so there is large flow of electrons, and that will increase the current. So at lower Vg only you will get some current. So your threshold voltage is decreased. Now the question comes, sir, here the threshold voltage is less. So why don't we always keep base at positive potential? Why do you keep source at 0 and body at 0? We should keep VSB as negative. We should keep VSB negative so that we have the lower threshold, and at lower value of threshold we get some current. Now for that my question will be, what was your target for MOS? You wanted to use it as an amplifier, or also you can use it as a switch, but was the target to have lower VT? No. If your VT is in middle, it's fine. Let's draw a graph first. Root ID versus VT. So that will help me to explain my point. Root ID versus VGS. This graph I am drawing. There is this VT1, VT2 and VT3. Let's call this one as VT1, this one as VT naught, and this one as VT2. If I am saying this is VSB equals to 0, so what this will be? VSB equals to positive or negative? Positive. That means your VB is negative. And what this will be? VSB equals to negative. That means your VB is positive. Because at positive VB voltage, if VB is positive, your threshold voltage is less. This value is less than this, than this. So at lower threshold voltage, you are getting some current. But was that your target? This was your target? No. If you keep VB to be positive, what will happen? If you keep VB to be positive, if I am having positive potential here, what will happen? This is N, this is P, and here positive potential is there. Now this diode will drive some current, and that is unwanted. There will be unwanted power consumption in body diode. In the MOSFET, there will be unwanted power consumption. If my VSB is 0, if my VSB is 0 volt, this will be also at 0 volt. This will also be 0 volt. There will be no current in the diode. The diode will not drive any current. If both source and body are shorted, there will be no current in the diode, so that diode will not drive any current. If diode is not driving any current, so there is no power consumption. So if you are keeping VSB positive, sorry, if you are keeping VSB negative, that means if you are keeping VB to be positive, you are having unwanted power consumption. What was the issue when VSB was negative? What was the issue when VSB was positive? That means if VB was negative, so the issue was that our VT was getting increased. So this is also not we want, that I don't want VT to be increased. And if VSB is positive, what is the issue? There is unwanted power consumption in the body diode. There is unwanted power consumption in the MOS circuit, and this is not I want. So that's why I keep VSB to be 0 only. So there is always some issue with VSB positive as well, with VSB negative as well. So when first thing is, when VSB was positive or you can say VB is negative. This seems more intuitive. VB is negative. Okay, so if VB is negative, that means VT will be increased. VT will be increased. This is not desirable. Not desirable. And secondly, if VSB is negative, if VSB is negative or VB is positive, then what will happen? This is N plus, and then this is P substrate body, P body I am writing, and this is at positive. So it will drive some current, and because of this current there will be unwanted power consumption. Unwanted power consumption. And this is also not desirable. That's why we always try to keep VSB equals to 0 volt, or I can say source body shorted. Source body shorted, or at least the minimum forward bias. At least the minimum forward bias, or I will write at least minimum forward bias. Understood this point? Minimum forward bias. What do I mean by minimum forward bias? That means here I will have minimum forward bias. If there is something in my circuitry that I cannot keep source and body shorted, so I will ensure that my body potential is such that I am having minimum forward bias. At least minimum forward bias. So that there is no unwanted power consumption. Well and good. Okay. Yeah, one correction I would like to make here is that this correction is that I shouldn't write at least minimum forward bias. My target would be to get the optimum threshold voltage. If I am not getting that, that means if I am not able to keep my source body shorted, if I can't keep this thing VSB equals to 0, then I will try to keep VSB in negative bias only. I will try to keep that in reverse bias. VSB equals to positive. If VSB is positive, that means this is positive, this is 0, source is 0, and body is negative. So I will try to keep the diode in reverse bias so that there is minimum leakage current. There is no current in the diode. Even if my VT is increased, that is fine for me. VT is getting increased, that is fine for me. What will be my first target in the IC? If I am designing an IC, what will be my first target? My first target will be source and body should be shorted. If I am not able to achieve that, what I will think second? My second concern will be the power consumption. I don't want high power consumption. VT is increased, that is understandable, but I don't want high power consumption. If I keep VSB negative, that means if I keep VB to be positive, I am increasing my forward bias between source and body. And if I increase my forward bias, there will be current increasing that, and that will lead to unwanted power consumption. But I don't want that. So I would keep base at the most negative potential in the IC. Whatever the most negative potential is there, I will keep it there, so that even at least the source and body are reverse biased. Getting this point? If the source and body are reverse biased, I will get higher VT, I will get lesser current, but at least I will not have unwanted power consumption. So I will not say that I am keeping it at minimum forward bias. I will say that I will try to keep it at maximum possible reverse bias. Not maximum possible. I will try to keep it at reverse bias. What will be my first target? My first target would be VSB shorted. If I am not able to achieve that, I will keep VB to be negative or VSB to be positive, because I want my source to body diode to be reverse bias. So, or source and body shorted, or at least source to body diode should be reverse bias. Source to body diode should be reverse bias. should be reverse biased. Reverse biased. And this all we studied for NMOS, not for PMOS. For PMOS, it will be opposite. First thing is that you would always want source and body shorted. But in case of PMOS, what will happen? Here it will be P positive. So your diode will be something like this. So you would want to keep VB to be positive so that it is more reverse biased. And if it is more reverse biased, there will be less power consumption. So in case of PMOS, if VB is positive, then VT will get higher. And if VB is negative, then VT will get lower. Right? And best thing you would want is source and body are shorted. If they are not shorted, you will try to keep VB to be positive so that there is no unwanted power consumption in the diode or in the MOSFET. Are you getting this point or not? I hope you have understood the complete MOS physics. I hope you have understood the complete whatever the phenomena, whatever the concept that I wanted to deliver. Now understanding MOSFET amplifiers, MOSFET biasing, it will be very, very easy for you. That's why I took so much time in MOS physics. People will say that this is needless, this is not relevant to gate examination, this is not relevant to analog electronics, this is not relevant to placements, but everything is relevant. Once we will deal the question, you will realize everything is relevant. So after this, we will try to solve an assignment, and I hope you have understood all the concept. Okay. So if you found the video helpful, you can share it. Thank you. Hi everyone. So now we have studied MOS physics. Now it's time to solve an assignment. So there will be 4 to 5 questions there. So let me show you the questions. This is the first one. A MOSFET is given. You have to find V naught for two conditions. First, considering R equals to 1 kilo ohm, and second one R equals to 4.5 kilo ohm. Then there will be these 6 configuration. 2 configuration are there more. So you have to find the region of operation. Mu and Cx value is given, W by L value is given, Vt is given. These configuration are given, values are given, Vgs value is given. So like that, you have to find the region of operation. 4 configuration, 5th, 6th configuration. The next one, this is the third question. You have to find that drain current of MOSFET. Drain current you need to find. That means this current you need to find. Drain current. These configuration is given. All those values are also given. Here also you need to find the okay. Here you need to find the RS value such that your op-amp is MOSFET is working in saturation region. So how will you find that? You can try it. And then here you need to find the bias current in the transistor. What do you mean by bias current? Drain current only. So again you need to find the drain current only. So here again you need to find the ID value. I guess that's it. Yeah. So these questions are there. We will solve one by one. You might not be able to solve it if you are solving it for the first time, because if you are just watching the video of MOSFET for the first time, you might not be able to solve it. No worries. Even when I was the student, I was also not able to solve it. So let's start with the first question. Slowly you will develop the approach. Let's start with the first question. This is R equals to 1 kilo ohm. So we will take two conditions one by one. First we are taking R equals to 1 kilo ohm. So let's take R equals to 1 kilo ohm in the next page. This is circuit A. I will remove this R. This is 1 kilo. Now you don't know in which region MOSFET is working. You have the value, you have VGS value. This is gate, this is drain, and this is source. If there is no fixed potential, we have to assume, right? So we have assumed, like we have to assume in the given sense only. What is the given sense? What is the general sense? I told you what is the general sense. The general sense is, क्या हो रहा है writing pad? Yeah. So what is the general sense? General sense is this is gate, this is source, and this is drain, right? So we have to assume it in that same manner. Yeah. So what is the VGS value given? VGS value is 2 volt. What is the VDS value? You don't know, but that is V naught because source is grounded only. VDS is, and VT is 1 volt. VT is 1 volt. Now can you tell in which region the MOSFET is working? No. You don't know in which region MOSFET is working. So you have to assume. We will start by assuming this is working in saturation region. So this is my way. I always assume in saturation region. Then I see if it is working in saturation region only, and then I will decide. So this is my way, that I always start by assuming it in saturation region. You can start from linear region as well, but my suggestion would be always start from saturation region. So let MOS is working in saturation region. Let MOS is working in saturation region. So what will be your ID? What will be the ID? ID value will be mu n ux w by 12 vgs minus vt square. I guess this value is given mu n ux w by 12. That would be 100 micro. So mu n ux into w by l, that is 2 milli actually. Okay, I will write down one by one. Mu n ux is 200 micro into w by l is 10 by 2. Always write down this micro, milli, kilo, always write it down. When you are solving the problem of MOS, always write it down along with. What is the value of VGS? That is 2. And what is the value of VT? That is 1. So what do you get? You are getting 1 milliampere. ID value you are getting 1 milliampere. Are you agreeing to this point? ID value is 1 milliampere, right? This value you got 1 milliampere. Now if this current is 1 milliampere, what will be the V0 value? What is V0 value? V0 value is 5 minus 1 kilo ohm into 1 milli. That would be 5 minus 1, that would be 4 volt. So V0 value came out to be 4 volt. But this is not your final answer. Now what did you do? You assumed here. You assumed MOS to be working in saturation region. So now you have to recheck if the assumption is correct or not. So what did you assume? You assumed the MOSFET to be working in saturation region. So now we will check in what region our MOS is working. So our V0 value is 4 volt. So now what is our VGS? VGS is fixed. That was 2 volt. What was our VT? VT was 1 volt. So what is my V overdrive? I told you what is V overdrive? V overdrive is VGS minus VT. V overdrive is VGS minus VT. I don't remember if I told you about this term or not. So V overdrive is VGS minus VT. Just nothing, just a term that is given to it. V overdrive. Just a simple term, nothing else. So V overdrive is 2 minus 1, that is 1 volt. So 4, and now what is VDS? VDS is 4 volt. Here VDS is equals to V0 only. VDS is equals to V0 only, that is 4 volt. So here what do you see? That VDS is greater than VGS minus VT, or directly we can write VDS is greater than V overdrive. So what do you understand by that? If VDS is greater than V overdrive, what do you understand by that? That MOS is in saturation. Saturation. So that means assumption, the assumption that we made, assumption correct, right? So the assumption that we made, that is correct. So if our assumption is correct, that means what is the final answer? What did they ask to find? You have to find the value of V0. So V0 came out to be 4 volt. So here your final answer is V0 is 4 volt. Now take the condition of R equals to 5 kilo, sorry 4.5 kilo. If R is 4.5 kilo, what will happen then? R is 4.5 kilo. What will be your ID? So again what I will do, assuming, what will I assume? Assuming saturation region. Saturation region. Again I will assume saturation region. So what will be my ID? ID will be same value. ID will be same. Why so? Because ID depends on VGS minus VT, and VGS minus VT is fixed here. Or if you don't want to do it, you can Start. Mu n Cux. Again, I am assuming it to be saturation region. Mu n Cux W by 2L VGS minus VT square. What is mu n Cux W by 2L? That is 200 micro into 10 by 2. 200 micro W by L is 10 by 2. What is VGS? VGS is 2, VT is 1. So the current came out to be 1 milliampere. If the current is 1 milliampere, if this current is 1 milliampere, tell me what will be the value of V naught? V naught will be 5 minus 4.5 into 1, 4.5 kilo ohm into 1 milli, right? So V naught will be 0.5 volt. V naught will be 0.5 volt. Now, what will be the value of VDS? VDS will be VDS, drain to source. VDS will be V naught only, and that is equals to 0.5 volt. What is VGS minus VT? VGS minus VT. What is the value of VGS minus VT? VGS is 2 minus VT is 1 volt. Now what do you see here? Here VDS is less than VGS minus VT, right? Here VDS is less than VGS minus VT. That means it is working in linear region. This is working in linear region. So the assumption that we made, that is wrong. This is wrong. So assumption is wrong. What did we do? First we assumed that it is working in saturation region. So for saturation region we know the current equation. We applied that current equation. Then we got to know, after applying the current equation, we found the value of V naught. Then we got to know VDS value is 0.5 volt. So based on that, our VDS is less than VGS minus VT. That means our MOS is working in linear region, not in saturation region. So assumption is wrong. Now we will make another assumption. What assumption we can make? Now we will make an assumption that our MOS is working in linear region. Now you will say, sir, if it is not working in saturation region, it is certain that it should be working in linear region. So why we are calling it as assumption? It is assumption only, because it is not sure that it is working in linear region only. If it is not working in saturation, it can be in cutoff as well. So now you will write assuming linear region. You are not very sure that is linear region only. So again you will assume only, and then you will find the value of V naught, and then you can comment if your assumption was correct or not. Are you getting this point? Like I have seen many people directly write that now MOSFET will be working in linear region. So now we will apply linear region equation. But whether it will be working in linear region or not, that will depend on the V naught value that you get. So you can't really say that certainly it will be in linear region. No, assuming it to be in linear region. So again you will assume it to be linear region, in linear region, and then you will find the value of V naught, and then you can comment assuming linear region. Okay, so what is the equation in linear region? Do you remember what is the equation? Mu n Cux W by L VGS minus VT into VDS minus VDS square by 2. This is the equation, right? You should be able to remember. Slowly you will remember if you don't remember. Okay, what is the value of ID? Look, do you know the value of ID? No. In case of linear region, you don't know the value of ID. Do you know the value of VDS? No, because VDS is also V naught. So there are two unknowns. But one thing you can see here is that 5 minus V naught by 4.5k is equals to ID. If this is ID, that means the same current is flowing through this resistance as well. So 5 minus V naught by 4.5k is equals to ID only. Are you getting this point? Simple network analysis here, right? So 5 minus V naught divided by 4.5k. I will certainly write k here. Why so? Because of the units. Unit पे गड़बड़ हो जाएगा, तो k लिखना ही है. We have to write k. Here I am writing mu n Cux, then I will certainly write 200 micro into 10. What is VGS minus VT? That is 1 only, because VGS is 2, VT is 1. That is 1 only, into VDS is V naught minus V naught square by 2. Now my complete equation is in V naught only. Are you getting this point? So that's why I replaced ID with V naught. 5 minus V naught by 4.5k. So from here, what do you get? This is 2 milli, 4.5 kilo. Look, what I will do, this value is 2 milli, and if I multiply 2 milli into 4.5 k, then k and milli will be cancelled. K is 10 to the power 3, milli is 10 to the power minus 3. So they will make 1 only. So that will be cancelled. So that advantage I will take. 5 minus V naught, 4.5k into 2 milli, basically it will be 9. V naught minus V naught square by 2, right? So this equation we can solve. 4.5 V naught square, this is 10 V naught plus 5. V naught will be 10 plus minus B square minus 4AC, 100 minus 4AC. 4 into 4.5, that will be 9 into 4 minus 4.5, that is 18. 18 into 5, 90 by 2A by 9. Now you will solve it and you will get two values of V naught. So which value you will pick? Let me see the final answer. I might have written it. So what are the two values we get? 1.46 and 0.76. 1.46 volt and 0.76 volt. Two values we are getting. Now the question is which value you will take. So V naught value here I will write. We are getting two values of V naught, 1.46 volt and 0.76 volt. So which value you will take? How will you decide? If let my V naught is 1.4. If my V naught is 1.4 volt, what is my VGS minus VT? That is 1 volt. So here, and V naught is equal to VDS only in our question. So here VDS is greater than VGS minus VT. That means it should go into saturation. But it is not in saturation. That we have already seen by the previous analysis. By the analysis here, what we got to know? That it is in linear region. It is certainly not in saturation region. That we have already seen. That it can't be in saturation region. So this case is not possible. This case is wrong. Because we already know that our MOS is not in saturation region. It can be in linear, it can be in cutoff, but certainly not in saturation region. So that condition is eradicated. Now let's talk about the second condition. If I take V naught equals to 0.76 volt, that is equals to VDS. What is the value of VGS minus VT? That is 1 volt. So here what do you see? VDS is less than VGS minus VT. VDS is less than VGS minus VT. That means it is in linear region. And the assumption that we made, that is correct. Assumption correct. So our V naught will be 0.76 volt. So that will be the answer. So many times these kind of questions are asked. You don't need to worry about these kind of questions. You don't need to what do we say, panic when you see these kind of questions. The general way is first assume the transition to be in saturation region, then find the conditions. Then you get to know your assumption is right or wrong. If it is correct, well and good, question is solved. If it is wrong, then make another assumption. The second assumption should be, it should be in linear region. Then you make that assumption, then solve the question. If you are getting two values, then pick that solution only which makes your assumption correct. So here this assumption was being corrected. So our V naught value was 0.76 volt. In the examination, within 2 to 3 minutes, you will be able to solve these problems. No need to worry. Here I am explaining. That's why it is taking time. Let's move on to the next problem. Solve this problem by your own, then only see the solution. Pause the video and solve this. Yeah, so let's solve this problem. So here they have given the current direction. Current direction is downward. And one thing I know that this is NMOS. Why so? Because arrow is outward. So I know this is NMOS because arrow is outward and current direction is given like this. That means this has to be drain. In NMOS, what is the direction of current? Drain to source. And in case of PMOS, what is the direction of current? Source to drain. That we have to remember. Electrons were going into the drain. So direction would be drain to source. So the current direction is drain to source. So the upper one is drain, lower one is source. First thing I saw that this is NMOS. Second thing I saw that the current is going from up to down. That means drain to source. That's it. And this certainly has to be gate. What is the VGS value here? 3 volt. VT value must be given in the question, that is 1 volt. Let me recheck. 1 volt. Any other information you have? You have the ID, current ID, that is given 150 microampere. So this is the all information you are having. Now to comment on that, you need the value of VDS and you don't have that. So first what you will do, you will assume it to be in saturation region. Let MOS in saturation region. Let MOS is in saturation region. If it is in saturation region, what will be ID? ID will be mu n. I will again and again write this formula so that you memorize it. Mu n Cx W by 2L VGS minus VT whole square. What is the value of mu n Cx? Here it is 100 micro. W by L is 10 by 2. VGS value is fixed minus VT value is 1. So what do you get? ID value you get is 200 microampere. So what did you get to know here? That if the MOS was working in saturation region, the current would have been 200 microampere. But the given current is 150 microampere. That means it is not working in saturation region. What do you do? ID versus VDS curve you have studied, right? If your VDS was such that it is working in saturation region, if your VDS was such that it is working in saturation region, then your VDS would have been somewhere here. Because in the saturation region, the current is maximum. The current is saturated. That means this is the maximum current that it can take. This is the scene. This is the maximum current that it can take, which is 200 microampere. For a particular VGS value, this is the maximum current it can take. VGS is fixed, that is 3 volt. So for a particular VGS value, this is the maximum current it can take. But now it is taking 150 microampere. That means VDS should have been somewhere here, right? This is your VDS operating. Operating means at which this transistor is operating. So this is your VDS operating. What is that region? Linear region. So your MOS, here you can say MOS is not in saturation but in linear. Did you understand this question? First you solved it, you found the current. The current came out to be 200 microampere. So that you got to know that for a VGS value of 3 volt, this is for fixed VGS. Here VGS is fixed. For a VGS value of 3 volt, your drain current should be 200 microampere. But the current is lesser, that means it has to be in linear region. That's it. So this was the first question. Let's take up the next one. What they are asking in the next one, I guess they have changed the data here. Okay, 2.5 and 200 microampere is coming. 200 microampere is coming. This is 2.5 volt. And from here 200 microampere is coming. Do you have the idea of VGS value? No. And what will be drain, what will be source? The current is coming like this and it is NMOS, so it has to be drain to source, and this will be gate only. The current will always be flowing in drain to source, right? Yeah. So ID value is given 200 microampere. Do you have the VGS value? Nothing you have. Again, let saturation region. So if it is saturation region, then ID would be equals to ID. Okay, I will write down the formula again and again so that you remember it. ID will be equals to mu n ux w by 2L VGS minus VT whole square. So 200 micro is equals to, I will write down this micro for sure. 100 micro into W by L is 1 by 2 VGS minus VT whole square. So from here VGS value came out to be 2, right? Not 2, sorry, 3. Yeah, VGS value came out to be 3. So from here VGS came out to be 3 volt. Now your VGS is 3 volt. So if it is in saturation region, your VGS should be 3 volt. But let us check if our assumption is correct. VGS is 3 volt. What is VDS? VDS is 2.5 volt. What will be V overdrive? VGS minus VT. VGS minus VT. That will be 2 volt. Here VDS is greater than V overdrive. That means saturation region. And if it is in saturation region, that means your assumption is correct. Assumption correct. Your answer is also correct. Your VGS is assumption is correct. That means it is working in saturation region only. And this is your final answer. They did not ask VGS value or anything. They just asked the region of operation. And here linear region was the answer. Right? Let's move on to the next one. This is very simple actually. Right? I can solve it here only. Now you will say, sir, now the current direction is not given. How we will decide which is drain, which is source? You can decide, right? If this potential is X, what will be this potential? X plus 4. So the one which is at higher potential, that is drain. In case of NMOS, the one which is at higher potential, that is drain. Do you remember these points? I will revise it once again. ध्यान से सुन लो, ठीक है, सभी ध्यान से सुनेंगे. In case of NMOS, the one which is at higher potential, that is drain. Lower potential is source. The current flows from drain to source, higher potential to lower potential. That's it. In case of PMOS, the one which is at higher potential, that is source, and one which is at lower potential, that is drain. The current flows from higher potential to lower potential, that means from source to drain. That's it. Very easy. You can remember it, right? Yeah. So one which is at higher potential, that means that will be drain. This will be source. Drain, source. And certainly this will be gate only. So here you can see what is the value of VDS? 4 volt. What is the value of VGS? 2 volt. What is your V overdrive? VGS minus VT. That means 1 volt. So VDS is greater than V overdrive. What is the answer? Saturation region. That's it. Very easy, very straightforward. You can solve this one here as well. What is the value of VDS? 2 volt. What is the value of V overdrive? VGS minus VT. Look, you will say that now, sir, gate is at higher potential. While designing drain and source, there is no meaning of VGS value. Only by VDS you are deciding. People may say that, sir, this is at the highest potential, so this should be drain. No, no, no. This will always be gate only. Now the task is between these two. This is at X, this is at X plus 2. So this will be drain, this will be source. What is your VDS? 2 volt. What is your V overdrive? That is VGS minus VT. 4 minus 1, 3 volt. So here VDS is less than V overdrive. What does this signifies? It is in linear region. Well and good. So linear region, saturation region. Okay. Now this question. Here you don't have potential of anything. You don't know the potential of drain, you don't know the potential of source. What will be drain, what will be source? Here you have to assume. If there is no potential given, you have to consider that this will be drain and this will be source, the general form. In previous questions, you had the potential of someone, you had the potential of drain and source, anything. But here you don't have the potential, you have to assume that upper one will be drain, lower one will be source, because this is NMOS only. Because the arrow is outward, this is NMOS only. Here again I will assume this is drain, this is source. Let's assume this potential is X, or forget about X. This potential is Vd, this potential is Vs, and this potential is Vg only. What is the value of Vds here? Vds, that is Vd minus Vs only. What is the potential of Vgs here? What is the potential of Vgs? That is Vg minus Vs. But you can write down Vg in terms of Vd. This is Vg minus Vs only. But what is Vg? Vg is Vd plus 1.5. Vg is Vd plus 1.5. Are you agreeing to this point? Vg plus 1.5 minus Vs. You can write Vgs is 1.5 plus Vds. Are you agreeing to this point? Vgs is 1.5 plus Vds. Did you understand this point? Right? Vg minus Vs, then I write down the value of Vg, that is Vd plus 1.5. So it is 1.5 plus Vds. And what is Vt? Vt is 1 volt, that is given. Vt is 1 volt is given. What is the value of V overdrive? V overdrive is 0.5 plus Vds. So here what do you see? Vds is less than V overdrive. Are you agreeing to this point? Because V overdrive is 0.5 plus Vds. So it is certainly greater than Vds. So here V overdrive is greater. So what does that implies? That implies that this is linear region, because V overdrive is more. Vds is small, that means it is linear region. Did you understand this point? How did I solve it? I just found the value of Vds, Vgs and Vt. That's it. Here I will have the same target. What is the value of Vds? Okay, before this thing I will tell you one interesting thing, that is, so while defining the saturation region, what do we do? Vds should be greater than Vgs minus Vt, right? This is what we do. What is Vds? That is Vd minus Vs. What is Vgs? That is Vg minus Vs minus Vt. Source to source get cancelled. So Vd should be greater than Vg minus Vt. That's it. There is no role of source. In case of NMOS, there is no role of source for defining the region of operation. Same in case of PMOS. In case of PMOS, what will happen? VSD should be greater than VSG minus mode of VTP. Right? So Vs minus Vd should be greater than Vs minus Vg minus mode of Vt, whatever it is. Vs would get cancelled. Minus of Vd should be greater than minus of Vg minus of mode of Vtp. Then Vd should be less than Vg plus mode of Vtp. Simple mathematics I have applied. This minus minus sign, minus minus got cancelled, so arrow sign will also change. So this is also the condition. So, and these are the conditions. So here what do we understand? That there is no role of source potential for defining the region of operation. But still we write in this manner, because it is easier to remember. Here if I had told you these formulas, you would have forgot, okay, where will this arrow sign come, how will the arrow come, when there will be plus, when there will be minus. So this I don't wanted you to go through. So that's why I told this formula Vds is greater than Vgs minus Vt. But you have to remember that there is no role of source potential while defining the region of operation. Are you getting this point? If your Vgs is greater than Vt, that's it. If your Vgs is greater than Vt, then your transistor is on and everything is in your control. Whether it will be in saturation or in linear, you can directly know it by the potential of Vd and Vg. If it is on, if it is not on, then it certainly depends on source potential as well, because Vgs has to be greater than Vt. right? We have understood everything. So here just one interesting point I wanted to deliver, that source has no role until VGS is greater than VT, because before VGS less than VT, the transistor is not even on. After that, if VGS is greater than VT, then only these things will happen. And here by default we consider that VGS is greater than VT. Here we had to consider that VGS is greater than VT. If this was the case, that VGS is less than VT, less than 1 volt, then everything that we have studied, that is wrong. There is no meaning of that. So we have to consider, by default we consider that VGS is greater than VT. So I should have mentioned it in the question, that your VGS, you need to consider VGS to be greater than VT. Otherwise the transistor will be off. Yeah. So here as well VGS is greater than VT, so your transistor is on. That we have to certainly consider. So your VDS is VD minus VS. What is your VGS? Here what is your VGS? Your VGS is, what is your VG? VG is VD plus 0.5. VD plus 0.5 minus VS. So VGS is VDS plus 0.5 volt. What is VT? VT is 1 volt. What is V overdrive? V overdrive is VGS minus VT. That is VDS minus 0.5. Which one is larger? VDS minus 0.5. Which one is larger? VDS is larger, right? Let's assume VDS is 1 volt. So what will be your V overdrive? That will be 0.5. So VDS is larger. So VDS is greater than V overdrive. That means this is saturation region. Are you able to understand this point? But one thing I should have mentioned, that your VGS is greater than 1 volt. In all these questions, here I will write it with the yellow pen because this is in the question only. Let VGS is greater than 1 volt. So this we have to consider. Okay, well and good. Let's move on to the next problem. So here in the first two questions, what did we learn? We learned about how do we find the region of operation, how do we apply the drain current formula, how do we apply the saturation current formula, right? So these formulas we have applied and then we found the region of operation. Now we will move to better questions. Here you again need to find the drain current of MOS. Do you know the region of operation? Again we don't know. What will be drain, what will be source? Do you know the potential of this point? No. Do you know the potential of this point? No, you don't know. You know the potential of this point? Yeah, but you don't know the potential of this point. We will again consider by the same formula, that is, this should be drain, this should be source. When it will be interchanged, I will tell you in the question itself. But here we have to consider by the general way, that upper one will be drain, lower one will be source, because we don't know the potential of drain, right? You have to find the drain current of MOS. This is the question now. Tell me one thing, what ID will be equals to? Can you write one equation, that is ID plus V naught by 10K plus V naught minus 6 by 20K is equals to 0. Is that equation correct? Yeah. Outward current, this outward current, this is also outward current. V naught by 10K, this is also outward current, or this is also outward current. Addition of outward current is equals to 0. Simple KVL, I am applying, sorry, simple KCL, I am applying KCL at node V naught. KCL at node V naught. This is what I did. I will not call this one as equation 1 because I need to find the ID value. So for ID value, I will write 6 minus V naught by 20K minus V naught by 10K. This is my I naught value. Again, you don't know the region of operation. Again, you have to assume. Okay, so we will start by assuming. What I will do, let MOS is in saturation. MOS is in saturation. Then what will be ID value? ID value will be mu n Cx W by 2L. Now I am not going to write the formula. Okay. VGS value do we have? VGS value is 3 volt. VGS minus VT square. ID value came out to be 200 micro, right? Or 200 micro. So ID value came out to be 200 microampere. Now, if it is 200 microampere, what will be the value of V naught that we can find? So 200 micro is equals to 6 minus V naught by 20K minus V naught by 10K. 20 will go here. 2 into 10 to the power 4. This will be 2 into 10 to the power 4. This will be 4 only. 6 minus V naught minus 2 V naught. 3 V naught by equals to 2. So V naught will be equals to 2 by 3. So what you are getting? 0.67. When you solve this equation, V naught value we are getting is 0.67. V naught value we are getting is 0.61. What is your V overdrive here? VGS minus VT. That is 2 volt. Right? V overdrive is 2 volt. Here you can see VGS minus VT. V overdrive is 2 volt. What do you see here? That your V naught is equals to VDS only. This is your V naught. V naught is VDS only. Here your VDS is equals to V naught. V naught that is equals to VDS. This is lesser than V overdrive. What does this shows? Linear region. If it is in linear region, your assumption is wrong. So the assumption you made, that is wrong. So this ID, this is wrong, this is also wrong. So now again you have to make assumption. Assuming, what assumption you will make? Assuming MOS in linear or triode, linear region. For linear region, what is the current equation? Mu n Cux W by L VGS minus VT into VDS minus VDS square by 2. So those who are solving it for the first time, मतलब जो पहली बार पढ़ रहे हैं, they, for them it might seem a bit hectic, like so much of calculation is there, how do we remember all these things? But once you practice enough questions, you will be habitual. The only thing you need to do, first you need to consider, then you need to find the parameters. Not satisfied? Satisfied? Good enough? Not satisfied? Assume the other region. That's it. In the second one, it will be satisfied, that's for sure. Right? So yeah. Now you have again two variables, ID and V naught. But ID we have wrote down in terms of V naught only. So 6 minus V naught by 20K. 6 minus V naught by 20K minus V naught by 10K. Also, you should have good aptitude to solve the problems. Like calculation should be better. That's why I am showing you all the calculation, because in these kind of question, calculation becomes a very important part. So mu n Cux is 100 micro, so I will certainly write 100 micro. I will not miss that. Into W by L is 10. VGS minus VT is 2. VDS is V naught only minus V naught square by 2. Right? So here this is 2 into 10 to the power 4. This is 2 into 10 to the power 4. This is 10 to the power 4. So LCM will be 2 into 10 to the power 4 only. Right? So 6 minus V naught minus 2 V naught, and 2 into 10 to the power 4 will be going here, and this is already 10 to the power minus 4. Are you getting this point? So this will be 20 only. 20. 2 V naught minus V naught square by 2. Well and good. Is there any mistake I have done? W by L is what? 1. Yeah, that's what I was thinking. W by L I have taken here also 1. W by L is 1 here, not 10. So this will be 2 only. इतना आंसर तुम्हारे को याद था, माइनस वी नोट स्क्वायर. तो वी नोट स्क्वायर minus 7 v naught plus 6. So v naught, 2 v naught values we will get, I guess, from here as well. But you can tell which value I should take. Here I am getting 1 as well and 6 as well, right? 1 we satisfied over 6, 36, 42, yeah. So from here v naught value we get, 2 values we are getting, 1 volt and 6 volt. If you take this 1 volt, what will happen? Your V overdrive will be lesser than Vgs minus Vt, right? If I take V naught equals to 1 volt, okay, I will write if V naught is equals to 1 volt, what is V overdrive? That is 2 volt only. Vgs minus Vt, Vgs minus Vt is 2 volt. So here Vds is less than V overdrive, that shows linear region. Linear region, and assumption is correct. Assumption is correct. So your V naught value will be 1 volt. V naught value will be 1 volt. But if you take दो एरो लगा दिए यहाँ पे, if you take V naught to be 6 volt, what will happen? V overdrive will be 2 volt and your VDS will be greater than V overdrive. That shows saturation region, but in the previous part of video we found out that this is not in saturation region. Not in the previous part of video, but in the previous part of solution we found out that this is not in, okay, wait, yeah, this is not in saturation region, right? The MOSFET is not working in saturation region, because here when we assumed it in saturation region, it came out to be in linear region. So this is not, certainly not working in saturation region. So this cannot be true. So the only option true is this. So your V naught value is 1 volt. That's it. Okay. Let's try solving this question on your own. Now you have the enough aptitude. You can take your time and try solving this question on your own. The question is, the MOSFET is working in saturation region. That is given. If it is working in saturation region, what should be the value of Rs? So now you don't have to assume. It is given that it is working in saturation region. What should be the value of Rs? This you need to find. Tell me what is the potential here. Will it be 1 volt? Can you directly say it that it will be 1 volt only? Yes, I can directly say it will be 1 volt only. Why so? Because there is 0 ampere current here. If it was driving some current, let's assume if my circuit was something like this. 4R, R, this is 5 volt, and this is driving some 1 ampere current here. Let's assume this is driving some 1 ampere current here. Can you say this potential will be 1 volt? This is wrong. This potential will be 1 volt. No. If this is not driving any current, then only you can apply the voltage divider. No. Are you getting this point? अगर यहाँ से करंट नहीं जा रहा तभी तो वोल्टेज डिवाइडर लगाओगे. R1 by R1 plus R2 into V in. If it is driving some current, then you can't apply voltage divider. What you will have to do? You will have to assume a voltage V here. So V minus 5 by 4R plus V by R plus 1 ampere is equals to 0. Then you can find the value of V. But if this 1 ampere is infinite, this 1 ampere is not there. If this 1 ampere is not there, then what will be the case? This will be the case. And from here, what will be the value of V? That will be 5V minus 5 equals to 0. V will be 1 volt. Basic network analysis, very basic network analysis. But these kind of concepts we will again and again use. People will every time think that we can apply voltage divider, but we cannot apply. We can only apply if there is 0 ampere current. If the node is driving some current, if there are two paths, then you can't apply voltage division. There is only one path. This node can drive current only here. That's it. Are you getting this point? So that's why we cannot apply node analysis here. Here we can apply, but if it was driving some current, we couldn't have applied it. So here this potential is 1 volt, right? This potential is 1 volt. Yeah, so 1 volt is fixed here. So what is the value of VGS? Because if it is in saturation region, it is given, we don't need the value of VDS. VDS की वैल्यू की जरूरत ही नहीं है क्योंकि this is working in saturation region. So we only need the value of VGS. What is the value of VGS? That is 1 minus, let's assume this current is ID, so that will be 1 minus ID into RS. Are you agreeing to this point? Why you are agreeing to this point? Because this is source. What is the potential of source? VG we got to know here, that is 1 volt. What is VS? VS will be ID into RS because this is source, right? This node is source. So Vs would be ID into Rs. So Vgs will be 1 minus ID into Rs, right? Vt is given 0.5 volt. Now current equation is given already. So what is ID? ID is, here I can write ID is Kn into Vgs minus Vt because Kn is already defined. Kn is mu n Cx W by 12. Kn into Vgs minus Vt whole square. So ID is 119 micro, that is equals to 4.12 milli Siemens per volt milli. What is VGS? VGS is 1 minus 119 micro into RS. This is VGS. 1 minus ID into RS. So ID value 192 into RS minus 0.5 whole square. Now I will directly solve it in gate calculator, or in your main calculator also you can solve. But how will you solve it in gate calculator? What you will do, you will convert this into milli because milli and milli will get cancelled. So 119 micro in milli, what that will be? 0.119. So 0.119 micro divided by 4.12. 0.119, I guess, I don't think I will be able to show it. So 0.119 milli divided by 4.12 milli. Milli and milli got cancelled. Then I will take under root. So here I am getting 0.169. So 0.17 I can write. This is equals to 0.5 minus 119 micro into RS. Because 1 minus 0.5 is 0.5 only, right? Now people will say that Bhaiya, you took the under root. So here plus minus should come, right? Whenever you are taking under root, always take plus sign. We have solved enough question, I have solved enough problems. If I had taken negative sign here, what would have happened? What would have happened if I had taken the negative? So if I had taken the negative sign, what do you mean by that? You are saying that your VGS minus VT is negative. If you are saying, sir, if you take under root, that means plus minus should come. But is that so? Because here you are writing some ID value is there. So ID by Kn under root. This is what you are doing here. And that is equals to VGS minus VT. Now if you are saying plus minus should come. So if it is minus, if you are taking the minus sign here, what will happen? You are saying VGS minus VT is negative. And if VGS minus VT is negative, the MOSFET will not even turn on. So never take the negative sign. Always take the positive sign. So this is one thing that you can note down in your notes, or you can highlight, that you should always take positive sign whenever you are taking under root, because VGS minus VT cannot be negative, right? So many times teachers don't tell this concept why we are actually taking the positive sign. So positive sign should be taken, that everyone remembers why it should be taken, because VGS minus VT cannot be negative, right? So from here I can directly solve and find the value of RS. Yeah, so in the gate calculator instead I will solve it. Minus 0.5 divided by 119 micro. अरे यार 0.5 minus 0.17 divided by 119 micro into 1000. 2.77 kilo ohm. 2.77 kilo ohm. So this is the value of RS. Well and good. I guess one more question is left. That is also very good question. This was actually very easy question. Just everything was given. You need to find the value of RS. This question also you can try solving. That is a very good question. And where am I getting these all these questions from? Because they are NPTEL assignments. From there I am getting these questions. So whatever that is necessary for you, that I am dealing here. Okay. Yeah. So find the bias current in the transistor. So again ID current you need to find. This value given is 40 kilo ohm. So RR value is given 40 kilo ohm. Now what do you think? This current 100 microampere is the answer. ID is 100 microampere. Is that so? Complete current is coming. Is that so? No. That is true that here there will be 0 ampere current. This is true. But who said current cannot flow from here? Current can certainly flow from here. There will be no current here, but certainly the current can flow from here, right? So let us say this potential is V naught. Let us say this potential is V naught. Then what this potential will be? If this potential is V naught, this potential will be V naught by 2. Say yes or no, right? VDS value is V naught. VGS value is V naught by 2. VT value is 1 volt. Until you know the value of V naught, you cannot decide in which region it is working. So again you have to assume that it is working in saturation region or linear region. So again you have to assume. The choice is up to yours. In what region do you assume? Okay. But before that, we cannot have two variables V naught and ID. So we have to write ID in terms of V naught. So what will be ID in terms of V naught? From upward 100 microampere current is coming. Here how much current is going? Can you tell how much current is going in this direction? V naught by 2R. Right? You know the potential of this node, you know the potential of this node. V naught minus V naught by 2R. So this current is V naught by 2R. This current is ID. So 100 micro is equals to V naught by 2R plus ID. So ID you can write 100 micro minus V naught by 80K. 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 So if I want to write it in micro only, 100 micro minus, I will also write down in micro only. So what I can do? 1000 by 80, 1000 by 80 V naught micro. Did you understand what did I do here? I have 1 by 80K. I want to write it in micro. So 1 by 80K is similar to 1 by 80 milli. So if I multiply and divide it with 1000, so what I will get? 10 to the power 3 into 10 to the power minus 3. So 10 to the power minus 3 into 10 to the power minus 3. That will give me micro divided by 80. So this is how I converted it in the micro. Because here the current was in micro. So I needed all of them in micro only. Or I could have converted in milli. This was also a good way. But I thought of making it in micro. This is my ID. So my ID will be 100 micro minus 12.5 V naught micro. This will be my ID. Now what we are assuming? We are assuming MOSFET to be in saturation region. Or I can assume it to be in linear region, because as far as I remember, it will be in linear region only. But since we are following the same method, so let MOS in saturation. This ID that I found, that is irrespective of linear or saturation, right? This ID that I found, that is irrespective of linear or saturation, because I did not apply any ID equation. I just assume ID as a variable. ID will be equals to mu n Cux W by 2L. So 100 micro divided by 2. VGS minus VT whole square. What is VGS? That is V naught by 2 minus VT. What is VT? 1. Right. Now ID I can replace here. ID is 100 micro minus 12.5 micro V naught, 50 micro, that will be V naught by 2 minus 1 whole square. Now micro will get cancelled, right? Micro, it can get cancelled. 100 minus 12.5 V naught, and this is 50 here. This will be V naught square by 4 plus 1 minus V naught. So 100 minus 12.5 V naught. The calculation is a bit complex, and these kind of complex questions are asked in GATE examination as well. You don't think that this kind of complex calculation will not be asked in the examination. It can be asked. Many times it has been asked. So yeah, you should be ready that these kind of calculation can also come. You should have the patience that slowly I can solve these problems, right? So 12.5 V naught I will put here only. Now this will come here, so 37.5 V naught, and this will come here minus 50. Well and good, is equals to 0. कोई मिस्टेक तो नहीं कर दिया है, बस ये डर लग रहा है मेरे को. ठीक है, minus 50. Okay, 12.5 I can take common, I guess. So this will be 3 V naught, right? I can take common. V naught square minus 3 V naught, 50 divided by 12.5, 12 चौके 48, 4. That's it. What did I do? I took 12.5 common. So 12.5 into 3 is 37.5. 12.5 into 4 is 50. That's it. So from here I can get the value of V naught. Two values I will get, I guess. Let me solve it. I solved it by this method only. So 2 I am getting values are 4 volt and minus 1 volt. Minus 1 volt is possible? No. If V naught is minus 1 volt, what will happen? The MOS will be off only. If V naught is minus 1, the MOS will be off. Because VDS is negative. For transistor to turn on, what is the condition? That VDS should be greater than 0 and VGS should be greater than VT. These are the conditions, right? Two conditions are there. That this should happen. That's for sure. That this should happen. But if you are saying that your V naught is minus 1 volt, then your VDS is becoming lesser than 0. Then your transistor will be off. But that is not possible. Why it is not possible? Let's assume my transistor is off. Let's assume my V naught is minus 1 volt and let's assume my transistor is off. What will happen then? V naught by 2R will be equals to 100 micro. What will be the value of V naught? The value of V naught will be 200 micro into R. So 200 micro is 2 to the power 4 into R value is 40 to the power minus 4 into. So V naught value will came out to be 8. I am assuming if my transistor is off. Now people may have the doubt that sir, it can go into cutoff as well. Why it cannot go into cutoff? That I am explaining. If my transistor is off, what will be my V naught value? V naught value came out to be 8 volt. And if V naught is 8 volt, what will be VDS? It will be 8 volt. What will be VGS? VGS will be 4 volt. And what will be VT? VT will be 1 volt. So VDS is greater than VGS minus VT. So this will go into saturation only. If you assume your transistor to be in cutoff, we get it to be in saturation. Did you understand that it cannot go into cutoff? So I will write it down. I will certainly write it down. What I will write down? Let V naught is minus 1 volt. That is equals to VDS. That means MOS goes into cutoff. And for now, let's assume that cutoff is an possibility because we haven't checked. We have not checked that cutoff cannot be one of the possibility. Here we eradicated the possibility of being in saturation region in these kind of questions. So here we eradicated those possibility. Why so? Because we have already checked that it cannot be in saturation region. But here V naught is becoming to be minus 1 volt. So there can be possibility that it can be in cutoff. There can be one of the possibility that it can be in cutoff region. So we have to check now. So check. I am writing check. We are checking. If MOS is in cutoff, यार ये पेन का क्या हो गया है? MOS is in cutoff, then what will happen? ID will become 0 ampere. Then V naught by 2R will be 100 micro. So from here V naught will be 8 volt. V naught is 8. V overdrive would be V naught by 2 minus Vt. That will be 3 volt. So here V naught is greater than V overdrive. Also this is V naught, and what is VGS? VGS will be 4 volt. Also VGS is greater than Vt, and also VDS is greater than 0 volts. By all these three conditions, MOS goes into saturation. So cannot be in cutoff. So here we checked that MOS cannot be in cutoff. Now we will take the second answer, that is 4 volt. Now we will take the second answer. So if V naught is 4 volt, if V naught is 4 volt, V naught is 4 volt, that means VDS will be 4 volt only, because V naught and VDS are equal only. What will be your VGS? VGS will be 4 by 2, 2 volt. What is your VT? That is 1 volt. So what will be your V overdrive? That will be 1 volt only. So here, what is the condition? That your VDS is greater than V overdrive. That means it is in saturation region only. Initially I thought it can be in linear, but it is in saturation region only. So the assumption is correct. Assumption correct. And if the assumption is correct, so V naught will be 4 volt. So this is the answer. What did they ask? They asked the value of V naught or ID, or find the bias current. So V naught will be 4 volt. What will be the bias current? ID value they are asking. ID value. So ID is 100 micro minus 12.5 micro into V naught. That will be 50 micro, because 12.5 into 4 is 50. So ID value will be 50 micro. That's it. Or after getting the V naught value or VGS value, you can find it by the expression as well. This expression, ID equals to mu n CUX W by 12. So mu n CUX W by 12 will be 50 micro only. 50 micro into VGS minus VT. VGS is 2, VT is 1. So from here also you will get 50 micro answer. Or by that equation also you can get, right? So very easy, well and good. I hope you have understood all the problems. And why did I take this exercise? That also you must have understood, because here my main task was to make you understand that how do you find the DC parameter, VGS, VDS, VGS minus VT, all those stuffs. How do you get to know about the region of operation? And if you know the region of operation, how to apply the current equation? Then this is how we find. And then we will bias the transistor in a particular region. So all these transistors were biased. What do you mean by biased? Giving a DC supply, that's it. Here you are giving a DC supply 6 volt to the transistor. So all these transistors were biased. So once we bias the transistor, then we will use it in amplifier. Then we will amplify the input signal. Which signal we will amplify, how we will amplify, that we will study. But why did I take this example? Why did I take this exercise? So that you could know how to bias the transistor, then how to determine the region of operation. So that's how we determine the region of operation. The same thing will be happening in BJT as well. So same thing we will study in BJT. So these kind of questions are asked in the examination. So I hope you have understood. So let's meet in the next video. Okay, thank you. Hi everyone. So till now we have seen most physics. We have seen the internal structure. We have seen the current equations. We have seen saturation region, triode region, and the current equation. We have also seen how to find the region of operation. So these kind of question we have seen. In the previous assignment, what did we show? We had some particular configuration given and there were some DC bias there. It could be voltage, it could be current. So there was some DC bias. And based on that, we were finding the region of operation. So what do you mean by bias? Bias means simply applying some DC. It can be voltage or it can be current. So this is what we have written. The process of setting DC operating voltage or current condition to the correct level so that an AC input signal can be amplified correctly by the transistor. So what do you mean by AC input signal that can be amplified? That we will see. But the meaning of biasing is just giving a particular DC supply. It could be a voltage, it could be a current. So let's assume this is my transistor. So I am giving a particular voltage supply to it. Some VDD I am giving. And then this VDD can drive some current that I can call ID. So I am giving some voltage supply. In the previous question, we could see 5 volt, 10 volt, 100 microampere current. So the some supply we are giving. That's it. Now, why is it necessary to give the supply? Why cannot I run the transistor without even giving the supply? So why I needed the MOSFET? In the first lecture, when I started MOSFET, I told you why I needed the MOSFET. Why I needed MOSFET? To amplify my signal. Let's assume I am applying some voltage here, 20 millivolts sin omega t. I needed to amplify it. So let's assume in output I am getting some 100 millivolts sin omega t. So this is why I needed it, so that it can amplify my input signal. One more thing I would like to tell you, here we will always amplify small signal only. We can't amplify large signal. What do I mean by small signal? Small signal means the amplitude is small. I cannot amplify large signal. Let's talk about this this mic. The same example I gave you when we were studying diode circuit. So let's talk about this mic. This mic has two things. One is the DC bias, which it is getting from this laptop. Some DC voltage it is getting. That is helping for this microphone to turn on. उस DC bias से microphone turn हो जाएगा. Then there is this voice input. I am giving some voice input here, and then this voice input is being amplified. So this particular microphone is getting two inputs. One is the bias, one is the DC bias, and the other one is my voice. That is a small signal. The bias, it might be getting 2 volt, 0.8 volt, 0.5 volt. Then there is my signal. So all these signals which needs to be amplified are small signal only. It has amplitude 20 millivolt or 40 millivolt. So all those signals are small signal. It cannot happen that I can apply 2 sin omega t and then I will amplify it. No. This much of large signal cannot be there. So that's why they ask you in the question that find the small signal voltage gain. That means small signal input is applied. Some people confuse it with frequency. It has nothing to do with the frequency. The only meaning is the amplitude is small. So this is why I needed my transistor. Let's assume I apply 20 millivolt and then I get 100 millivolt sin omega t. So that was the reason why I needed my transistor. Now what if I don't even apply the DC bias? I only apply the small signal. So what was my small signal? What if I apply only small signal? There is no DC bias. I am telling you the reason why I need DC bias. So what if I don't apply any DC bias, only I apply small signal? What will happen? In this case, what is the value of VGS? Here, in this case, what is the value of VGS? VGS turns out to be 20 millivolt sin omega t. So maximum value of VGS is 20 millivolt and minimum value of VGS is minus 20 millivolt. Let's plot ID versus VGS. VT will be some 0.5 or 0.7 or 1 volt. Let's assume my VT is 1 volt. VT cannot be so small, 0.02. 20 millivolt cannot be VT. VT will be 1 volt, 0.5 volt, 0.7 volt. At least this much value will be there. Where will be this 20 millivolt? It will be somewhere here, right? Or more nearer, but somewhere here. This 20 millivolt will be in this range. Tell me, will the transistor turn on? Your VGS value is so small that transistor is not even turning on. That's why you need to give the DC bias. Are you getting this point? Transistor लैग कर रहा है यार थोड़ा सा. Transistor doesn't even turn on. Okay, let me refresh it once, then I will start the video. Yeah, so I was saying that transistor doesn't even turn on. So to turn on the transistor, we have to give that DC bias, and then on that we can superimpose or we can apply the small signal. Are you getting this point? We did the same thing in the diode circuit as well. What did we do in the diode circuit? In the diode circuit, first we turned on the diode. We had two signal here. One was DC and then the other one was, this was the DC and then we had applied some AC. So what this DC signal was doing, it was turning on the diode, and then what this AC signal was doing, if the diode is turned on, then based on the diode current, we were getting a small signal resistance, that was neta Vt upon I diode. So in the small signal AC analysis, we were replacing this diode with the small signal resistance. That's it. This is what we were doing when we were studying the diode circuit. It is again lagging. Okay. Yeah. So here also we are doing the same thing. We are applying a DC signal that will make sure that our transistor is turned on, or in whatever region we want it to operate. It can be linear region, it can be saturation region. That we will learn in the future, that my transistor is turned on. So in what region I would want it to operate, linear or saturation. So that we will learn in the further part of the video. So here my primary target is to turn on the diode, not the diode, the transistor. So my primary target is to turn on the transistor. So for that I will give a DC bias, this VGG, and then a small signal voltage. So VGS would be DC bias plus the small signal voltage, that is 20 millivolts sin omega t. Now since this is a small signal voltage, you will not have to worry whether it may turn off my transistor. What I mean to say, let's assume if it was large, let's assume the DC signal I gave is 2 volt, okay, and the signal, the AC signal that I am applying is 1.5 sin omega t, and value of Vt of my transistor is 1 volt. Then what will happen? The minimum value it can attain is minus 1.5. So 2 minus 1.5. At some value you will get your input voltage to be 0.5 volt. So your transistor may get turned off. But since this is a small signal voltage, 20 millivolt is a small signal voltage, the region of operation will not change, because there will be a very small change. There will be a very small change in VGS. What that change will be? Very small change. That will be, maximum voltage will be 2 plus 20 millivolt, that would be 2.0 02 or 002. 002 will be 2 millivolt only, so yeah, 02, and minimum would be 1.98. So that is very near to 2 only, 2.02 and 1.98, very near to 2 only. So your operating condition will not change. Your operating condition will be the same. If it is running in saturation, it will be in saturation only. If it is running in linear, it will be in linear only. So that's why the applied input, the applied AC signal that we want to amplify, that is small. So we can draw it like, how will my VGS look like? So my VGS will be simply a DC plus a small signal. This will be my VGS. Versus time we are drawing. So this is the DC, that is 2 volt. 2 volt I can show here. 2 volt plus 2 volt plus the AC signal. That is imposed on it. So this point will be 2 plus 20 millivolt, and this point will be 2 minus 20 millivolt. So it will not change the operating condition. Let's see it in one more graph. We will see it in the ID versus VGS graph. So this is our ID versus VGS transfer characteristic. I am assuming my Vt voltage to be 1 volt. So where will be my operating condition? This is my operating condition. I am running it at 2 volt plus 20 sin omega t, 20 millivolt sin omega t. So this is my operating condition. So my operating condition will be somewhere here. Let's assume this is my operating condition. Let's assume this is 2 volt. So what this point will be? Although it will be very nearer, but to show you in the graph, I will make it far away. So this I am thinking this will be 2 plus 20 millivolt, and this will be 2 minus 20 millivolt. So I don't need to write it down. So this is 2, this point will be 2 plus 20 millivolt, and this point will be 2 minus 20 millivolt. So basically, what is my signal? My signal is something like this. My signal is 2 plus 20 and 2 minus 20 and sinusoid. So my signal is something like this only. This is my signal. बन जा भाई सही से. VGS is the input. Input I am applying 2 plus 20 and 2 minus 20. That's why I showed it like this. It is my input only. And with respect to this input, what I am getting at the output. Let's assume if my input was 3 volt. So with respect to 3 volt, this was the ID I was getting. Right? If my input is 2 volt, with respect to this 2 volt, what ID I will get? With respect to this 2 volt, what ID I will get? This ID I will get. This ID I will get. If my input is 2 minus 20 millivolt, with respect to that input, what ID I will get? This ID I will get. And if my input is 2 plus 20 millivolt, what ID I will get? This ID I will get. Are you getting this point? So at 2 volt, this ID I am getting. At 2 plus 20, this is 2 plus 20, this ID I am getting. At 2 minus 20, this ID I am getting. So this kind of waveform I am getting. I can make a better waveform here. So when you apply this sinusoid input, with respect to that input, you are getting this output. Are you getting this point? So this was the case when my VGS is 2 plus sine omega 20 millivolts sine omega t. When my VGS is, I will apply two kind of VGS. First one I am applying 2 plus V in, small signal voltage. Now the second VGS I will apply is 4 plus V in. Now I am taking VGS value to be 4. So my DC bias is 4. So it could be somewhere here, could be somewhere here, and then plus minus 20, plus minus 20, minus 20 and plus 20. थोड़ा और आगे बनाना पड़ेगा. Gap should be similar, no? Gap is the similar now. This is 4 volt. Here this is 4 plus 20, here this is 4 minus 20. So this is my input. With respect to this input, what I am getting? What output I am getting? When you apply this input, this is the output you are getting. Output is very much amplified. You can see it, right? This was your input, output is very much amplified. Here this range is same, that is 40 millivolt. This is same, but here the amplification was this much. Here the amplification is this much. Here your magnitude has increased. So what did you see here? When the slope is higher, at this point this was the slope. The graph is going something like this, like this. The slope is continuously increasing. So the point where the slope is higher, you are getting more current in the output. And if there is more current, that means there will be more gain. Why so? Because this is your MOS. Let's assume this is your MOS. And this is the VGS. And then you have a ID. And this is your load RL. And let's assume you are collecting your output here. Based on your VGS, you are getting more current. If you are getting more current, that means there will be more voltage drop across RL. If the current is more, there will be more voltage drop across RL. That means the V0 value will be larger. If V0 value is larger, that means there will be more gain. That's it. If V0 value is larger, that means there will be more gain. If V0 value is low, the gain is low. So more ID, that means more gain. So when your slope is higher at the point, this point, when your slope is higher, your gain is more. So here I can write del ID by del VGS at what point? At VGS 2 is higher than del ID upon del VGS at point VGS 1. So I got to know that in this case I will get more gain. In this case I will get more gain. Here I am getting more gain. So now this parameter becomes an important parameter, that is output current divided by input voltage. Now this is an important parameter for us. So let's revise what we have studied in this lecture till now. So first we started with what do you mean by biasing, giving a DC supply. Why do we need the biasing? If we only apply the small signal voltage, what will happen? The transistor will not even turn on. So to turn on the transistor, we will apply a DC bias. Now after DC biasing, we will superimpose the small signal input voltage. If we are after superimposing the small signal input voltage, it will not affect the region of operation. Why so? Because the limit is very small, 2 plus 20, 2 minus 20, very small range it is. So it will not affect the region of operation. Now then we saw that in graph we saw that if we are giving the DC bias to be 2 volt, then the amplification we are getting is this much. If we are giving the DC supply to be 4 volt, then this much amplification we are giving. So at the higher VGS, we are getting more amplification. That means when the slope is higher, we will get more amplification. Now at 6 volt, there will be higher slope, so we will get more amplification. So what do you think here? Now what do you think? That we should keep VGS value to be very high. What do you think? Here, by seeing this graph until now, what you will think that we should keep VGS value as high as we can, because at higher VGS we will have more slope, and if there is more slope, that means there will be more gain, and this is what we want. So we should keep VGS value to be very high, but this is not the case. We have to find an optimum value of VGS, not very high. What will happen if VGS value is very high? First thing, more power consumption. Power consumption will be more. If VGS is very high, that means you have to give more supply from your side. Let's assume VGS is 10 volt, so you have to give at least 10 volt from your side. So this much voltage you will give, that will eat up more power, and who knows, your chip cannot take this much of power. When you are designing chip, on chip there are transistors only, there will be these kind of MOS only, and you have to give them bias. You have to bias all those transistors. So if you bias all those transistors at too much of high voltage, let's assume at 10 voltage, then your chip may burn out. So you cannot give very high voltage. This is the first thing. The second thing is that we will study later on. When we study the amplifier, then we will study that while operating the MOSFET in an amplifier region, while operating the MOSFET as an amplifier, we have to bias the MOSFET in saturation region. What did I say? When you are operating the MOSFET as an amplifier, you have to bias the MOSFET in saturation region, not in linear region. First thing is that you are operating it as an amplifier, so it has to be turned on. It cannot be in cutoff, it has to be turned on. If it is turned on, then there are two possible regions, linear and saturation. So you do not bias it in linear, you bias it in saturation. Why so? The region we will see later on. Why do we bias in saturation region? The region we will see later on. Now the thing is, if I keep on increasing my VGS value, what will happen? If I am increasing my VGS value, what will happen? V overdrive will increase. If V overdrive increases, that means VDS will be lesser than V overdrive. That it will go out of saturation. If I keep on increasing my VGS, my V overdrive will increase. If my V overdrive will increase, that means my transistor will fall out of saturation, because V overdrive is increasing and VDS is small only. So if VDS is small and V overdrive is keep on increasing, so my transistor will fall out of saturation region and I cannot operate it as an amplifier. So when you are operating the MOSFET as an amplifier, you have to make sure that the VGS value cannot be too large. First thing is the power consumption. If it is very large, there will be more power consumption, and second thing is your transistor may fall out of saturation. The region I explained, and now I will just write down the region. Okay, I will just write down why I cannot keep VGS value to be very high. We will try VGS keep value to be high. We will try to keep VGS value to be high, but cannot keep very high. So this parameter becomes very important. Del ID upon del VGS. We will try to get as much del ID by del VGS as much we can. We need del ID by del VGS to be very high, right? So this I will write down. At higher VGS, you get higher value of ये सही से नहीं लगा हुआ क्या, लैग तो अभी भी कर रहा है ना. Get higher value of del ID by del VGS, and that eventually gives more gain. But while using MOS as an amplifier, you cannot keep VGS value, VGS DC I am writing, VGS DC value to be very high. Like you cannot keep from 2, 4, 6, you cannot keep 6, 7, 8. That much value you cannot keep. There are two regions, right? What are the two regions? Value to be very high. What are the regions? First is the Y. First is the more power consumption. Then, and what is the second region? Transistor MOS will fall out of saturation. And why do we need to keep it in saturation? That we will study in the further part of the lecture. In the next video or next to next video, we will see why do we need to bias it in saturation region. So this you have understood, right? Now this del ID upon del VGS is an important parameter, and we have given this parameter a name that is known as transconductance. So what is transconductance? That we show by GM. GM is the transconductance. So what is transconductance? The change in output current with respect to the change in input voltage. This is known as transconductance. I don't need to write the definition. I guess this is more than enough. The change in output current with respect to the change in input voltage. And writing एक बार चेक कर लेते हैं कैसी आ रही है. थोड़ी तो खराब आ रही है आज यार राइटिंग. ठीक है, थोड़ा लैग कर रहा है. I hope you people are fine with that. So the change in output current with respect to the change in input voltage, that is known as transconductance. And more GM, that means more current. More GM means more output current, and more output current, that means more gain. So let's consider an NMOS. This is an NMOS. So what will be the GM for this NMOS? What will be the GM? GM will be del ID upon del VGS. Make sure I am writing capital ID and capital VGS. What do you mean by that? Large signal. That means, if I am saying large signal, that means I am talking about DC. Small signal means small signal AC signal. And if I am saying large signal, that means I am talking about DC only. So GM is a DC parameter. GM is a DC parameter that can be found with the expression of del ID by del VGS. Output current divided by the input voltage. That's it. So for triode region, for triode means linear region only. So for linear region and saturation region, we can find the value of Gm. So for triode region, what is the value of ID? That is mu n Cox W by L VGS minus VT into VDS minus VDS square by 2. What will be the expression of Gm? Gm expression is only one. Always there is only one expression of Gm, that is output current by change in output current with respect to the change in input voltage. So del ID by del VGS. This is the Gm. So Gm would be del ID by del VGS. So you have to differentiate it with respect to VGS. Mu n Cox W by L. Now you will go inside. VDS is a constant one. VDS is a constant value only. Why it is constant? Because we are differentiating with respect to VGS. So only VDS will come. If you differentiate it with VGS, this will be 1 and VT will be 0. So 1 minus 0 into VDS, that would be VDS only. And when you differentiate it with VDS square, it will be 0 only. So simply your Gm for triode region, came out to be mu n Cox W by L into VDS. Many times students ignore this formula because this is not oftenly used, but they can ask you 1 or 2 marks of numerical kind of question from here. That they will ask you the Gm of triode region. Gm of saturation region is oftenly used. We will find it again and again, but this we don't use again and again. Only once or twice we will see it. So I will take a numerical example so that you remember it actually. Okay. So you have to remember it. Sometimes they can ask you question from triode region as well. They will just simply give the mu n Cox W by L value, they will give the VGS VT value, they will give the VDS value. Then they will say find the transconductance of this given configuration. Then blindly you will go for saturation region. No, first you need to check the region of operation. If you go to know that the region of operation is triode, then you have to apply this formula. The formula will change. The formula for transconductance in saturation region will be different. What that will be? Let's check that. This is transconductance for triode region. Transconductance for linear region I did not write. Okay. So in the next page I am going to write transconductance for saturation region. Transconductance for saturation region. What that will be? Simply write the expression. What is the expression of saturation region current? Mu n Cox W by L VGS minus VT whole square by 2, right? Now if you, what is the expression of Gm? That is del ID upon del VGS. That's it. Output current divided by input voltage. So what will be the expression of Gm here? Del ID by del VGS, that would be mu n Cox W by L, because this 2 will come ahead. So 2 and 2 will get cancelled, VGS minus VT. I hope you know how to take the differentiation, right? So this will be the expression of Gm for saturation region, which is very important. We will use it again and again, but this also you need to remember. This also you will remember. Well and good. You will certainly remember, right? Because this is also very important one. Yeah. So this we have found. Now Gm versus VGS curve, that this we are drawing for saturation region. For saturation region. Just a second, is lagging too much. Just a second. Yeah, so Gm versus VGS graph we were drawing. So for saturation region we are drawing. For saturation region. So what is the expression in saturation region? Mu n C x some constant value Vgs minus Vt. So after Vt it will start. Before Vt the Gm will be 0. Why so? Because current will be 0. When Vgs value is lower than Vt, the current will be 0. So there is no meaning of Gm. It will be 0. After that linear expression is there. But in reality this is not the graph. In reality the graph is different, and that we will study very in depth but in EDC. That is important for EC guys only. This is not important even for placements. They will not ask you GM versus VGS graph. When we study EDC, I will tell you very in depth for linear region as well, for saturation region as well, how the graph goes something like this. Something like this. So we will study in depth how it goes like this, why it goes like this. So for linear region as well, for saturation region as well, we will study the in-depth concept of transconductance. Even the current expression will change. Something different will be happening, but this is not that much important for circuit analysis part. For circuit analysis part, this is just a graph I made in front of you, so that if anyone asks you what is GM versus VGS, then you can roughly make something. You can tell him those expression, because these expression will be used. But for circuit analysis part, this graph is not important. I just drew it here. When we study device physics, we will study very in depth about it. And electrical guys need not to worry that what will happen if someone asks us this. They are not going to ask you these questions, because that is in depth analysis of device physics. So yeah, just here I drew it. No need to worry about it. Just remember these two things. GM for triode. What is GM? The change in output current with respect to the change in input voltage. What is the expression for triode region? You don't need to mug it up. You can derive it even in your brain. Okay, the current equation I know. You just need to differentiate it with respect to VGS. I never mug up this formula. I just derive it there only, because one step it will take. That's it. Del ID by del VGS, so mu n Cx W by L into VTS. And what about this? That is mu n Cx W by 2L W by L VGS minus VT. Now this is one formula. I told you saturation region is important. So for saturation region, we will write two more formulas. That we will derive from this formula only. This formula we have got del ID by del VGS, that is mu n Cx W by L VGS minus VT. But we will derive two more formulas, because that is important part. You can at any time you need to use any formula. So we will derive two more formulas. So how we will derive that? So what you can see from equation 1, let's just call this as equation 2. From equation 1, what if I do something like this? From equation 1, what do? I will take this 2 here, and one of VGS minus VT downward. There are two VGS minus VT, no? VGS minus VT into VGS minus VT. So I will bring one more VGS minus VT downward. So 2ID divided by VGS minus VT. If I do this, what I will have in the right hand side? What that will have? Mu n Cux W by L VGS minus VT. Isn't it GM only? This expression, this particular expression, isn't it GM only? Yeah. Why did I do that? So that I could make the expression of GM from here. Isn't it equal to GM only? So one more formula I got for GM. What is that? 2ID by VGS minus VT. I will recommend you to remember this formula. I will recommend remembering this formula, because a lot of times we use it. 2ID upon VGS minus VT. Okay, so this is the second formula. This is also very important. One more formula we can get. Again, let's write down the expression of ID. ID expression is mu n Cux W by 2L VGS minus VT whole square. I will multiply mu n Cux W by L on the both of the side. Mu n Cux W by L on both of the side I am applying. Into ID, here also I will apply. Mu n Cux W by L. It will be the whole square, right? Mu n Cux W by L, it will be the whole square. Into 1 by 2, this 2 is here. VGS minus VT whole square. I can bring this 2 here, right? So I will remove it off from here. This 2 I have removed it from here and I have brought it here. And this I will take near. So what do you get? This square, this complete expression is a square, so I can take under root on the other side. So from here what do I get? Under root 2 into mu n cux w by L into ID, that is equals to mu n cux w by L VGS minus VT. And what is this expression is equals to? Mu n cx w by L VGS minus VT. Mu n cx w by L VGS minus VT is equals to GM. So one more formula of GM I am getting. Again I am recommending to remember it. 2 into mu n cx w by L ID. That's it. Can you remember this? I hope you can remember these 3 formulas, which are very important. Why we are writing these 3 formulas? Because we are going to use MOSFET in saturation region for amplification, and GM is a very important parameter. So we are checking all the possible conditions. One of the expression is this, one more expression is this, and the most common expression is this. At any time you may need to use any formula, so you should be ready for that, right? What if in the question they have given only mu n cux w by L and ID value? You have mu n cux w by L value and ID value. From there you can find the GM expression. What if in the question you have ID and VGS value only, or VT value? From there also you can find the value of GM. What if in the question you have mu n cux w by L value and VGS VT value? From there you can find the value of GM as well. So there are multiple ways of finding GM values for saturation region only. For triode region, this is the formula. Only one formula is there for triode region. Well and good. Understanding this concept, let's move on to the next one. So why did we find this GM? Because higher GM means higher gain. Higher GM means del ID by del VGS is higher, that means slope is higher, that means higher gain. But we cannot keep on increasing the slope because we may fall out of saturation, or there will be more power consumption, right? So this much we have seen. After that we should start studying the biasing. Now we will see how to bias the circuit, how much bias we can apply, how to bias the circuit, like where I should give the 5-volt voltage source, where I should give the current source, that we will study. But before that I will give one more important concept and some questions we will solve. So these are the questions given in front of you. There are 2 questions. You have to find the transconductance. So M1 and M2 are identical. M1 and M2 are identical MOS with transconductance GM. Both are having GM transconductance. M1, M2, I did not even show. This is M1, this is M2. Both are having GM transconductance. So what do you mean by that? And what do you mean by this line, this dotted line? That means this Vin and Vin are shorted. Both of the transistors are having same input voltage. That's it. This dotted line means at gate you are having Vin, and here also at gate you are having Vin only. This is what this dotted line means. They could have shown it this way as well. They could have shown it like this. But in many questions you will find these dotted line as well. If they had shown like this, then you could have simply understood, okay, Vin is going in this transistor as well, Vin is there at M1 as well, Vin will be going to the M2 as well. But they can show it by dot as well. If they are showing by dot, what does that mean? That both of the transistor is having Vin voltage at the gate. You need to find transconductance of the overall configuration. So this is your overall configuration. That's it. So for your overall configuration, let's make it smaller. This is your overall configuration. So for your overall configuration, what is the input? Vin. What is the output current? I out. That's it. So what will be the overall GM? Overall GM. Overall transconductance. That we can say capital GM I am writing. That would be del I out upon del Vin. So this is what you need to find. That's it. This is your target. You need to find del I out by del Vin. Now GM of this transistor is given, GM of this transistor is also given. So अरे space ही नहीं छोड़ा मैंने. For transistor M1, for M1, what will be the GM? GM will be this current which is not given. Let's assume I call this I1 and this current I call I2. The current in M1 is I1, the current in M2 is I2. So what will be GM? That would be del I1 by del V in, right? And for M2, what will be GM? Del I2 by input is the same only, del V in. Now what is your capital GM? Capital GM is del I out by del V in. But one thing you can see is that, what you can see? That your I out is equals to I1 plus I2. Say yes or no. I out is equals to I1 plus I2. I out is equals to I1 plus I2. This is the output current, which is the addition of these two current. And based on that, I could find the value of GM. GM is del I1 by del V in, del I2 by del V in. So I can simply replace this del I out with I1 plus I2. What do you get from here? Del I1 by del V in plus del I2 by del V in. What is del I1 by del V in? That is GM. And what is del I2 by del V in? That is also GM. So overall GM will be twice. That's it. Here the overall GM is twice. When we connected them in parallel, the overall GM became twice. What did I do? First I found out the value of GM. That I found out. Then here also again I found out the value of GM for M2 then M1. My first target would have been to find the final expression. What do I need to find? What do I need to find? Del I out by del V in. This is what I need to find. Then I could see that in M1 transistor my GM is del I1 by del V in, and in my M2 transistor my GM is del I2 by del V in, and I out is the combined expression of I1 and I2. So I out is I1 plus I2. So basically del I1 plus I2. So del I1 by del V in plus del I2 by del V in. So GM plus GM 2 GM. That's it. That's my answer. So many people confuse it with very complex analysis, like they introduce in MOSFET amplifiers and all those things. But this is not related to MOSFET amplifier. We haven't even studied MOSFET amplifiers. Still, we are able to solve these kind of problems. So it's not related to MOSFET amplifier. There is only one simple expression for transconductance. That is output current by input voltage. Change in output current by change in input voltage. Tell me the answer of this question, this particular question. What will be your overall GM? For this whole expression, this is the DC bias, right? So overall GM is del I out by del V in. Overall GM, overall transconductance. Change in output current divided by change in input voltage, that is this. This is your capital GM. Tell me what is the expression of GM1? The transconductance of M1 and M2 is GM1 and GM2 respectively. So what is GM1? What is GM1? What is that output current for transistor M1? What is the output current for transistor M1? That is del I out. What is the input voltage for transistor M1? That is del V. Isn't it the same as capital GM? That's your answer. That's it. What do you need to find? The overall transconductance. No matter how many transistors you add up, you can add up M3, M4, M5, M6, M7, but the input is applied to M1 only. And the same current will be flowing in all the transistors because they are in series. Let's assume I keep on adding up transistor. These all are transistor. I keep on adding up M3, M4, M2, M4, M5. But the final input is applied to this transistor only, and the same current is flowing. So overall transistor would be output current divided by input voltage, and the same transconductance will be there for M1 as well. Why so? Because it has the same output current and it has the same input. So your GM is small GM1 only. That's it. So this is your answer. Did you understand it? No need to confuse yourself when you see these kind of question. Just write down the simple expression that I have taught. What I have taught will be more than enough for you in the examination, in any interview. Just you need to believe in yourself. You just need to write the expression. What is the expression of transconductance? Change in output current with respect to the change in input voltage, del I out by del V in. And what is the transconductance for M1? M1 has the same transconductance, that is output current is I out only, input voltage is V in only. So it would be GM1 only. That's it. So these two questions we have solved. Now we will see one more important parameter. This is not the concept, it is a parameter, that is output resistance. What is an output resistance? If I am asking you find output resistance, if I am asking you find output resistance, what do you do? I give you a network and I am asking you find output resistance. So here what you will do, you will apply a voltage and get the current out of it. That's it, right? In case of MOSFET, what is our output? Input is VGS, output is VDS. So from VDS, how much current is coming? That will give the resistance. That we call output resistance. So from VDS, how much ID is coming? So del VDS by del ID will give us resistance. And this is the characteristics that we have studied. For linear, it will rise like this, and this one is for saturation. Saturation, right? Saturation, linear and saturation. And saturation we studied about two things. One is the ideal, when your channel length parameter lambda is 0, and one is practical, when your lambda is infinity. We also found out the value of RDS when we studied MOS physics. When we studied the MOS physics, do you remember we found out the value of RDS? When we were studying channel length modulation, we found out the value of RDS in saturation region. What was the expression, if you remember? That was 1 upon lambda ID for practical case, and for ideal case, R naught was infinity. Do you remember it? For practical case, the expression was 1 upon lambda ID. If you don't remember, I will make you recall. So this was the ID saturation expression, right? This is the expression of ID saturation. So here, if I do 1 upon del ID by del VDS, what will happen? This is a constant expression, and 1 plus lambda VDS. So you are just differentiating it with respect to VDS. So what will remember? Only lambda will remember. Are you able to understand? So lambda will be there. So what will be your expression? Your expression of RDS would be 1 upon lambda ID saturation, but for ideal case, right? So this we have already derived when we were studying MOS physics. You can check out there. Very simple derivation is there. So this is the practical one. Practical one. What is the RDS for practical? That is 1 upon lambda ID sat ideal. So lambda will be value will be given to you in the question. Then you can find out the value of RDS. How will you find out? Because you have the value of lambda, you can find the ID saturation. But in ideal case, what is the expression of this? That is mu n Cx W by L. This will not be there. This is eradicated. I am asking you to write the ID saturation in the ideal case. In ideal case, lambda will be 0. If you just differentiate it, what will happen? If you just differentiate it, del ID by del VDS, what you will get? Mu n Cx W by L VGS minus VT square into lambda. That's it. Now what is this? ID saturation in ideal case. So that will be lambda into ID saturation in ideal case. So just the inverse we have to take, because RDS is del VDS by del ID. So inverse we have to take. So after taking the inverse, this is what we are getting. And in case of ideal case, what do you get? You get it to be infinity, right? In case of ideal case, you get RDS to be infinity. Why it is infinity? Because if you differentiate this expression with respect to VDS, what will be the answer? 0. Del ID by del VDS will be 0, because there is no expression of VDS for the ideal case. This is for ideal case. Ideal case. In the ideal case, there is no VDS involved. If there is no VDS involved, that means the expression will be 0 only, and if it is 0, the RDS will be infinity. So this is the story for saturation region. Practically it is 1 upon lambda ID, and ideally it is infinity. So MOS in saturation region. So MOS in saturation region, if you are seeing from this terminal, so MOS in saturation region can be replaced with the simple current source. Simple current source, but with the output resistance of RDS. With the output resistance of RDS that has a value of 1 upon lambda ID sat, but ideal case. Current source, constant current source. This is for practical scenario. And what is the same for ideal scenario? It will simply be replaced with the current source only. This when we are seeing from drain to source terminal. If you are seeing from drain to source terminal, then only you can replace it with the current source. It's not that if I am seeing from here, I will replace it with the current source. No. From here it is not a current source. From output it is a current source. From output it acts like the current source, not from the input side. Well and good. So from output it is acting like a, from output it acts like a current source. So this is drain to source. Here this is also drain to source, and this is current source. Now people say that it is a constant current source. Yeah, this will be a constant current source, but only when VGS is constant. In some question your VGS will be varying. Let's assume my MOSFET is in saturation region. I am telling one of the statement, that is my MOSFET is in saturation region, that I am saying, but my VGS is varying. My VGS is varying, still the MOSFET is in saturation region. So what will happen to my current source? The current source value will also vary, right? The ID versus VGS plot we make. This is our ID versus VGS plot, right? ID versus VDS, sorry. ID versus VDS. So in this region we are working. So here we are saying that it is acting as a current source, but for a particular VGS only. What if my VGS is varying? What if my VGS is VGS2? So the value of current will be changed. Here the value of current is this. Here the value of current is this. So you can't say this will be a constant current source. This will be a current source depending on the value of VGS. That's it. In the saturation region, you can replace the MOSFET with the current source and the output resistance, but the current source will have a varying value with respect to VGS. If the VGS is constant, then the current source will be constant. Did you get this statement or not? So you can't directly say this statement is wrong, that in saturation region MOSFET is replaced with a constant current source. No, MOSFET is replaced with a constant current source only when VGS is constant. If the VGS is varying, even the current source will be varying. So in the saturation region, you can only replace the MOSFET with the current source. Now the value of current source depends on VGS. So I will be a function of VGS. This is what I will write. This I will be a function of VGS. This I will be a function of VGS. Okay, so saying that in MOSFET region, in saturation region, MOSFET is replaced with a constant current source, that is wrong. MOSFET is replaced with a current source. The value of that current source depends on the VGS value. That's it. Well and good. Now let's do the same thing for triode region. But triode region is very interesting. Why it is interesting? Let's check that out. So in triode region, actually there are two regions. One is the deep triode, other one is the sublinear. Let's check that out in the next page. This is nothing written, it is just the expression of triode region current is there. So let's study that triode region more deeply. This is your ID versus VDS plot. So when you draw the curve, there is always a curvature there. It's not that it rises like this and then this. There is a curvature. And what I was saying that in linear region, the current increases linearly. Here I can see that the current increases linearly. But is it happening by this expression? I am saying ID versus VDS is a linear expression. But is that so? See the current expression. In the current expression, there is a term of VDS square by 2. There is a term of VDS square by 2. So is that linear? No, this is not linear because there is a term of VDS square by 2. But when the value of VDS is low, when the value of VDS is low, that means in this particular region, when the value of VDS is low, we can assume this expression going towards 0. Are you getting this point? When the value of VDS is low, we can assume VDS square by 2 going towards 0, and that happens in deep triode region. So we call this region as deep triode region. Deep triode region, and this region is known as this one sublinear. This is not completely linear, this is sublinear. Here VDS square will be coming in action. Are you getting this point? Here VDS. So in deep triode region, what do you see? Del ID by del VDS is a straight line. For a resistance, if I plot V versus I curve, how will the curve look like? Voltage versus current. How will the curve look like? A straight line only. If voltage is increasing, that means current will also increase. So for a resistor, what happens? VI curve is linear. VI curve is linear. In MOSFET characteristic, what do we see? In deep triode region, there is a linear relation between output current and output voltage. So the expression is linear only. So in deep triode region, you can replace the MOSFET with the resistor from output terminal. And what will be the value of that resistor? That we can find by simple expression. So what will be your RDS? And we call it R on actually. We call it R on. The expression that we write, that we call R on, not RDS. RDS expression is given for saturation region only. So for linear region, we generally call it R on. So R on will be del VDS by del ID. That would be 1 by del VDS by, 1 by del ID by del VDS. Del VDS. I will put on the charger. Yeah. So R on is 1 by del ID upon del VDS. And for deep triode region, for deep triode region, what is the scene? VDS is very small. By the way, what do you mean by very small? So typically VDS should be lesser than 2 VGS minus VT. That is the typical value. ओके ये तो कुछ गड़बड़ लिख दिया मैंने लगता है. 2 VGS मैंने VGS minus VT मान लो 1 वोल्ट है तो VG ना this should not be the scene. It should be VGS minus VT by 2, right? VDS should be lesser than VGS minus VT by 2, because if VGS minus VT is 2 volt, yeah, So typically this is the scene. Typically, this is not a hard and fast rule. It is not any hard and fast rule. Okay, don't remember it. Okay, if it is lesser than that, you just need to compare. If you find that VDS value is typically small, this expression can go to 0, then you can take this as 0. Let's assume if VDS value is 0.1 only. If it is 0.1, what will be the square of that? 0.01. 0.01 by 2. That will be very low. That will be very low. So this can go to 0. So typically your VDS can go to 0. If VDS value is very small, so your VDS can typically go to nearly go to 0. So what will be the expression of ID? Expression of ID will be mu n Ux W by L VGS minus VT into VDS to VDS. So what will be del ID by del VDS? That would be mu n Cux W by L VGS minus VT. And what will be your R on? R on is typically 1 upon del ID by del VDS. That would be 1 upon mu n Cux W by L VGS minus VT. VGS minus VT. That's it. Again, you don't need to mug up this formula. You can derive it anytime. So there are many formulas in this particular video. This R on formula is there. Then one more formula we find. For RDS, these formulas are there, right? But you don't need to mug up anything. You just need to know the expression that okay, what is output resistance? Del VDS by del ID. You know the expression of ID. You can find it out in one expression only, or even in the brain you can think about it. Okay, del ID by del VDS. For saturation, I need to find in saturation region. It doesn't even depend on VDS. It will be infinity. If this is not the if this is not ideal case, okay, it is practical case, then there is channel length modulation. So lambda factor will be coming 1 upon lambda ID set. That's it. For this deep triode region, okay, deep triode region, VDS square will be going towards 0. So only mu n Cux WIL VGS minus VT will be remaining. So 1 upon mu n Cux WIL VGS minus VT will be my expression. For GM also I don't need to mug up the formula. For triode region, I can find, okay, for triode region, what is the expression of my GM? Del ID by del VGS. So expression will be mu n Cux WIL into VDS. That's it. For triode, deep triode, for every region. Here there is no meaning of triode or deep triode. For every region, this will be the formula only. Because here the differentiation is made with respect to VGS. So this expression and this expression are itself going towards 0 only. This one is going towards 1 and this one is going towards 0. So there is no meaning of triode or deep triode. The formula of GM will be the same for both of the region. And then when we talk about transconductance for saturation region, this is very important parameter. So for that we have to remember two formulas. This we can derive very quickly, mu n Cx W by L VGS minus VT. Then the other one is 2ID upon VGS minus VT. This I will keep in mind, 2ID upon VGS minus VT. And the other one is root 2 into mu n Cx W by L into ID. That's it. So these formulas I will remember. Root 2 into mu n Cx W by L ID. So these three formulas I will remember, and then I found out how to find the expression of GM just by the simple formula we have to go. Nothing, no concept of MOSFET amplifier used. Simple formula is there. Then we find out the output resistance. Okay, so this was the summary of this lecture. And one more thing I need to show, that is how will I show the MOSFET in saturation region. Like here I showed the MOSFET in saturation region, so here I will show the MOSFET in triode region. So MOS in triode region. So it will be replaced with the resistance. Gate, source, drain. So it will be replaced from drain to source side. It will be replaced with the resistance of R1. That's it. This is drain and this is source. Okay, in triode region. Triode region. Okay, not in triode region, in deep triode region. MOSFET in deep triode region. Deep triode region. In deep triode region, it will be replaced with RO. The form expression is here. 1 upon mu n W by L, P just minus Pt. I hope you have understood the complete lecture. By using all these things, whatever that we have studied in MOSFET till now, we have seen the MOS physics, then we saw some question. Now we have seen the important parameter. Like first we saw why do we need to bias, like understood why do we need to bias, so that the transistor turns on, then we can amplify it. When we saw the biasing, what did we saw there? We see that del ID by del VGS is a very important parameter. Higher the slope, more the gain. So at high value of VGS, you get higher slope. So then I found out the expression of del ID by del VGS for both of the region, for saturation and triode, and then we saw the output resistance. Output resistance is also an important parameter. When we study amplifier, it will be used there. So output resistance is also an important parameter. So we also studied about the output resistance. So that expression also we found out. Well and good, very easy. So let's move on to the next lecture. In the next lecture, we will see very important assignment. These kind of questions are not asked in GATE till now, but they can be, those questions can be asked any day. So in the next lecture, we will solve those assignments. We will solve those assignments. Okay, thank you. Hi everyone. So in this video, we are going to see assignment 5, and this assignment is fusion special. What do I mean by that? Fusion special, that means these questions are not that straightforward. If you are studying it for the first time, you cannot solve it by your own. You have to watch the solution, then only you should solve it. So those who have studied analog electronics before as well, they can try solving it on your own, but these are very good questions. In the GATE examination, these questions are not asked yet, but in the upcoming examination, these questions will certainly be asked. And in the interview also, these questions are asked. In the interview, they ask you the Vx versus Ix waveform, these kind of questions they ask. So in this video, we are going to solve around 9 to 10 questions. It will be a long video. It can be of around 2 hours, I guess. So around 9 to 10 questions we will see, and in each question you will learn something new. So have the patience, sit with notes and paper and pen, and then watch the solution. And once we are done with the question, try solving it on your own, then move to the next question. So these questions will build your concept to the next level. So we'll start one by one. So this is the first question. This question has 3 parts. You have to draw Vx versus Ix curve for this particular circuit. Your Vt value is given. This is your Ix value is given, and Vx value you are sweeping from 0 to 3 volts. Sweeping, that means I am increasing from 0 to 3 volt. And you need to plot Gm versus Vx curve as well. The definition of Gm is also given, that is del ID upon del Vgs. Same will be happening with this circuit, circuit B. Here also again Vx versus Ix, Vt value is given, Gm you also know. So Vx versus Ix and Gm versus Vx as well. Those you need to draw. This is the third circuit. Now this is a different kind of question. In this one, V in value is given. Again, we are sweeping V in value from 0 to 3 volt. You have to plot V naught versus V in now. Okay. In this question, Vx versus T, Ix versus T. Vx waveform with respect to time, Ix waveform with respect to time. Did I miss any question? No. Then this is the next one. Same question. This is the next one, and then this is the next one. Well and good. So we will solve it one by one. Don't be in a hurry. Have the patience and see the solutions. So you have to draw Vx versus Ix. This is the first circuit. I am drawing it on the next page. So this is our first circuit, circuit A. So tell me, what is the VDS value here? Since we need to write down the current equation, so I need to write down the value of VDS, VGS, VT, VO drive. Then I need to see in which region it is working, saturation or linear. If it is working in saturation region, the current equation will be different. If it is working in linear region, current equation will be different. So what is your VDS? VDS is 3 minus Vx. What is your VGS? That is also 3 minus Vx, because drain and gate are shorted. Drain and gate are shorted. What will be your VT? VT will be 0.7 volt. So what will be your VO drive? VO drive would be VGS minus VT. That would be 2.3 minus Vx. This is your VDS. This is your VO drive. What do you see here? Your VDS is always greater than VO drive. Always. Right? Always. Irrespective of the value of Vx, no matter how much you increase or decrease Vx, VDS will always be greater than VO drive. Do you agree with this point? Because what is VDS? It is 3 minus Vx. Let's just say Vx is 1. So what will be your VDS? 2. What will be your V overdrive? V overdrive is 2.3 minus Vx. If Vx is 1, V overdrive would be 1.3. So always 2 will be greater than 1.3. Simple mathematics is there. It will always be true, right? No issue with that. VDS is always greater than V overdrive. That means it will always be in saturation region. So one thing you understood here is that I will write down a separate note. That is, if gate and drain are shorted and drain are shorted. Shorted means they are at same potential. If drain and gate are shorted, the MOS will always be in saturation. MOS will always be in saturation, right? This is your NMOS. Drain and gate are shorted. Drain and gate are shorted. Drain and gate are shorted. So your VDS value will always be greater than VGS minus VT, because here VDS is equals to VGS. VDS is equals to VGS. Something is getting less from VGS. VDS is equals to VGS. Now if something is getting less here, that means this will be certainly greater. That's it. And similar thing will happen with NMOS as well. This is your NMOS. This is your NMOS. Now these are shorted. This is your gate and this is your drain. So here VSD, this is source, this is source. Here your VSD is always greater than VSG minus VT. VSD is greater than VSG minus VT, right? So it will always be in saturation. You have to remember this. If your if your gate and drain are shorted, the device will always work in saturation region. The region is simple. You can directly see it, because VDS will always be greater than V overdrive or VGS minus VT. Well and good. So this was the thing that we understood. So my device is working in saturation region. So what will be the equation of Ix? That would be some constant. That would be mu n CXWIL. So some constant. I just need to draw the graph. I don't need the values. I need to draw the graph. So some constant into VGS minus VT whole square. VGS minus VT is this 2.3 minus Vx whole square. So this will be my Ix equation versus Vx. So if my Vx increases, my Ix decreases, right? If my Vx increases, I am drawing Vx versus Ix. Sorry, Ix versus Vx, I should say. Ix versus Vx. So if Vx is 0, this is my Ix. Some k into 2.3 square. No need of values, you just need to draw the graph. Now if Vx is increasing, the Ix will decrease like this, right? Now tell me one thing, what will be this potential? When will the Ix current be 0? When Vx is 2.3 volt, right? When Vx is 2.3 volt. When Vx is greater than 2.3 volt, what will happen? When Vx is greater than 2.3 volt, what will happen? Your VGS would be less than 0.7 volt, right? What is your VGS? VGS is 3 minus Vx. If it is less than VT, what is VT? VT is 0.7. If it is less than VT, that means if Vx is less than 2.3 volt or greater than 2.3 volt, sorry, if Vx is greater than 2.3 volt, what will happen? The device will go into cutoff, right? So I will write it in better manner. So for cutoff, what is the condition for cutoff? That your VGS should be less than VT. What is your VGS? 3 minus Vx should be less than 0.7. That means your Vx is greater than 2.3 volt. So when Vx is greater than 2.3 volt, your ID will be equals to 0 ampere. Not ID, I can write Ix. Ix equals to 0 ampere. So till 2.3 volt it will decrease, and after that it will be 0 ampere always. Now people will say, sir, if I put Vx equals to 2.4 volt in this equation, then what will happen? Sir, the current would be K into 0.1 square. No, the current will be 0. The current will be 0 because this equation is valid only for Vx value 0 to 2.3. That's it. If your Vx value is greater than 2.3 volt, your Ix will always be 0. So this thing you need to keep in mind, and this thing you need to keep in mind. That if I increase further Vx, my Vgs value will be lesser than 0.7. If my Vgs value is lesser than 0.7, that means if my Vgs value is lesser than Vt, then my device will go into cutoff and the current will be 0. That's it. Right? Well and good. So this is the expression of Ix versus Vx we have drawn. Now talking about GM. Talking about GM. Device is always device, or I can write MOS. MOS is always in saturation. So what is the GM value for saturation? If you remember previously, we have studied it. What is the GM value for saturation? Some constant, I can call it K dash, some constant into Vgs minus Vt, right? Say yes or no. It will be mu n CX W by L Vgs minus Vt, right? This is the expression. So GM, what will be GM value? K dash into, what is Vgs? Vgs is, what is Vgs minus Vt? That is 2.3 minus Vx. That's it. 2.3 minus Vx. That's it. This is your GM. So GM versus Vx curve you can also draw. MOS is always in saturation for Vx equals to 0 to 2.3. For Vx value 0 to 2.3, then only it is in saturation. When Vx is greater than 2.3, what will happen? Ix will go to 0. If Ix is 0, then certainly GM will be 0. If there is no current, there is no meaning of GM, right? So certainly GM will be 0. So for Vx greater than 2.3, GM is 0. Otherwise, it is following this equation. We are going to draw GM versus Vx curve. If Vx is 0, then this is your GM. K dash into 2.3. And if Vx is 2.3 volt, you can put equal here as well, because at 2.3 as well it will become 0. So it is decreasing like this. After that it is going towards 0 till 3 volt. Well and good. That's it. Understood? So this is the curve. So what was this question? Everything was given. You got to know that device is working in saturation region. When it is working in saturation region, you could write the equation of current. It is working in saturation region for Vx value 0 to 2.3 volt. Then you could write the equation of current. You could draw the Ix versus Vx waveform. After that, you got to know that if Vx is greater than 2.3 volt, what is happening? The device is going into cutoff region. If it is going into cutoff region, then the current would be 0. That's it. And also, what did you understand? If your drain and gate are shorted, the device will always work in saturation region. Now, talking about GM formula we already know. Some constant into Vgs minus Vt. Why we are not considering about constant? Because we just need to draw the curve. That's it. Nothing else. So, constant into Vgs minus Vt. Vgs value we know 2.3. Vgs value is Vgs minus Vt value is equal to V overdrive only, that is 2.3 minus Vx. Then we could draw the curve, and if Vx is greater than 2.3 volt, the current would become 0, and if current becomes 0, then your GM would always be 0. So curve goes like this and then this. That's it. Say yes or no. Understood? Everything is clear? Let's move towards second question. This question is better than the previous one. So I will write down the values which are given. What was the values given? Vx you are sweeping from 0 to 3 volt. Vt value was 0.7 volt. That's it. Okay. Now what people will think if they are watching this question for the first time, what they will say, sir, here Vgs is equals to 1 minus 1.9 volt, that is equals to minus 0.9 volt, that is less than Vt. This shows that your Ix will always be 0 ampere. Now this line is completely wrong. Why so? This is completely wrong. Why so? I told you one thing. Source and drain are not absolute. this is what we are going to do. First we will see what kind of device is that. This is NMOS. If this is NMOS, that means drain will be at higher potential and source will be at lower potential. The one which is at higher potential, that will be drain. The one which is at lower potential, that will be source. And in case of PMOS, one which is at higher potential, that would be source, and one which is at lower potential, that would be drain. And current will always flow from high potential to low potential. That's it. This is what I told you to remember in the complete MOS physics. Some equations and this thing. This is a very, very important thing. A lot of teachers don't teach this thing, and in the examination, if they ask these kind of question, you will be messing it up. You are sweeping your Vx value from 0 to 3 volt. For 0 to, if your Vx value is from 0 to 1.9 volt, what will happen? If your Vx value is from 0 to 1.9 volt, this potential will be low, right? And this potential will be high. If your Vx value is between 0 to 1.9 volt, this will be low, this will be high. What will happen? This will act as a drain. This is at higher potential and this will act as source. Say yes or no. Okay, so let's write it down. I should not write it in the question itself. So what will happen is that this is your given circuit. So here Vx is at lower potential. Since this is at lower potential, and this is at higher potential. So this will become drain and this will become source. The current will be from drain to source, right? Current will be from drain to source. So you can show it something like this. This is your drain which is at 1.9 volt. So it will be from drain to source in this direction. The current will be from drain to source. Basically this has become your source. So it is looking like this only now. Just the opposite I have drawn. I have drawn it in this manner. This point is going here, this point is going here. That's it. Now this has become source. And this is your 1 volt. And your current will flow in this direction. Now can I write down the value of VDS, VGS and VT, all those things I can write. So what is the value of VDS now? VDS, drain to source, 1.9 minus Vx. What is the value of VGS? VGS, gate to source, that is 1 minus Vx. What is the value of VT? That was given is 0.7 volt. This is not PMOS, okay? In the initial phase, you can get confused. Sir, this is PMOS. No, no, no. In PMOS, this is the scene. In PMOS, what is the scene? This is the scene. And this is source there. Now I am drawing like arrow like this. Arrow is going outward. If the arrow is going outward, that means it is certainly NMOS. But the source has changed. Source is the upper one and drain is the lower one. This is not your IX, this is actually ID. This is actually ID. IX direction is always from Vx to 1.9. They have given the IX direction in the question itself. In the question itself, they have given the IX direction. That is from Vx to 1.9. Vx to 1.9. So this is IX. But first I will write down the value of ID. Then I will see what I need to do. And what will be your V overdrive? V overdrive would be 0.3 minus Vx. Till this point, everything is clear or not? First thing we saw there is that Vx value is increasing from 0 to 3 volt. Then we got to know that till 1.9 volt, it will be interchanged because the upper potential is low. That means that will act as source and 1.9 will act as drain. So current will flow from drain to source, higher potential to lower potential. So current will flow like this and that has become source. So VDS value is 1.9 minus Vx. VGS value is 1.9 1 minus Vx. VT already given and V overdrive is also there. What did you see here? That your VDS is greater than VGS minus VT. If you are getting confused with this diagram, you don't need to draw it. You just get to understand that, okay, this is source, this is drain. Then VDS I can write, VGS I can write, everything I can write. So here you can see is that your VDS is greater than VGS minus VT, which is V overdrive, VGS minus VT. That means it is also working in saturation region. But till what point it will work in saturation region? This is in saturation region. You always need to see cutoff region, when it will go into cutoff. For cutoff, your VGS should be less than VT. Your VGS should be less than VT, or I can say your VO drive should be less than 0. Say yes or no. What is VO drive? VGS minus VT only. VO drive is VGS minus VT. So VO drive should be less than 0. That means your Vx should be greater than 0.3. So for cutoff region, your Vx should be greater than 0.3 volt. Say yes or no. If Vx is greater than 0.3 volt, your device will go into cutoff. And this is all happening for 0 to 1.9 volt. So what did we get to know here is that for 0 to 0.3, your device is in saturation region. Your device is in saturation region. Here VDS is greater than VGS minus VT. So it is in saturation region. So what will be the expression of ID? Expression of ID I am writing. Expression of ID. Expression of ID would be K into VGS minus VT. That would be K into VGS minus VT 0.3 minus Vx whole square. This is your ID. But here you could see that the ID direction is from 1.9 to Vx. ID direction is 1.9 to Vx. But Ix direction is from Vx to 1.9. So Ix is negative of ID. So what will be your Ix? That would be minus K into 0.3 minus Vx whole square. This is your Ix. Now you need to plot. This is your Ix. And then one more thing you know is that for 0.3 to 1.9 volt, it is going into cutoff. If it is going into cutoff, that means your Ix is 0. Ix is 0 ampere. I can write down the value of Gm as well, right? I can write down the value of Gm as well. So here what will be the value of Gm? If current is 0, then Gm is certainly 0. Here what is Gm? Gm is always some constant K dash into VGS minus VT. Some constant into what is VGS? VGS is VGS minus VT. What is VGS minus VT? That is 0.3 minus Vx. That's it. This is your Gm. Any issue with that? Right? Yeah. So this was the expression of Gm. So Gm expression we have, I expression we have for 0 to 1.9 volt we have. So now we can draw the characteristics. So Ix versus Vx I am going to draw, and in the next I am going to draw Gm versus Vx. Ix, sorry, Ix versus Vx, and then this is Gm versus Vx. So if Vx is equals to 0, then your Ix is some negative value. If Vx equals to 0.3, it will go to 0. So it goes something like this, right? After 0.3, it is 0 only. The response is not linear, right? It follows the square equation. It follows the square equation. So quadratic like this, not linear. And till 1.9 we have concluded. After 1.9, what will happen? We will see it, because after 1.9 the drain and source will be interchanged. Here drain and source are like this. This is drain, this is source. After 1.9 that will be drain, that will be source. So we will analyze that, but till 1.9 we are drawing. This is 1.9 volt. So till 1.9 volt, this is what we have got. For Gm, what is the scene for Gm? At 0 it is some voltage, some value, that is K into K dash into 0.3, and at 0.3 it will be 0. At 0.3 volt it will be 0. And after that till 1.9 it remains 0 only. So this we have done till 1.9 volt. After 1.9 what happens, that we will check now. For Vx greater than 1.9 volt, what will happen now? This was your Vx given. this was your 1.9 volt given, and this was 1 volt. This will become higher potential. That means this will be drain, this will become lower potential, this will be source. What do you see here? And this is certainly gate only. There is no doubt in that. Gate is always fixed. This is gate, that is fixed. So what do you see here? What is your VGS here? 1 minus 1.9, that is minus 0.9, that is less than VT. MOS is off. And if MOS is off, then your IX is 0 ampere and your GM is also 0. That's it. So after 1.9, nothing changes. After 1.9, what did we get to know is that your IX is 0, so certainly your GM is also 0, because VGS value is minus 0.9, which is less than VT. So we can copy the same diagram for the final one. So what I am going to do, I am just going to increase the IX value, that's it, till 3 volt, which will be 0 only. And after in this one, for GM as well, I am going to increase it till 3 volt. It will always be 0. That's it. So when we saw this question for the first time, what did we understood? Vx and 1.9 will be interchanged. The upper one will be source, lower one will be drain, because that is at lower, drain is at higher potential, source is at lower potential. So 1.9 is the high, and till 1.9 volt Vx will be low. So the current direction will be in this direction now. So we could write down the value of VDS, VGS, VT, then I could write down the expression of current ID, and ID is equals to minus Ix. Then I could write down the expression of Ix as well. Then the GM formula I know, that is K, some constant into VGS minus VT. VGS minus VT I know, the constant value I don't need to bother about. So that would be 0.3 minus Vx. But I got to know that after Vx is greater than 0.3 volt, the device will be in cutoff. The current will be 0. If the current is 0, then GM will certainly be equals to 0. This we analyze till 1.9 volt. After 1.9 volt, what happens is that my VGS is less than VT. My VGS is minus 0.9. That is less than VT. So my IX and GM both will be 0. That's it. So this is the second question. Well and good. Let's move towards the third question. You have to solve it on your own. Now you can try doing it on your own. The same thing is happening. I will write it down. What is happening? Vx is sweeping from 0 to 3 volt. Vt value is given, that is 0.7 volt. Here it will be VTP, because since this is NMOS, sorry, PMOS. This is PMOS. You could directly see the arrow is inward. The arrow is inward, that would be PMOS. This is 0.7 volt. Well and good. Everything is crystal clear. Okay. Now you have to draw Vx versus Ix. In case of PMOS, which is at higher potential? Source is at higher potential, right? In case of PMOS, source is at higher potential. So what do you see? For Vx equals to 0 to 1.9 volt. What is happening? This is 1 volt. This is Vx, and this is 1.9 volt. This will be at higher potential. This will be at lower potential. If it is at lower potential, in case of PMOS, it will be drain. And this will be, since it is at higher potential, this will be source. Well and good. Everything is clear. What will be the direction of current from high potential to low potential? The direction of current will be this. Given Ix is this. Given Ix is this. But actual ID will be this. I don't need to draw the circuit. I can directly write down the VDS, VGS, all those values. What will be my VSG value? Why I am interested in VSG? Because I am talking about PMOS now. So what is my VSG? VSG, that would be 0.9 volt. Source to gate. What would be my VSD? VSD, that would be 1.9 minus Vx. What would be my V overdrive? That would be VSD minus VT. Sorry, VSG minus VT. Sorry. VSG minus VT. So 0.9 minus 0.7, that would be 0.2 volt. Everything is clear? Say yes or no. So what do you see here is that what is your VSD? So let's write down the condition. This is your VSD. VSD is depending on Vx. So your region of operation will also depend. Are you getting this point or not? Your VSD is depending on Vx. So your region of operation will also depend on Vx. How? For saturation, what do you need? Your VSD should be greater than V overdrive, right? What is your VSD? 1.9 minus Vx. That should be greater than V overdrive, that is 0.2 volt. So Vx should be less than 1.7 volt, right? Vx should be less than 1.7 volt. This you got to know. Other thing you got to know is that your V overdrive is always greater than 0. So MOS is always on. MOS is on. V overdrive is always greater than 0. So your MOS is always on. Here, what was the scene? Your V overdrive was depending on Vx. So if Vx was greater than 0.3, your MOS was getting off. Here your V overdrive is not depending on Vx. 40 to 1.9 volt. This we are considering only 40 to 1.9 volt. Forget about 3 volt anything. For 0 to 1.9 volt, your V overdrive is not depending on Vx. Your V overdrive is constant, that is 0.2 volt. That means MOS is always on. Now I got to know the condition for saturation. The condition for saturation is your Vx should be greater than 1.7. Then what do you understand by that? If your Vx is less than 1.7, then your device will be, if your Vx is less than 1.7, then your device should be in saturation region. This is given, this I derived. But if your Vx is greater than 1.7, what will happen? Your device will be in linear region till 1.9 volt. This we are talking about till 1.9 volt. Till 1.9 volt we have talked about. Say yes or no, everything is crystal clear. So for Vx less than 1.7 volt, what will happen? Vx less than 1.7 volt. What will be your ID? ID would be some constant into Vsg minus Vt whole square. So some constant into what is Vsg? Vsg minus Vt. So this will be Vsg minus Vt, 0.2 whole square. So ID is a constant current. And what is your Ix? Ix is negative of ID, right? Because ID is flowing from 1.9 to Vx. ID is flowing from 1.9 to Vx, but Ix is flowing from Vx to 1.9. Ix is flowing from Vx to 1.9. So ID is negative of Ix. So Ix would be minus K dash 0.2 whole square. So this will be your Ix voltage. This will be your Ix. So this we are talking for 1.7 till 1.7. Now what about GM? What will be your GM? So GM would be some constant. It could be anything. Some constant K I am writing. It could be any constant into Vsg minus Vt. What is the value of Vsg minus Vt? This is 0.2, right? This will be your GM. Say yes or no. Well and good. Yeah. So this I have written Ix and GM value for Vx less than 1.7 volt. Now for 1.9 to 1.7 volt. 1.9 to 1.7 volt. 1.9 to 1.9 to 1.7 volt I am going to write. So what will be your Ix? What will be your ID? Tell me. What will be your ID? Some constant. It can be any constant. I have to give different name. Some double I am writing. Some constant into Vsg minus Vt. Vsg minus Vt into Vsd minus Vsd square by 2. Some constant Vsg minus Vt. What is Vsg minus Vt? That is V overdrive into that would be 0.2 into Vsd. What will be your Vsd? That would be 1.9 into Vx. 1.9 minus Vx, sorry. This would be the equation, right? Now this is your ID. What will be your Ix? Sorry, this is your ID, and what will be your Ix? Ix will certainly be negative of this. That's it. Just the negative of this. This will be your Ix. Negative of ID. That's it. Now how will you draw it? correct expression is very much difficult, but we can do an approximate expression, right? Drawing the correct expression of this very much difficult, because here you have linear term as well as square term as well. You need to simplify it in a very great manner, then you need to differentiate it, then you can draw. But but intuitively we can also draw, that I will tell you when we draw the characteristics. First we are writing down the expressions, and what will be your GM? Do you remember the GM formula for triode region? GM formula for triode or linear region. Do you remember the formula? What was the formula? Some constant, then VGS minus VT get cancelled. Some constant into VDS, that's it. Some constant into VDS, right? This was the formula. Because the expression was mu n CoX W by L, VGS minus VT into VDS. Just you need to differentiate it with respect to VGS. So what you will get? This will be 1, only VDS, and this will be 0. So some constant into VDS. So some constant into VDS. Sorry, not VDS. If we are talking about PMOS, it would be VSD. So what is the value of VSD here? 1.9 minus Vx. So drawing this is not that much of task. This will be very easy. So this is your GM. So you have all the expression. Now you need to draw the curve. The curve we are going to draw only till 1.7. Sorry, 1.9. 0 to 1.9. So 0 to 1.9 we are going to draw. After 1.9 what will happen, that we will see. But till 1.9 we can draw. Vx versus Ix versus Vx and GM versus Vx. This is Ix versus Vx. And this is GM versus Vx. So Ix versus Vx till 1.7 volt. This is 1.7 volt. So till 1.7 volt, what is the expression of Ix? That is some constant value. This is constant, right? This is also a constant value. This k will be some negative, k will be some positive value only. Mu n CoX W by L, whatever the k is. So that will be some positive value only. In this case, it would be mu n CoX W by 2L, and in this case, k would be mu n CoX W by L. So that will be some positive value only. So complete value will be negative. So Ix is negative. Ix is negative. Some negative constant voltage. And till 1.7, this will be some positive voltage. This will be some positive voltage. Well and good. Now, after that, what happens? Look, after that, if Vx increases, then this value will decrease. This value will decrease, and this value will also decrease. Which value will decrease more? This is my question. If Vx increases, this value will decrease, and this value will also decrease. Which value will decrease more? Vx will increase from 1.7 to 1.9. Let's check that out. If your Vx is 1.8, what will be this value? 0.1. If your Vx is 1.8, what will be this value? 0.01 square by 2. Very less, right? Very less. If your Vx is 1.7, what will be this value? It will be 0.1 square by 2. I am really sorry. It would be 0.1 square by 2 if Vx is 1.8. So overall value will be 0.01 by 2. Very less. If your Vx is 1.7 volt, what will be this value? If Vx is 1.7 volt, this value will be 0.2 whole square by 2. So it would be 0.04 by 2. 0.02. This is also very less. You can ignore this factor. Here, this particular value is very less. For the range 1.7 to 1.9, you can simply ignore this factor. That's it. If you simply ignore this factor, what happens? If your Vx increases, the current magnitude decreases. The magnitude of current decreases, but since there is negative direction, negative sign, so it will go like this. At Vx equals to 1.9, what will be the current? At Vx equals to 1.9, this is 1.9, 1.9, the current will be 0. At Vx equals to 1.9, the current will be 0. So I know the current will go like this. The current will go like this from here to here, right? It will go nearly linear. Although this expression is also there, so it will not be completely linear, but nearly linear it would be. Nearly linear. Nearly linear. The word is complex. Okay? Are you getting this point? if your Vx is from 1.7 to 1.9 volt, what is happening is that if your Vx is increasing, your current magnitude is decreasing. Current magnitude is decreasing, but the current is in negative direction. So in positive direction, it would increase. And at 1.9 volt, the current would be 0. I know that at 1.9 volt, the current would be 0. So it will increase like this. And magnitude is decreasing. What is the magnitude here? Let's just say magnitude is 3 ampere. Let's just say magnitude is 3 ampere. After that, the magnitude will be 2 ampere. But actually, value is increasing. Minus 3 is less than minus 2. But the magnitude is decreasing. Are you getting this point? So magnitude is decreasing. And nearly linear it will go, but not completely linear. Why so? Why not completely linear? Because this factor is also there, but this factor is very low, so you don't need to consider it. So it will go like this. And what about this? This will certainly be completely linear. At 1.9 it will be 0, so this will certainly be linear. This will be your 1.9 volt. This is a linear expression, so it will linearly go down. Linearly go down. That's it. So till 1.9 we have wrote it down. For Vx greater than 1.9 volt, what will happen? Now this is the task. For Vx greater than 1.9 volt, what will happen? Let's check that out. So for Vx greater than 1.9 volt, what will happen? This will be at higher potential, this will be at lower potential. So I can draw the circuit. Higher potential, lower potential. If it is at higher potential, this will become source and this will become drain. Right? So what will be your VSD value? That would be Vx minus 1.9 volt. What would be your VSG value? That would be Vx minus 1. What would be your Vt value? That would be 0.7 volt. So what will be your V overdrive value? V overdrive would be VSG minus Vt. Everything is correct. VSG is Vx minus 1. Vt is 0.7. So V overdrive would be VSG minus Vt. And VSD is Vx minus 1.7. So here your VSD is greater than V overdrive. Say yes or no. No, 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 no. VSD is not greater. VSD is lesser than V overdrive. VSD is lesser than V overdrive. Why so? Because this potential is same. Vx minus 1.9 versus Vx minus 1.7. Let's just say if Vx is 2. So this value will be 0.1 volt. If Vx is 2, this value will be 0.1 volt and this value will be 0.3 volt. So this is greater. This value is greater. This value is greater. And that value is V overdrive. So V overdrive is greater. If V overdrive is greater, that means it is working in linear region. It is working in linear region. Right? So it is working in linear region. And what is the direction of this current? That is Ix, and Id will also be in the same direction. I can write down the expression of Id and Ix. This lecture will take time, but certainly you are going to learn a lot of new things here. And this will help you a lot in the interview as well as in the written test of any company. Also in the GATE examination, I am expecting these kind of questions to come very, very quickly. And these are very conceptual questions. And if you have the 4 options, it will be easier for you. But if you don't have any option, then it is a bit difficult. So what is ID? ID will be some constant. And we are writing for Vx greater than 1.9 volt. Vx greater than 1.9 volt. It will be some constant into VSG minus Vt into VSD minus VSD square by 2. Some constant. VSG minus Vt. What is VSG minus Vt? That is V overdrive. Vx minus 1.7 into what is VSD? VSD is Vx minus 1.9 minus 1.9 minus Vx minus 1.9 square by 2. This is your ID or Ix expression. Now the expression looks very complex. Here you cannot even ignore any factor. Why so? Because if Vx equals to 3 volt, then this will become significant. If Vx is equals to 3 volt, this will become significant because 1.1 square by 2. This is a significant value, 1.21 by 2. It is a significant value. So you cannot ignore it. But one thing I know is that if I increase my Vx, if I increase my Vx, if I increase my Vx, what will happen? VSD will increase and VSG will also increase. If I increase my Vx, this factor will increase, this factor will increase, this factor will also increase. The doubt is this factor will increase, this factor will increase, now this factor will also increase. So overall this factor will increase and this factor will also increase. So the value of ID will increase or decrease. This is the doubt. The expression you have wrote, if Vx increases, this factor will increase, this factor will increase and this factor will also increase. Tell me one thing, overall value will increase or decrease? It will increase only. Why so? Do you remember the ID versus VDS curve? ID versus VDS curve. If I increase my VDS anyhow, my current increases, but in linear region, if I increase my VDS, my current increases. But what is the formula? Some constant into VGS minus VT into VDS minus VDS square by 2. So there also you can argue, sir, this value is increasing, this value is also increasing. So why this overall value should increase? Because this value doesn't increase that much as VDS. Are you understanding this point? VDS increases more and this value doesn't increase as much as VDS. So it will increase only. The argue could be, sir, VDS is also increasing, VDS square by 2 is also increasing. So increase minus increase, what will happen? Overall increase or decrease? It can be anything, but VDS square by 2 will not increase that much as VDS. So while current increases only. The same thing is happening with ID versus VSD as well in case of PMOS. So here the current is going to increase only, but not linearly, but square relation would be there. So current will increase. And what about GM? Do you remember the formula of GM for triode region? That is some constant into VSD. So what is your VSD? VSD is Vx minus 1.9, right? So it is certainly going to increase as well. Vx minus 1.9. At 1.9 it will be 0. Is there everything correct? Let me check. Yeah, so the GM formula is correct. Some people may have a doubt. In the initial question I wrote the GM is del ID upon del VGS. So what is ID here? Is ID equals to Ix or ID is the current that we are taking? So in the question it needs to be defined what is ID. So ID I will write current from drain to source in case of NMOS and current from source to drain in case of PMOS. This should be defined in the question only, and also in the question GM value should be given, that should be del ID upon del VSG. Look, if they have given that your GM is del Ix upon del VGS, then there would be no problem. But if they are calling ID, then they have to define, because our ID direction is getting changed in the question, right? Our ID direction is getting changed. Initially, here my ID direction was upward. Now what is my ID direction? For Vx greater than 1.9 volt. For Vx greater than 1.9 volt, what is happening? Oh, I forgot to tell, for Vx greater than 1.9 volt, this is becoming source and this is becoming drain. Did I tell you that? Yeah, here I told you. So yeah, this is my ID. Now this is my ID. That is getting changed. So here I don't need to write. So ID direction is getting changed. So based on that, my GM direction will also change. So GM is going like this. Now GM will increase. So they have to define in the question. Did you understand this point? The high chances is that they will define GM as del Ix upon del VGS. They will define GM as del Ix upon del VGS or del Ix upon del VSG. If they are defining del ID upon del VGS or del ID upon del VSG, then they need to define what is ID. So ID is the current from drain to source in case of NMOS, and current from source to drain in case of PMOS. So here the current from source to drain, this is the current. And in the previous case, the current from source to drain, this is the current. So this is the ID. And based on that, we are writing our GM equation. So K into VGS minus VT. Here also we wrote in the same manner K into VSD. Here also some constant into VSD. Crystal clear? Everything is clear, right? So based on the given equation, you need to find out the value of GM. For Ix, there is no issue because Ix direction is shown, but GM is the expression. So for that, they need to define it. Yeah. So Ix versus Vx curve we are drawing. So in the next page only I should draw, I guess. So this was the Ix versus Vx curve. So after that, after 1.9, it will increase like this. Because I told you, if Vx is increasing, the current will increase only, right? This expression will not increase that much, but this expression will increase. So the current will increase only. It will increase till 1 point. It will keep on increasing, but we are going to draw till 3 volt only. And if we are drawing GM versus Vx, I can just copy this one. GM versus Vx. So after 1.9, what is the scene? After 1.9, it is increasing in positive direction only. So like this, it is increasing. It will keep on increasing in the same manner, but we have to write down till 3 volt only. So this expression might seem a bit complex to you, going like this and then increasing, because the ID direction is getting changed. First GM was decreasing, then again increasing, because ID direction first was in this direction and then ID was this direction. So that's why GM expression is going like this. Are you understanding this point or not? Well and good. So in the question, ID direction should be defined. Understood? So these three questions we have seen. In the last problem, what was the scene? Three condition we saw. For Vx less than 1.9 volt, it is certainly interchanging. The upper one is working as drain, lower one is working as source. So current direction will be from source to drain. That is your ID. So then we go to know the condition of saturation and linear. So Vx less than 1.7, it is working in saturation. Vx greater than 1.7 till 1.9, it is working in linear. Then we could write down the expression. Ix expression we could write down, GM expression we could write down. And similarly for linear region as well. Then we could draw the graph. For Vx greater than 1.9 volt, it is working in the Vx will be source and 1.9 will be drain. And it is working in linear region. So for linear region, we could write down the expression of Ix as well. And then we could write down the expression of GM as well. And then we could draw the graph. Well and good. Now we are moving towards the different kind of questions. Here we just need to draw V0 versus Vin, and Vin value is getting swept. Vin value is getting swept from 0 to 3 volt. So let's check that. Let's check out what happens. Okay. Yeah. So this will be a very interesting question, and I have changed some values. Here RL value is very low, and you have to find the maximum value of V0 as well. You have to draw the graph, and also you need to tell me what will be the maximum value of V0. So let's start solving this problem. If I ask you one question, what is that question? I am asking you, what is the minimum value of Vin at which the transistor turns on? Approximate value. What should be the approximate value of Vin at which the transistor turns on? You are sweeping Vin voltage from 0 to 3 volt. What is your answer? 1.7 volt. Is that your answer? That means you want to say that for Vin less than 1.7 volt, MOS is off. Is that your statement? If this is your statement, this is absolutely wrong. Why so? Let's just say I am saying that at 0.1 volt my transistor is not turning on. If it is not turning on, then what is the potential at V naught? 0 volt, because there will be 0 ampere current. The whatever the current that is flowing through MOS, the same current is flowing through RL. So there will be 0 current through RL. So V naught will be 0 volt. This potential is 0 volt and this potential is 1 volt. Which one is higher? This one is higher. Right? This one is higher. So if this is higher potential, that means this will be drain and this will be source. The current will flow in this direction. Are you getting this point or not? Initially, there is no current. When Vin equals to 0 volt, there is no current in the transistor. So V naught becomes 0. What I mean to say is that I will write down all these points now. Initially, MOS current is 0 equals to 0 amp. If that is 0 amp, that shows that V naught is equals to 0 volt. What will happen? V naught will become source because that is at lower potential, and 1 volt would become drain. Right? Tell me one thing. Can this ever be source? Can this ever be source? Let's just assume that this potential, let's call this as X potential. So I am calling this Vx is becoming drain. Vx is becoming drain. Someday, by some value, somehow your Vx, this potential is becoming source. Currently, this one is source and this one is drain. Currently, this is the scene. Let's just say sometimes it becomes source. Then what will happen? If this becomes source, then what will happen? The current will flow in this manner. Say yes or no. If this becomes source, if X potential becomes source, the current will flow in this manner. If the current flows in this manner, then what will be the voltage drop? Like this. Now this V naught voltage drop will certainly be lesser than 0. Say yes or no. If someday your potential X becomes source, then what will happen? The current will flow in this direction. The voltage drop at V naught will be negative. So here you are having negative and here you are having 1 volt. Which one is higher? This one is higher. Can this be source? No, drain. So the potential X can never be source. What did I do? I assumed that potential X is source. If I assume it to be source, then the current direction would be from up to down. If that is the current direction, then V naught will be negative. And if V naught is negative, that means drain potential is negative and source potential is at 1 volt, which is not possible. So what did I get to know? That 1 volt will always be drain and V naught will always be source. Say yes or no. No matter how I draw the circuit, V naught will always be source and 1 volt will always be drain. So this is what we are going to write now. So let's assume potential X is source. So we'll draw the circuit once again. This is the potential X which is at 1 volt. If it is source, what will be the ID direction? This would be ID direction. Then V naught will be negative. But Vs that is equals to Vx that is at 1 volt and V naught which is equals to Vd that is negative, and this is not possible. Right? The drain potential cannot be negative and source potential being positive and drain potential being negative. This is not possible. That means what does that show? That shows that X will always be drain. X will always be drain and V naught will always be source. That means this will always be at higher potential, this will always be at lesser potential than V naught. So how will your diagram look like now? I can make the diagram like this. This will always be drain, this is source, this is source. Basically the current direction will be in this direction. The current direction has to be like this. So what I am doing, the current is flowing from 1 volt to outward towards V naught. So this is how I can show it. This is RL and this is your V in. That's it. This is how your circuit should look like. This is your final circuit. Final circuit. Are you understanding this point or not? Did you get this point? I assume that if X is source and V naught is drain, then V naught is becoming negative and X is at one potential, which is not possible. That's why V naught will always be source and X will always be drain. So this is how I made it, and this is NMOS. Since this is NMOS, the direction of current will always be from drain to source. One thing also I got to know that V naught can never be greater than 1. So what is the maximum value of V naught? 1 volt, right? That's it. The maximum value of V naught is 1 volt. But before that, let's solve the circuit now. So this is the circuit. This is our final circuit, which I have drawn here. Now, for V in less than Vt or V in less than 0.7 volt, MOS will be off. Say yes or no. Initially MOS is off, so V naught is at 0 volt. Initially MOS is off, so V naught is at 0 volt. So for turning on the transistor, you need VGS greater than Vt. Initially, V naught is at 0 volt. Initially, V naught is at 0 volt. Until V in is less than 0.7 volt, MOS will be off. Are you agreeing to this point? Because you need VGS greater than Vt, but here your VGS is less than Vt. When V in is equals to 0.7 volt. At 0.7 volt, what will happen? Let's assume I consider transistor to be on. I am assuming the transistor is on. So at 0.7 volt, there will be some current here. If there is some current, there will be some voltage drop. It can be some 0.001 voltage drop. Why so? Because just as you turn on the transistor, what will happen? What is ID versus VGS curve? ID versus VGS curve. It goes like this. Just as your VGS is, just as the current flows, that value is very less, right? This value is very, very less. The current value is, this current value is very less. So very less amount of current flows here, very less. And this value RL is also very less. That means this V naught will also be very less. But it will be somewhat greater than 0, that's for sure. Your V in is at 0.7 volt. Your V in is at 0.7 volt and your V naught is 0.001 volt. That means your VGS is some 0.69999 volt something. Here also it will not turn on, but you can say that approximately nearly around 0.7 volt it will turn on. So I am writing when V in is equals to 0.7 plus volt. So just somewhat greater than 0.7, your transistor will turn on, because when you turn on the transistor, the ID is very small. That means V naught will be very small. So this I can write down. ID I can show. V naught I will remove. This also. MOS is on. When MOS just turns on, at that time ID is very small. And what is your V naught? That is ID into RL. That is also very small, right? Let's check the region of operation. What is VDS here? VDS is 1 minus V naught. What is your VGS? V in minus V naught. What will be your V overdrive, that would be V in minus 0.7 minus V naught, right? For saturation, VDS should be greater than V overdrive. So V in should be less than 1.7 volt. For saturation, your V in should be less than 1.7 volt. Are you agreeing to this point? Did I write it correctly? VDS should be greater than VGS minus VT, so V not getting cancelled. V in should be less than 1.7 volt. When V in is less than 1.7 volt, it is in saturation region, and when V in is greater than 1.7 volt, it will be in linear region. Now, since it is in saturation region, so the current should be constant. Is that so? Because we have studied in saturation region, the current is constant. In saturation region, the current is constant. But the current is constant only when this is for a particular VGS value. VGS value should be fixed. If your VGS value is fixed, then only the current will be constant. Here VGS value is fixed. No, value is varying on V in minus V naught. So the current is not constant. So let's take the condition for 0 to 1.7 volt. Let's see what happens. For our target is to find V naught. And what is V naught? V naught is ID into RL. So for finding ID, we need to know the region of operation. If we know the region of operation, we can write down the value of ID. So for V in equals to 0 to 1.7 volt, what will be your ID? ID will be some constant, right? Okay, some constant into VGS minus VT square by 2. What is VGS minus VT? VGS minus VT is V in minus 0.7 minus V naught. V in minus 0.7 minus V naught square by 2 will be taken care in the constant only. So this is some constant into V in minus 0.7 minus V naught into whole square. So what will be your V naught? V naught is ID into RL. So basically your V naught would be K into V in. Although these are not small signal, I have developed the habit of writing V naught like this. Actually V naught should be written like this. What is small signal? We will learn it. No need to worry. All this should be written like in this manner, V naught, the way I have written, but I have developed the habit of writing V naught like this. You just need to consider this is capital V naught. We are doing the DC analysis. If we do the DC analysis, we write in capital. If we do the AC analysis, we write in small. You will know the region in the next lecture, but just consider here we are doing DC analysis, so everything is large V naught. Capital letters, all are capital letters. And I have developed this habit, which is wrong actually. I should not develop this habit. So K into V in minus 0.7 minus V naught whole square. So what will be your V naught? V naught would be ID into RL. So K into V in minus 0.7 minus whole square into RL. So this will be your V naught value. If you see intuitively, what do you see? If your V in increase, then your gate voltage is increasing. That means your current should increase. If your current is increasing, then your V naught should increase. If your V naught is increasing, that means your source potential is getting decreased. If source potential is getting decreased, if your V naught is increasing, that means your source potential is getting increased. If your source potential is getting increased, that means the difference here, VGS, is getting decreased. Then the current should decrease. Did you understand this point or not? What I mean to say is that if Vin is increasing, then if gate voltage is increasing, current should increase. Because what is the current? K into VGS minus VT. VGS minus VT whole square. The gate voltage is increasing, then the current should increase. If the current is increasing, then V naught should increase. If V naught is increasing, then what is happening to VGS? Source potential is increasing, then VGS is going down. If VGS is going down, the current should go down. What do you think what will happen? The current will rise or fall? If I increase V in, the current will rise or fall? The current will rise only, but not very fast. The current will not rise like this. The current will rise slowly. Why is it so? Because if I increase V in, the V naught does not increase as much as V in. Did you understand this line? If I increase V in, the V naught doesn't increase as much as V in. Why so? Because RL value is very low. If you just increase V in, ID value is already very low, because I told you if your transistor is turning on, then ID value is low. RL value is very low, so V0 value will also be very low. V0 will increase, but very slowly it will increase. This is the assumption we have to make, or this is also a fact that always source potential does not increase as much as gate potential. When we study amplifier, you will also get to know that the gain will be less than 1. The gain will be less than 1. So V0 will follow input V in. If V in is increasing, V0 will also increase, but it will not increase as much as V in. Are you getting this point or not? It will not increase as much as V in. So this is what I wanted to write. If I increase V0, if I increase, not I, people will think this is current. If we increase V in, I will increase, V0 will increase, but V0 will not increase as much as V in. V0 will increase, but not as much as V in. Are you getting this point? So for saturation region till 1.7 volt, I am drawing V0 versus V in. So V0 will just keep on increasing, but till what point it will increase, we don't know. After 1.7 it will be in saturation region, so we will talk about that. So it will increase like this. So at 1.7 volt, the value V in value is 1.7 volt. V0 value will be very less. It will be very less than 1.7 volt. Are you getting this point? Because V0 is increasing, but not as much as V in. V in has increased from 0 to 1.7. V in has increased from 0 to 1.7. The increase is 1.7 volt. But in case of V0, it will not increase that much. Practically, it will increase nearly around 0.2 volt or 0.3 volt only. Very less it increases. So not that much. Okay. So it increases very less. I will draw a better diagram. Well and good. After 1.7 volt, what happens? For V in greater than 1.7 volt, it will be large. For V in greater than 1.7 volt, what happens? A diode is in saturation. No, sorry, triode. Diode is in triode region. So what is your ID value? ID value, some constant into VGS minus VT. What is your VGS minus VT? VGS minus VT is this V in minus 0.7 into VDS. What is VDS? VDS is 1 minus V0. This is your ID, and your V0 would be ID into RL. Right? Now again you will have a doubt. Sir, what will happen if we increase V in? The V0 will increase or it will decrease? It will again increase. If you are increasing the gate potential, it is certain that your current is going to increase and V0 will increase, but not as fast as it could. Are you getting this point? It cannot increase as fast as it could. It will increase slowly only. So the waveform will be same. In the examination or in the interview, if they ask you to draw the waveform, you will draw it in the same manner only. You will just tell them, sir, it will keep on increasing. Now the question from their side would be coming is that, okay, I admit it will keep on increasing, but till what value it will increase? That would be their question. Oh, I can make it also better. Okay, that seems good. Now their question would be, what would be the maximum value of V0? Tell me. That would be 1 volt only. Why so? Why is it so? Because what was your circuit? This was your circuit, and then there is this V in. V in could be anything. This was your 1 volt and this was your V naught. If your, let's just say if your V naught goes above 1 volt, what will happen? This will, let's just say this is 1.1 volt. If this is 1.1 volt, what will happen? This will become drain and this will become source. Right? What will be the current direction? This would be the current direction. If this is the current direction, then what will happen? The V naught potential will become negative potential, and which is not possible. This I explained you in the earlier part of video. Not possible. So V naught can never be drained. V naught can never be drained. If it tries to be drained, the V naught potential becomes negative. And if it is negative, then source is already at 1 volt. Source is already at 1 volt and drain you are saying negative. So this is not possible. If drain is negative, that means that has to be source and 1 volt has to be drain. So which is not possible. So maximum value V naught can attain is 1 volt. Say yes or no. At 1 volt, what will happen? Let's just when V naught is 1 volt, what will happen? VDS would become 0. If VDS becomes 0, then your ID would become, basically ID would not become 0. What I mean to say is that V naught will be 1 volt, that is the maximum value. So V naught value will be, what will be the maximum value? It will be around 0.99999 something. V naught can go up to 1 volt. It's not that it will go till 1 volt, right? Because if ID becomes 0, V naught goes to 0 only. So basically it will rise from 0 and it will try to go towards 1 volt. That's it. So let's not write it. No meaning of writing it. So did you understand this point? The maximum value V naught can attain is 1 volt. And V in can be anything. When V naught is attaining 1 volt, what should be the value of V in? It has to be at least greater than 1.7 volt, right? It has to be at least greater than 1.7 volt. It can be 1.8 volt. Because let's just say if your V naught is 1 volt and your V in is 1.6 volt. Is that possible? Here your VGS would be 0.6 volt, which is less than VT. So that will turn off the transistor. If transistor is turned off, then V naught will go to 0 volt only. So it has to be at least greater than 1.7 volt. That's why 1.7 volt will come here only. Till 1.7 volt, V naught will never reach 1 volt. V naught is never going to reach 1 volt. Till 1.7 volt. It will be certainly lesser than 1 volt. After, it can reach towards 1 volt. Right, that after 1.7 volt. After 1.7. Well and good. So this is what I wanted to tell in this particular question. So that was actually a very good question. So I hope you have understood. In the examination, they can ask you this kind of waveform. In the interview as well, they can ask you this kind of waveform. So you should have the intuition to tell them like how I am treating this particular problem. So you will start with V in, okay, V in increases, then V in current will increase, then V naught will increase, but V naught will not increase as much as V in. Now if V in is increasing, it will keep on increasing, V naught will also keep on increasing, the region will also change from saturation to, the region will also change. Here what was the region of operation? Here the region of operation was saturation, and here the region of operation was linear. The region of operation will also change, but the maximum value V naught can attain is 1 volt. It will be 1 volt. The maximum value V naught can attain is 1 volt. Lesser than 1 volt, somewhat lesser than 1 volt, it would be 0.9999999. Because if it is 1 volt, the transistor will turn off, then V naught will be 0 volt. If transistor turns off, V naught will be 0 volt. So it will be some 0.99991 volt. So maximum value we can say it will be 1 volt. It cannot go above 1 volt. Why so? Because if it goes above 1 volt, V naught will be drain and 1 volt will be source, which is not possible. So all these things you need to tell in the interview. And in the examination, gate examination, they can ask you these kind of questions. They can ask you region of operation. They can ask you when will the transistor turn on. Here I made a mistake. What is the mistake that I did? It's good that I noticed it here only. So till 0.7 volt, V naught will be 0. Waveform is rising like this. I made a blunder here. So this waveform was wrong. Till V in equals to 0.7 volt. It will be in cutoff only, no? This mistake I did here. This is cutoff, and this is cutoff, and this is saturation. This is cutoff, and then it rises like this. Cutoff and rises like this, right? Till 0.7 it is in cutoff, from 0.7 to 1.7 it is in saturation, then 1.7 to next it will be in linear. So region of operation you can tell how will the waveform go, and maximum value also you can tell. So these kind of questions you will be very much comfortable answering. Well and good. Let's move towards our next question. Now these questions are also very important as well, and also simple as well, simpler than all these things. In the first kind of question, what did we do? In the first kind of question, what did we do? We fixed the potential. There are no resistor, no capacitor. Vx value is getting changed. Here 1.9, here 1 volt. The potential is fixed. Then next kind of question, here we connected RL. The resistance we connected. Now we are connecting capacitor. So what will happen? Let's check that out. So here in this question you have to draw two waveforms, Vx versus time t and Ix versus time t. And initial capacitor voltage is given, that is 3 volt. Initial capacitor voltage is given 3 volt. So if Vx is at 3 volt and this is at 0 volt, so certainly this will be drain and this will be source, right? This will be source and the current will flow like this only, right? Satisfied with that? Okay. So what we are going to do? We are going to write VGS, VT, all those values. So VGS is fixed here, that is 3 volt. VT is 1 volt. So what will be your V overdrive? That will be 2 volt. What will be your VDS? VDS will be Vx, or you can say Vc. VDS will be Vx, or you can say Vc. Vx, Vc, right? So at t equals to 0 plus, initially the capacitor is not going to change its voltage, it will be 3 volt only. So what is the VDS value? That is 3 volt. So at t equals to 0 plus, VDS is greater than V overdrive, right? VDS is greater than V overdrive. Transistor is in saturation region. If transistor is in saturation region, what will be the current? Current Ix. What will be the current Ix? That would be some constant into V overdrive square. V overdrive square would be this. So this will be the current. Now this current is flowing in this manner. In this manner, this current is flowing. What this current will do? It will discharge the cap. So at t equals to 0, what is the circuit? At t equals to 0 plus, MOS is acting as a current source only. MOS is acting as a current source that has the value of k into 2 square, and then here there is a capacitor connected. So this capacitor is charged to 3 volt, and this is your Vx. The capacitor will start discharging. Capacitor will start discharging. And how it will discharge? Linearly. Why linearly? Because the current is constant. If the current is constant, what will be your Vx or Vct? That would be initial voltage is 3, then the current is flowing in the opposite direction. The current is flowing like this. So 3 volt minus 1 by C integration I dot dt. 3 volt minus whatever the capacitor voltage is there and whatever the current is there, current I am calling it current I into T. So the voltage is going down from 3 to some voltage. From 3 to some voltage it will go down. So voltage will go down. You are drawing Vx versus time t. Vx versus time t. So initially your voltage was 3 volt. Now it is going down. Till what voltage it will go down? Till what time we don't know about that. But till what voltage it will go down? Tell me. When your VDS is equals to 2 volt, when your VDS is equals to 2 volt, what will happen? VDS would become equals to VO drive. What I am writing, when VDS or Vx is less than 2 volt, that means your VDS would be less than VO drive. VDS would be less than VO drive because VO drive is fixed, that is 2 volt. VO drive is 2 volt. What will happen? MOS will go into triode region, and then in the triode region, what does the MOS acts as? The MOS acts as resistance. So in triode region, MOS will act as resistance. MOS, in the previous lecture we have studied it, right? MOS acts as resistance. So till 2 volt it is going. You don't need to tell the timing, but you need to tell the potential. When Vx is going down from 3 to 2 volt, till that potential will go linearly and the current will be constant. The constant current would be somewhat this. Ix we are drawing. Ix versus time t. The current would be constant and that constant current value is k into 2 square. K into 2 square till time t1. Till time t1. K into 2 square. So for time t greater than t1, MOS goes into linear region, and in linear region it acts as a resistance. So MOS will act as a resistance now. This is 2 volt now, right? This is your Vx which is at 2 volt now, and this is your Ix. What will happen? It will get discharged. Till what voltage it will discharge? 0 volt. Because when there is 0 volt here, VDS will become 0. If VDS is becoming 0, the current will be 0, right? Basically your Ix would be, what is your Ix? That is some constant into VDS. VDS is VGS minus VT. VGS minus VT is 2 into VDS, that is Vx minus Vx square by 2. We actually replace it with the resistance. We actually replace the MOS with the resistance in linear region. In linear region, MOS is replaced with the resistance between drain and source. R1 or R, whatever it is, R. MOS is replaced with the resistance, but there is an approximation. Do you remember that approximation? We approximate that VDS value is very small. So when we were deriving it, what was the expression? Some constant into VGS minus VT into VDS minus VDS square by 2. What I was doing? Del ID upon del VDS. So if I do del ID upon del VDS, what I was doing? I was considering this as 0 and VDS would be gone. So VDS would become 0. And this would be our fixed resistance. 1 upon this value would be our fixed resistance. So I made an assumption that my VDS value is very small. That was the assumption which we will not forget. So here what does it look like? That my Vx voltage will go down from 2 to 0 volt exponentially. But it will not be perfectly exponential. Why so? Because initially the VDS value is 2 volt, which is not very low. So it will go down, it will certainly go down, but not perfectly exponential. So now you can draw the graph of both Ix and Vx. So here I am writing both Vx and Ix will go down to 0. Will go down to 0, right? Both Ix and Vx will go down to 0. Now we can draw these curves. This was your Vx and this was your Ix. So I will draw it somewhat like this. I am not drawing it like this. Then and then exponential. No. Why so? Because I made an assumption when I was deriving the formula of R on. I made an assumption that VDS is very small, but that is not exactly small. So I will not say that it will go down exponentially. In the interviewer, if the interviewer asks you, how will the waveform go? So you will not say, sir, it will certainly go down exponentially. No, no, no. Sir, nearly exponentially. It will be nearly exponentially, sir. Why it is nearly exponentially? Because when I am deriving the formula of R on, it has the VDS term. So this R value is not constant. It is depending on VDS value. But for our better expression, we take R value to be constant. But actually, it is varying, and it depends on VDS value, right? I told you when we were studying R on value, when we were studying about R on value, I told you there as well that R on is not constant. It depends on VDS, but since we are assuming VDS to be very small, you can assume it to be constant. But here VDS is not that small, so we have to take care that it will go down like this, but there will be something. There will be this. It will not be completely exponential. So this we have to take care. And here also I will make it somewhat like this, not completely exponential, but somewhat exponential. Follows the exponential nature, but not completely exponential. So till this point it was in saturation region, and then it was in linear region. Here it was in saturation region, and then it was in linear region. So did you understand this problem completely? We started with, okay, 3 volt here. The transistor is in saturation region. If it is in saturation region, it will be replaced with a constant current source. It will go down, current will remain constant. But till what voltage it will go down in saturation region? Till 2 volt only. When Vc is equals to 2 volt, when it is equals to 2 volt, my transistor is going into linear region. So in the linear region, my transistor will act as a resistance. So now my voltage will go down exponentially, not linearly. So voltage is going down exponentially, but it is not perfectly exponential because R on value, the resistance R value is depending on the VDS voltage. So I cannot predict the waveform, but it is not completely exponential, that I can say. It is not completely exponential. And this is the Ix voltage. Well and good. Everything is crystal clear. Okay, let's move on to our next problem. This is the next problem. It is more intuitive. Try solving it on your own, then see the solution. So let's solve this question. I added one more thing. You have to find the minimum value of Vx. You have to tell the minimum value of Vx as well. Initial voltage is 3 volt. Initial voltage is 3 volt. One thing, what did you notice here? Here the drain and gate are shorted. Which will be drain, which will be source? This is at 3 volt. This is at 0. So this will be drain, this will be source. That's it. No problem. Here drain and gate are shorted. Drain and gate are shorted. What does it show? What does it show? It will be in MOS will always be in saturation. Saturation. So you can directly replace it with the current source, and Vc value will go from 3 to 0 volt like this. Wrong. Why so? Let's check that out, because it is not that straightforward, because this assignment is fusion special. So this is not that straightforward. What is your VGS? That is equals to Vx. What is your VDS? VDS is also equals to Vx. What is your V overdrive? V overdrive is VGS minus VT. That means Vx minus 0.7. Right? VT is 1. Okay. VT I am taking 1. VT is 1. V overdrive this is. It is in saturation region, that's for sure. What will be your Ix value? Some constant into V overdrive. This is your Ix value. I told you one thing. In saturation region, the current is constant. But when VGS is fixed, here VGS is not fixed. VGS is varying. VGS is depending on the value of Vx. So what is happening? It will act as a current source. Certainly it will act as a current source, but the current source is varying. The current source will change the value of Vx, and that change in the Vx will change the value of current source. Are you getting this point or not? The current source will change the value of Vx, and Vx will depend on the current source value. So basically you can replace it with the current source, but the current source is varying. So here how I will replace my circuit? This is a current source I, which will be a varying one. This is a current source I, this will be a varying one. This is your VC potential or Vx potential, I should write. Vx potential. Initially it was charged to some voltage, then it will go down. And this is your Ix, which is a function of Vx. And this potential Vx is a function of Ix. Why it is a function of Ix? Because what will be your Vx? Vx will be initial voltage 3 volt minus 1 by C integration Ix t dot dt. Ix t dot dt. So what is happening in this circuit is that initially there is some current which is discharging the capacitor. If the capacitor is getting discharged, that means the current is also getting low. Then this low current is also discharging. What I mean to say is that this is a capacitor which is at 3 volt. Let's just say initially it was getting discharged with 2 ampere current. After some time it will be getting discharged only but 1.5 ampere current. After some time it will be getting discharged only but 1 ampere current. It is not getting charged. It is getting discharged only but the amount of current is getting decreased. Amount of current is getting decreased. Are you getting this point? So it is getting discharged but the amount of current is getting decreased. So slowly the current is getting decreased and also the voltage is also getting decreased. So how will your waveform look like? We will draw Vx versus time t and Ix versus time t. So initially your Vx was 3 volt, then it is going down. Now the question is till what voltage it will go down? Till 0 volt or some particular voltage? Tell me the answer of this. Till 1 volt only. Why so? Because when, okay, one thing I can tell here is that, so I will draw this waveform a bit downward. Here your Vx is going down. Here Vx is going down. And why did not I make it linear? Because Ix is not constant voltage. This is depending on Vx, so I can't make it linear. So that's why I had to make it something like this. This is not exponential. It is somewhat like some waveform that you don't know, but it will certainly not be linear. That's for sure. It will certainly not be linear. It will be somewhat waveform that you don't know. Here Vx is going down. Vx is going down. Till what voltage it will go down? Till what voltage? When your VGS is less than VT, what will happen? MOS will be turned off. MOS will be off. And if MOS is off, how will you replace the MOS? This was your cap. And your MOS will be open circuited. Right? Because it is off. That means there is no current. So MOS will be open circuited. And this was the ground. This was your Vx potential. What is your VGS? VGS is Vx only. VGS is Vx only. When it is less than Vt, then your MOS will be turned off. So what is happening? The capacitor is getting discharged. It was getting discharged. At the time when this potential reaches 1 volt, after that let's just assume it tries to go to 0.99 volt. If it is trying to go to 0.99 volt, what is happening? This is saying that it is lesser than Vt. 0.99 is lesser than Vt. And if it is lesser than Vt, MOS will say I will not give any current. If it is not giving any current, then capacitor will not discharge further. So capacitor will remain at the 1 volt only. Are you getting this point or not? Understood? The capacitor was trying to discharge. It discharged till 1 volt. When it was 1 volt, the next potential was 0.99 volt. If you were getting 0.99 volt there, what the MOS will say? That it is lesser than Vt. If it is lesser than Vt, I will not give any current. If I am not giving any current, the capacitor has to hold its voltage. The capacitor has to hold its voltage. The capacitor is holding its voltage to 1 volt. So from 3 to its discharge till 1 volt. That's it. Understood this point? So this is actually a very, very important point which is oftenly asked in the gate examination. What is the minimum value of Vx? It will discharge till 1 volt only. Till 1 volt only. If Vx is less than 1 volt, there is no current. No current. And if there is no current, that means no further discharging. So till 1 volt only it will decay, and after that it will remain constant always, and constant. So let's just say till at some time t1 it reaches to 1 volt. After that it will remain constant. And what about your Vx? What about your Ix? Your Ix will go down. What will be the nature? You don't know. It will certainly be not linear or anything. Your Ix will go down and it will remain 0. At what time it will be 0? At t equals to t1 only it will be 0. Why at t equals to t1 only? Because at t equals to t1 you are reaching 1 volt. After that there will be no MOS current. If there is no MOS current, then this will be your Ix only. This was your Ix. There will be no MOS current. After that there is no current. That means your Ix is equals to 0. So if Vx has reached to 1 volt, your Ix will be 0 only. So that's it. That would be the graph. In the examination, most of the time they will just ask you one simple question: what will be the minimum value of Vx? Then they will frame 4 options: 1, 0, -1, 2 volt. So answer would be 1 volt. Why so? Because till 1 volt it will discharge. That's it. Understood? So this is the waveform. So this was also a very conceptual question and very, very important with respect to gate examination. In the interview they can ask you anything, but in the gate examination this is very important for gate examination. Right? Let's move on to our next question. This is also very conceptual. Here I have connected two capacitors now. So both drain and source are varying. Both drain and source are varying this time. So what is the potential at drain? And we cannot call it drain. First we need to see the potential. What is Vc 0 minus? That is 1 volt. And what is Vc1 0 minus? That is 3 volt. Which one will be drain? Which one will be source? You already know. Vt value is 0.7 this time. This time I have taken Vt value to be 0.7. You have to draw Vx1 versus T, Vx2 versus T, and Ix versus T. Very, very conceptual question it is. Those guys who have good idea of transient analysis, they can only solve this question. You have to get a very good idea of transient analysis, and I am pretty sure most of you guys don't have good idea of transient analysis. But that's why I told you, if you are studying analog electronics, please do have good idea of transient analysis. People will say that you can study analog electronics without studying transient analysis because they want views. But for actual understanding, for real understanding, for solving the question in the examination, for being confident, you should know the transient analysis first. Because I am going to highly use it in op-amp. When I teach op-amp, complete transient analysis will be used. How RC circuit is charging, what is switch capacitor. A lot of teachers in the gate industry don't even teach switch capacitor. Forget about all those things. They don't even teach switch capacitor. Every time they will include resistance. If there is no resistance, how the capacitor will charge, how capacitor will discharge, they will not teach it. Although whatever the concept is used, that I will teach here only. No need to worry about that. But do study network analysis as soon as possible. Okay, so try solving it on your own, then see the solution. So let's start the solution now. So here what do you see? Here your at t equals to 0. At t equals to 0 plus, I can write your Vx2 is 3 volt. Your Vx1 is 1 volt. One which is at higher potential, this is at higher potential, and this is lower potential. That means this will become drain and this will become source. So you have to interchange your circuit. So let's interchange it. because this is becoming source now. This is becoming source now. So I have shown Vc2 here. This is the capacitor 2C, which is charged to 1 volt. This is charged to 1 volt. And this is the capacitor C. This is the capacitor C, which is charged to 3 volt. Which is charged to 3 volt. And this is 2 volt here. This potential is there Vx2 and the lower one is Vx1. This potential is Vx1 and this potential is Vx2. So Vx2 initially was 3 volt and this is 1 volt. Did you understand this diagram now? Did you understand this diagram? Say yes or no. The current will be flowing from this 3 volt. This is the potential which is at 3 volt and this is at 1 volt. The current will be flowing from 3 to 1 volt. So what is happening? The capacitor C is getting discharged and 2C is getting charged, because from the positive potential the current is getting out. From the positive potential the current is getting out. That means the current would be getting in into the negative potential. If the current is getting in into the negative potential and if the current is getting out of the positive potential, what does that mean? The capacitor is getting discharged. This is the scene, plus minus. If this would have been the scene, this is 5 ampere current. Let's just say 5 ampere current. So the current is getting into the positive terminal. The capacitor is getting charged. If it was getting out of the positive terminal, that means capacitor is getting discharged. So here the current is getting out of the positive terminal. The current is getting out of the positive terminal. So C is getting discharged and 2C is getting charged. You can see the region of operation as well. What is your VGS? VGS is 1 volt. What is your VT? 0.7 volt. What is your VDS? 2 volt. VO drive is 0.3 volt. So until your Vx goes to 0.3, it will always be in linear region. Sorry, it will always be in saturation region. I am really sorry. It will always be in saturation region, because here your VDS would be, here your VDS is greater than VO drive. That means it is in saturation region. So until this Vx2 minus Vx1, which is your VDS, is 0.3, then your VT will also change. So forget about the region of operation. For now it is in saturation region. We will check if there is something else or not. We will check. First let's find the steady state value. This is our task. Let's find the steady state value. First we got to know that it is in saturation region. There is a current flowing. That current will also not be constant. Why so? Because the current will also be the function of Vx1. Here the current would be flowing. Yeah, tell me what this current would be. Let's just call this current as Iy. So this current Iy would be negative of Ix, because Ix current is flowing from Vx1 to Vx2, but Iy current is flowing from Vx2 to Vx1. So this will be negative of Ix. So this Iy would be a function of Vx1 and also Vx2. Why also Vx2? Because Vx1 will depend on Vx2. So I should directly write it will be a function of Vx1. It will be a function of Vx1. Now there is a current source which is charging the capacitor 2C and discharging the capacitor C. What will happen in the circuit now? Till what voltage it can charge? What is the maximum voltage this capacitor 2C can get? Maximum voltage that 2C can get. What is the maximum voltage? This 2C is getting charged. Let's just say it is charged to 1.1 volt. What is VGS value? 0.9. If it is charged to 1.2 volt, what is VGS value? 0.8. If it is charged to 1.3 volt, what is VGS value? 0.7. If it is charged to 1.31 volt, what is VGS value? 0.69 volt. Is that possible? 0.69 volt. Is that possible? No. What will happen? The transistor will turn off. If the transistor is turned off, it will not supply any charge. So did you understand it? If your 2C is charged to 1.31 volt, the transistor will not supply any current. Transistor will turn off. So maximum value Vx1 can get is 1.3 volt only. So capacitor C can charge up to 1.3 volt only. The cap C shows that capacitor 2C, sorry, the capacitor 2C can charge up to 1.3 volt only. Why so? Because if 2C charges above 1.3 volt, MOS will be off. MOS will be off. So Vx1 steady state, what will be your Vx1 steady state? That would be 1.3 volt only. Say yes or no. Vx1 would be 1.3 volt only. So when Vx1 was increasing, because Vx1 was increasing, right, from 1 volt to 3 volt, from 1 volt to 1.3 volt, there was IY current. There was IY current flowing out of capacitor C, right? So your capacitor 2C is getting charged from 1 to 1.3 volt. So this IY current was getting out of this, right? Say yes or no. Now tell me one thing, C and 2C, both of the capacitors are having the same current or not? Say yes or no. C and 2C, both of them are having the same current or not? Yes, they are having the same current. Both cap C and 2C are having same current. Same current. If both of the capacitors are having same current, like when the current in C is equals to current in 2C. What is the formula of current? That is the change in charge with respect to the time. The change in charge in C with respect to the time. Time would be certainly same. So the change in charge in C would be equals to the change in charge in 2C. What is the change in charge in 2C? What is the formula of charge? Q equals to CV. Say, whatever the capacitor is. So this capacitance of this 2C is 2C only. And what is the change in charge? It rises from 1 to 1.3. Rises from 1 to 1.3. Final minus initial. This is the change. What about the change in charge? The change in the charge of capacitor C, that we don't know. So what will be the change? Capacitance into the change in charge, that we don't know. So what that change would be? That change would be 0.6 volt. So basically there would be a change of 0.6 volt. Final voltage you don't know. Final voltage you don't know. Minus initial voltage you know. Initial voltage you know. So what is the initial voltage? Forget about this. You just know the change. You just know the change. That is 0.6 volt. And one thing I know, initially it is charged to 3 volt. Now there will be a change of 0.6. So it will go down to 2.4 volt because C is getting discharged. Say yes or no. Initially it was charged to 3 volt, right? There is a change of 0.6 volt, that I know. There is a change of 0.6 volt because the change in 2C is 0.3 volt. So there will be a change of 0.6 volt in C. One thing also I know is that it is getting discharged. So if initially it is having 3 and it is getting discharged, so finally what it will have? 2.4. Right or wrong? Right. Yes. So the change in capacitor, change in the voltage of capacitor C will be 0.6. Change in capacitor C voltage would be 0.6 volt. So Vx2 will go from 3 to 2.4. So Vx2 will, so capacitor C will discharge from, capacitor C will discharge from 3 to 2.4 volt. So Vx1, is it Vx2? Okay, Vx2. Vx2 will decay down from 3 to 2.4 volt. Say yes or no. Did you understand it or not? When you saw the circuit, you got to know that this is acting as drain, this is acting as drain, this is acting as source. So you made this circuit. Then you what did you get to know? You got to know that the current will be flowing like this. Right? The current will be flowing like this. That means it is charging the capacitor 2C and discharging the capacitor C. Till what voltage the capacitor 2C can charge? That is 1.3 voltage. Till 1.3 only it can charge, because after that the current will be 0. So till 1.3 it will charge. If it is getting charged till 1.3, that means it is gaining 0.3. Then how much C would get? 2C into 0.3 would be equals to C into the gain. 2C into 0.3, 2C into 0.3 into equals to C into the gain. So the gain would be 0.6 volt. It can be gain also, decay also, but you got to know that it is decaying. So from 3 to 2 point, from 3 to 2.4 it is going. So steady state voltage. So VC1 steady state, VC1 steady state would be what? 2.4 volt. Say yes or no. What an amazing question it was, right? So these kind of problems, these kind of concepts are only found on prep fusion. Marketing करना तो पड़ेगा यार, इतना मेहनत कर रहा हूँ तो मार्केटिंग तो करना बनता है. तो नाउ वी आर गोइंग टू ड्रॉ द वेवफॉर्म्स. What waveform did they ask? Vx1 versus T, Vx2 versus T, and Ix versus T. So for Vx1, it started from 1 and rises up to 1.3. Started from 1, rises up to 1.3. And that will be the steady state. Let's assume it reaches the steady state at time t1. This is the time t1 when it reaches the steady state. And voltage is 1.3 volt. What about Vx2? It starts from 3 volt and goes till 2.4. What is this? This is not exponential. It can be anything, because Vx1, Vx2, Ix all are function of each other. All are function of each other. So it can be anything. It rises to, it goes down to 2.4 volt and then remain there as it is. This will be 2.4 volt. By the way, you can at steady state, I will draw the circuit now. At steady state, what is the scene? Here only I can draw. This is 2.4. This is 1.3. And this was 2, right? So here, what is your VDS? VDS is 1.1 volt. And what is your VDS is 1.1 volt. What is your VGS? That is 0.7 volt. And V overdrive will be 0 volt only. So again, it is in saturation region only. So we started from saturation. Here I told you, we started from saturation, and we always remained at saturation only. So the region of operation is not that important, but we always was in saturation. We can check it the initial condition at the final condition. So we were always in saturation region. After that, certainly we will go into cutoff. So this is the cutoff. This is saturation. This will be cutoff. And what about Ix? Ix will slowly decrease. Why it will slowly decrease? Why it will slowly decrease? Because VGS potential is getting decreased. VGS is getting decreased. Also VDS is also getting decreased. But you don't need to think about VDS because we are running in saturation region. So if you are running in saturation region, you only need to think about VGS. So VGS is getting decreased. So current will also decrease. And when Vx reaches 1.3 volt, when Vx reaches 1.3 volt at time t equals to t1, time t equals to t1, when Vx reaches 1.3 volt, the current would become 0. Current would become 0 when Vx reaches 1.3 volt. After that, the current would be 0. Say yes or no. Well and good, understood? Crystal clear? So you can revise it once again. I hope I have explained it in a very good manner. You can revise it once again. Then we can move on to our next question. So I will frame one more question that will enhance your knowledge more. So I will frame one more question here. Then we can proceed to our next question. So let's start this question now. So this question I have framed just now only. What it is saying, Vx2 value for t less than 0 is 2 volt. So this capacitor is charged to 2 volt and this capacitor is charged to 1 volt. So here I don't need to interchange. So I reduced the problem. I don't need to interchange here because this is drain, this is source. So drain is already at higher potential. I don't need to interchange it. Vt is 1 volt. Vt is 1 volt, that is given. You have to find the steady state value of Vx1 and Vx2. Steady state value of Vx1 and Vx2. So what should be the steady state value of Vx1? Vx1 steady state. What will happen? This is drain, this is source, there will be current here. There will be a current flowing here that will charge the capacitor 2C. So 2C can charge up to what voltage? It can go to 1, 1.1, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, 7 volt. When it reaches 7 volt, what is your VGS value? 1 volt. If it is going to 7.1 volt, what will be your VGS value? VGS value will be 0.9 volt. At that time, your MOS will turn off. And if MOS is turning off, then there will be no further current and capacitor will hold its voltage. So it will charge up to 7 volt. So Vx1 steady state will be 7 volt. This is not the final answer. Those who have got the final answer, they have to wait. Just wait. I will solve it. I will give you the final answer. So Vx1 steady state is 7 volt. So if it is 7 volt, then how much voltage it has increased? 6 volt, right? From 1 to 7 it went. Vx1 went, the capacitor 2C went from 1 to 7 volt. 1 to 7 volt. So if I apply that charge conservation that I applied there, because the current is same, so 2C got 6 volt. So how much C will get? How much voltage C will get? 2C, the charge that 2C got, that was 2C into 6 volt. Here in the previous problem we solved it, no? What is the charge that capacitor C stored? C into delta Vc. And what is the charge 2C stored? 2C into the change in voltage. Change in voltage was 1 to 1.3. So 1.3 minus 1. So similarly here 1 to 7. So change in 6 volt. And 2C will have delta Vc. So delta Vc would be 12 volt. And if delta Vc is 12 volt, this 2 volt is, this capacitor C is getting discharged. This capacitor C is getting discharged. C is discharging. C is discharging. If C is discharging, then initially it was having 2 volt, then it will discharge by 12 volt. It will discharge by 12 volt. So what will be your Vx2 steady state? It was 2 volt and then it will lose 12 volt. So Vx2 steady state would be minus 10 volt. And this whole analysis is wrong. Right? Why so? Because here you told that it will rise up to 7 volt. Okay, fine. Because VGS would be greater than VT. Now you are saying that it will decay till minus 10. That means this will be the scene. This will be the scene. It will decay till minus 10. You can write in this manner that it will decay till minus 10, then I can improve it like this. Is that possible? Your drain is at minus 10, your source is at 7. Is that possible? No, this is not possible, right? We are in the previous question we considered this equation that your VGS should be greater than VT. But did you consider this equation? as well, that your VDS should be greater than 0 as well. For the transistor to turn on, your VGS should be greater than VT, but your VDS also should be greater than 0. Are you getting this point or not? Your drain to source voltage should also be greater than 0. This is the condition as well. So you have to consider that as well. Now we will solve the problem correctly. In the previous problem, I did not care about it. Why I did not care about it? Because at the steady state, I could see that my VDS is 1.1 volt. So here I could see that my VDS is already greater than 0 volt. So this is also one of the conditions that you need to take care. But here I could see that what is my VDS? Here my VDS is, this is minus 10 and minus 10, this is minus 10. Drain is minus 10. And source is at, source was at 7 volt. Vx1 was 7 volt. Vx1 was 7 volt. Source was at 7 volt. Minus 17, which is wrong. It cannot be like that. So now I have to take care of the condition that your VGS, so your VDS should be greater than 0. So this is our circuit. This is 8 volt. 2C. This is 1 volt. C. This is 2 volt. Now there is this current I. This is your Vx2, and this is your Vx1. Let's just assume if there is a current I flowing, both of them are having the same current. The current in 2C would be the same in current in C, right? Tell me one thing, if this 1 volt is developing, if this 2C is developing X voltage, then how much voltage this 2C will lose? Are you getting this point? That C is getting discharged. C is discharging and 2C is charging. So if 2C is getting X amount of voltage, if 2C is getting X amount of voltage, then how much voltage C will lose? If 2C is getting X amount of voltage, then how much voltage C will lose? Let's check that out. Let's check it out. So let's assume that if both of the current are same, that means the charge, that is change in charge, would also be same. The change in charge would also be same. So what is the change in charge in case of 2C? That would be 2C into change in charge. Change in charge. Let's just call it delta V into 2C. The change in charge. That is delta V into 2C. What will be the change in charge in this one? That would be delta V into C. So what is the relation? Delta V into C would be equals to 2 into delta V to C, right? This is the relation. The change in voltage, the change in voltage of C would be twice of the change in voltage of 2C. Let change in voltage of 2C is X. That means 2C is gaining X voltage. 2C is gaining X voltage. So what will be your Vx1? Vx1 steady state would be 1 plus X. So if it is gaining X voltage, then how much C will be losing? 2X. Because capacitance value is half. If capacitance value is half, it will lose 2X. If it is gaining X, it will lose 2X. Say yes or no. In the previous program, what was happening? Here it was gaining 0.3, 1 to 1.3. So it was gaining 0.3. So it was losing 0.6. It has gained 0.3. So C was losing 0.6. Say yes or no. So similarly, Here, if it is gaining x, then how much 2c will lose? How much this c will lose? C will be losing 2x. If 2c gains x voltage, then C loses 2x voltage. Say yes or no. What will be your Vx2 steady state? That would be 2 volt minus 2x. 2 volt minus 2x. It was gaining x voltage and it was losing 2x voltage. It was gaining x, it was losing 2x. So if it was gaining x, 2cx would be the charge. And if I was losing 2x, then what will be the charge? C into 2x. So 2cx. Right? So this is the Vx2 steady state. Vx2 steady state. And one thing I know that at steady state, what will happen? Your VDS will be 0. Because if VDS is 0, the current I would be 0 ampere. So that is the steady state voltage. So VDS is 0. That means Vx1, what is VDS? VDS is Vx2 minus Vx1. Vx2 minus Vx1 is equals to 0. So Vx2 is equals to Vx1. So 2 minus 2x is equals to 1 plus x. X will be 1 by 3 volt. X will be 1 by 3 volt. X will be 1 by 3 volt. So what will be your Vx1 steady state? That would be 1 plus 1 by 3. 1 plus 1 by 3 would be 1.33 volt. And what will be Vx2 steady state? 2 minus 2 by 3. 2 minus 2 by 3 would be what? 1.33 volt only. Of course, both has to be same only. 2 minus 2 by 3 would be 1.3 only. Say yes or no. Did you understand it or not? We tried to solve it. We tried to solve this problem in the same manner that we studied. So what we have studied, that the 2C can charge up to 7 volt. So we did that. When we did that, what did we get to know? That if 2C is getting charged to 7 volt, if 2C is getting 6 volt, then C will lose 12 volt. If 2C is getting 6 volt, then C will lose 12 volt. If C is losing 12 volt, then what is happening? The C will be at minus 10. C will be at minus 10. Source will be at 7. That means so VDS is going very low. You take care of the condition of VGS greater than VT, but you forgot about the condition of VDS greater than 0. In the previous question, we took care of VGS greater than VT. We took care of VGS greater than VT, then we checked if VDS is greater than 0 or not. Yeah, it is good. Well and good. Here, we took care of VGS greater than VT, but we forgot to check of VDS greater than 0. Then we got to know that VDS is not greater than 0. Then what did we understand? That we need to take VDS equals to 0. If VDS is equals to 0, that will be the steady state. Because if VDS is 0, there will be no current. So capacitor will neither charge nor discharge. So they will hold their voltage. If VDS is 0, there is 0 current. If there is 0 current in the MOS, then capacitor will hold their voltage. Right? Then what we know? If 2C is getting X voltage, then C will lose 2X voltage. If 2C is gaining X voltage, then C will lose 2X voltage. That's it. So C was having initially 2 volt, then minus 2x, and it was having initially 1 volt, then plus x. So 1 plus x, and this will have 2 minus 2x. And at steady state, VDS will be equal to 0. So both of the potential will be equal to 0. If both of the potential are 0, then I could get the value of x. That was 1 by 3. So Vx1 steady state would be 1.33 and Vx2 steady state will also be 1.33. So that was an amazing question. 2 questions I have shown you. I hope you are very much comfortable with all those kind of concept. Well and good. We can solve more question like that. So we will solve more question because that is an important part for your preparation. But let's see it later on. We first solve the question that is already given. Okay, so here VC1 is 3 volt. This is given. and Vc2 is 1 volt. It is also given, right? So what will be your Vx1 at t equals to 0? Vx1 at t equals to 0 plus 3 plus 1, it will be 4 volt only. And what will be your Vx2 at t equals to 0 plus? That will be 3 volt only. So this will be your drain and this will be your source. So this is your drain and this is your source. And this is certainly gate. Know about that. What is your VGS value? 2 minus 3, which is equals to minus 1, which is less than VT. MOS never turns on. MOS doesn't even turn on. This is the steady state. Ix is equals to 0. There is no current in the MOS. Ix is equals to 0 and this is the steady state. That's it. What did we get to know? Here we get to know that your VGS is less than VT. That means MOS is never turning on. There is no current, nothing. The capacitor will hold their voltage. There is no current, no source. So capacitor will just hold their voltage. So you have to draw Vx1 versus T and Vx2 versus T. Right? Vx1 versus T and Vx2 versus T. थक गया भाई ये लेक्चर रिकॉर्ड करता करता मैं. लाइक तो बनता है. You should give a like, right? If we are explaining these kind of concept, you should certainly put a like at least. Vx1 versus T, Vx2 versus T, and Ix versus T. Always 0 ampere current. And I strongly, highly recommend you to study network analysis from Prefusion once. Please study network analysis from there. In network analysis, you will see a lot of these kind of concepts which are not taught to you in your gate preparation or even for placements. And in the examination, in the interview, you face these kind of question and everything goes blank. It affects your complete examination as well. So whatever the subject we study, we will build so much of strong concept in that. No matter how tough the question is framed in the examination, you will be able to answer. And that is my promise. So always 3 volt will be there and Vx1 will always be at 4 volt. Vx1 will always be at 4 volt. And Vx2 will always be at 3 volt. And the current will always be 0. This was 4 volt and Vx2 will also be like this. So it will always be at 4 volt, it will always be at 3 volt. That's it. And this will always be 0 ampere. Any doubt about that? No doubt, right? So this was the question. Let's move on to the next problem. This is the problem. So for t less than 0, Vin is 0. And for t greater than 0, Vin is 3 volt. So whenever there is a step input applied, this is step, right? This is step input. So whenever there is a step input applied from 0 to some 3 volt, then you always need to solve the problem from minus infinity. In the network analysis, I also told you, if we are having some step, you will always solve from minus infinity. You have to take the condition of t less than 0 as well. For t less than 0, what was the scene? For t less than 0, here we are solving the problem. So for t less than 0, Vin was 0. If Vin was 0, VGS was 0. Vin was 0 volt, VGS was 0 volt. No current. So V naught at t equals to 0 minus would be same as Vc at t equals to 0 minus. That would be equals to 1 volt. Here I did not mention that Vc voltage is 1 volt for t equals to 0 minus. I have to understand it by my own. In the previous problems, it was given that at t equals to 0 minus, this is the voltage. But here in the diagram, it is just shown that it is at 1 volt. That's it. You have to start the circuit from t equals to 0 minus or t equals to minus infinity. You have to start the circuit from t equals to minus infinity. You have to take the condition from minus infinity to 0. You have to take the condition from minus infinity to 0, then you need to proceed from 0 to infinity. So in the complete window you have to solve the problem. So for lesser than that, there was nothing happening in the circuit. So luckily in this problem, if even if you have started from here, your answer would be correct, because previously nothing was happening. But I will give you one more question where previously something was happening, so then your answer will not be correct. So luckily in this question you are safe, because previously nothing was happening. So VC voltage was at 1 volt only. Now for t greater than 0, or at t equals to 0 plus, V in is 3 volt. V in is 3 volt. And the capacitor is at 1 volt only. So we can draw the circuit now. V in is 3 volt. This is grounded. Capacitor is at 1 volt. And this is your V naught. What will happen? The current will flow, right? Say yes or no. What is the VDS value here? VDS value is, I can call it, is it V naught or Vx? V naught. So VDS value is equals to V naught. And at t equals to 0 plus, if you are talking about, that is equals to 1 volt. What is VGS value? That is 3 volt. And what is VT value? 2 volt. So V overdrive is, VT value is 1 volt. No, why I am writing 2 volt? VT value is 1 volt. So V overdrive is 2 volt. It is working in linear region. You can see it directly, because VDS is lesser than V overdrive. So it is working in linear region. So it can be replaced with the resistance. If it is replaced with the resistance, what will happen? The capacitor will discharge. This is 1 volt. The capacitor will discharge, and till what voltage it will discharge? Till 0, because here VGS is always greater than VT. VGS is always greater than VT. So you don't need to think about this condition, but you have to think about this condition, that VDS goes to 0. If VDS goes to 0, then it will be discharged to 0 volt. Always you need to take care about two conditions. VGS is greater than VT. If your VGS is greater than VT, checked, nothing. Now your VDS will be going towards 0. So your VDS will be going towards 0. I needed to plot V naught versus V. What did I needed to plot here? V naught versus time t. So V naught initially was at 1 volt, and it will decay down to 0 volt, right? And it will remain at 0 volt only. And this was working in linear region. In the previous question, which I took here I did not draw any waveform or anything, because I just simply asked you the question, what will be the steady state voltage? Now people will say these kind of questions are not asked in gate examination, but certainly it will come. I can write it on paper and sign it. In the gate examination, always the question for condition VGS greater than VT has been asked. For the condition VGS greater than VT, it has been asked in the gate examination. Certainly there will be one question which will ask you for VDS greater than 0, and that will be the solution. So be prepared for that. It is certainly coming. In 1 or 2 years, it is certainly coming. The kind of paper, the kind of level they are setting up, certainly these kind of questions are coming. So don't fall for the teachers or even for any educator. They say that these kind of questions are not asked, this concept is not asked. The reality is they are afraid to take up these kind of questions on blackboard. They are afraid to take up. This is the reality. It may seem disrespecting to some people. It may seem, it may sound harsh to some people, but I'm really sorry. This is the reality that I'm telling, that people are not really fond of taking tough examples, because what teachers think is that if I am dealing tough examples, the crowd will not come to me. And this is the reality. If I teach these kind of tough concept, the students will not be happy. They will not be coming. Okay, I will study from him, because the student has to put some stress on the brain. But if you are not putting the stress on the brain, you are not going to get good rank. Ask many of the previous year aspirants. They studied simple thing only. You will keep on studying simple thing. In the examination they will ask you tough questions. If you are preparing for 365 days, for 364 days you will be very happy. On the 365th day you will write down the examination and you will be disappointed. Or even if you crack the examination, in the interview you will be disappointed. I can guarantee. In the interview, in M.tech MS interview, you will be disappointed. Even if you crack the interview while going for placements, you will be disappointed at that time. So yeah, just study thoroughly whatever that I am teaching. I am not taking much of your time. I am taking certain time that is required. It's not that I am blindly teaching anything. I know a lot of things as well. I know more things. Motorola Wising, all those things I didn't. I am not going to teach in the complete network in this complete analog course. But whatever that is required, that is need to be taught, right? Yeah. So this was the question we have solved. Now let's move on to our last question. So this is the last question. So here Vt is 1 volt that is given. You have to draw Vx versus T curve. And again there is a step input. I told you if there is step input, you always have to start from t equals to minus infinity or 4 or t less than 0. So for t less than 0. So for t less than 0, what is the circuit? This is the circuit for t less than 0. Here again your VGS is 0. Again your current will be 0. Nothing will happen in this circuit as well. Right? For t less than 0, nothing will happen here. Current is equals to 0. So this is the steady state only. So let's call this potential as Vx. Not Vx, sorry, it will be Vc. So your Vc for t equals to 0 minus would be 2 volt only, and that will be the same for Vc equals to Vc at t equals to 0 plus. Now let's see the circuit for t greater than 0. What is happening? This is 2 volt and here there is 3 volt and this is Vx. So your Vx potential here, what was your Vx potential? Vx potential for t equals to 0 minus. What was the Vx potential? This was 0 and this would be 2 volt. So what will be your Vx potential at t equals to 0 plus? This was 3 plus 2, 5 volt. Vx potential at t equals to 0 plus, this was 5 volt, right? And since now what is happening? Since this is 3 volt here and Vx potential is 5 volt, what is your VGS? VGS is 3 volt. What is your VDS? VDS is 5 volt. What is V overdrive? V overdrive is VGS minus VT, that would be 2 volt. So here VDS is greater than V overdrive, saturation region. So there will be a constant current here, that is this ID current, and that ID current would be some K into, in saturation region, some K into VGS minus VT 2 square. So there will be some ID constant current. Now where will this ID current would be flowing? The current would be flowing like this, right? Because this is the ID current, this Vx is an open end, so that current has to go here. Now people will say, sir, here there is 0 ampere current because gate drives a 0 ampere current. So from where this current is coming? From the battery. This ID current is flowing like this. This is the ID current. ID current will flow like this. This will be the path of the ID current. What will be the path? This is 3 volt battery. This is the battery of 3 volt. From 3 volt battery to the capacitor, and then there is the MOS circuit. This will be the path. MOS. This will be the path of ID. From 3 volt battery, ID is coming and going like this. input current is 0, but battery can drive some current. No, this is a battery. 3 volt we have shown by the dot, but there is a battery of 3 volts. So battery can drive a current. No. People get confused often that, sir, there will be no current in the 2 volt voltage, so 2 volt capacitor. So that's the steady state. That's it. No, bro. The battery can drive some current, right? Battery can drive it. Yeah. So what this current will do? It will charge the capacitor in the opposite direction. It is charging the capacitor in the opposite direction. What did we consider? This we consider Vx. So it is charging the capacitor in the opposite direction. Yeah. So this was not Vx. This was Vc. So it is getting charged like this. Now tell me, Vx value will go up or go down? Vx value will go up or go down? What is the initial Vx value? 5 volt. Now what will happen? This 2 volt will be reducing because it is getting charged in this direction. Let's just say this capacitor is having 2 volt and now the current is flowing out of it. What will happen? This will go to 1 volt. It will reduce. The similar thing is happening like this. The current is getting out of the positive terminal. The current is getting out of the positive terminal. So the capacitor is getting discharged. Right? The capacitor is getting discharged. So capacitor is getting charged in opposite direction. Charged in opposite direction. So it is getting charged in opposite direction. What does that mean? Vc value will decrease. Vc value will decrease. If Vc value decreases, then what is your Vx potential? Vx potential is 3 plus Vc. That means your Vx will 3 plus Vc. Why I am writing Vx? 3 plus Vc. That means your Vx goes down. Your Vx is going down. So you started from 2 actually. You started from 2, then there was a sudden jump to 5, then it is going down. Now it is going down. How it is going down? It is going down with the constant slope because Vc is constant. What is Vc? Vc is initial was 2, then 1 by c integration I dot dt. I is constant now. 2 minus 1 by c. What is I? I is constant. I is constant. That is 4k. So I is constant. So Vc will go down constantly. So even Vx will also go down constantly. So Vx versus T we are drawing. So initially it was at 2 volt. Then there was a sudden jump to 5. Then it is going down. So from 5 to till what voltage it can go down? From 5 to till what voltage it can go down? Here Vgs is always greater than Vt. V overdrive is always greater than 0. So that is certain that it will always be on. There is no issue with that. The other point is you need to check VDS value. So for VDS needs to be greater than 0. VDS needs to be greater than 0. For transistor to turn on, VDS should be greater than 0. VGS is always greater than VT here. This is your VGS. VT was 1 volt. VGS is fixed, that is 3, and VT was 1. So this is fixed. These voltages are fixed now. These voltages are fixed. VT was 1 volt. Transistor is on. There is no issue with that. Till what voltage Vx can go down? If Vx is going towards 0, if Vx goes to 0, after that it cannot go down. Why so? If it is go down, then that. If it goes down, then 0. Let's just say if it goes down to 0.1, what will happen? VDS value will be minus 0.1. Now, no one will say that, sir, if this is going down, that means this will act as source and this will act as drain. If that happens, then what will be the direction of current? The direction of current will be like this. Now, the capacitor will charge. If the capacitor is charging, then again Vx will go up. Did you understand this point? I explained it very fastly. What did I say? The Vx cannot go down from 0. If I say that Vx is going down to minus 0.1, what will happen? This is at minus 0.1 and this is at 0. Then you will say that, sir, this will act as drain and this will act as source. Okay. If this is happening, then the current will be flowing from drain to source. Current will be flowing in this direction. The same current will be flowing in the capacitor in this direction. Then the capacitor will charge. So if the capacitor is charging, then Vx voltage will go up. Because what is the Vx voltage? 3 plus Vc. So if Vc is going down, then Vx voltage will go up. So you reduce this to minus 0.1, but it is going again towards 0. So again it will be higher than this 0 potential. Again it will go to 0.1. Then again you will say this is drain and this is source. Then again you will start following the current in this direction. Then again you will say that sir Vx is going down. Again you will say sir Vx can go up to minus 0.1 volt. Again the same thing will happening. So this, it will not go like that. What it will say that if I am going Vx equals to 0, at that time only I will stop. That's it. That will be the steady state. So steady state Vx voltage will be 0. In the previous questions as well, this doubt may come to you. Like in what questions? Let me show you. The same doubt might have occurred to a lot of students in the previous questions. Like I guess in this question also that same doubt would have come that sir it is going towards 0. What if it goes towards minus 0.1? Let's say it goes towards minus 0.1 and this is 0. Then what will happen? The current will flow in this direction. If the current flows in this direction, this will charge the capacitor. This charges the capacitor, that means it will rise to, from minus 0.12 it will rise to 0, then again 0.1. If again it is happening, again it will become drain and again it will become source. Again it will discharge. So basically the steady state voltage is 0 volt only. So it cannot go down 0 volt. Are you getting this point? If it goes down to 0 volt, there is a lot of things happening in the circuit. If it is goes down 0 point minus 0.1, that means it will say the current should flow in this direction. That will again charge the capacitor. Again it is charging the capacitor, again it is going up. So basically the steady state voltage is 0 volt. So the kind of feedback is working there. What is feedback? You don't know, but you will study it in the analog electronics. In the whole course, you will study it. Kind of feedback is working there. It is saying that if it is trying to going down from 0, if it is trying to going down to minus 0.1, then it will rise up again to 0 volt. It will get a force to rise up again to 0 volt. Yeah, so it will linearly rise, but till what point it will linearly decay? It is linearly decaying, but till what point it will linearly decay? Because what is VDS? VDS is equals to Vx. And what is V overdrive? V overdrive is 2 volt. When Vx is less than 2 volt, you will get into linear region. And in the linear region, this will act as a resistance. And this will be the gap. So when Vx is equals to 2 volt, this will be the same. So when Vx equals to 2 volt, you started from here only. When Vx equals to 2 volt, till this point it is working in saturation region. After that it will nearly decay exponentially. Nearly exponentially. Why nearly? Because R depend on the value of Vx as well. So nearly exponentially. So this region would be linear. And this voltage we will be getting at some time t1. So steady state voltage of Vx is 0 volt. There is no doubt about that. But it will decay like that. If they ask you what is the steady state voltage of Vc, tell me, what is that? Vc steady state. Vc steady state. Okay, this is the question I am leaving for you. You have to write down the final answer in the comment section. You have to write down the final answer in the comment section. I will write down the final answer in the comment section as well. I will also write down the final answer, but you have to write down the final answer. What is the Vc value at steady state? This is very simple. What is the Vc value at steady state? Very simple it is. Okay, you will write it down. Vc direction is this. Take care of the direction. So what is the Vc value at steady state? This you need to write down in the comment section. So I hope you have understood this problem. In this problem, we saw initially there is 2 volt. Okay, then 5 volt is coming. There will be a current. The current will be from the saturation region. So that current will be charging the capacitor in the opposite direction. That means Vx will be going down. If Vx is going down, it will go down till 2 volt in linear region. After that, it will go down. Sorry, till 2 volt it will go down in the saturation region. After 2 volt, it will go down by the linear region. So it is going like that. So till 0 volt it will discharge, and if Vx is 0 volt, what will be the Vc value at steady state? That is very simple. You can tell that. What will be the Vc value at steady state? That I am expecting in the comment section. And if you like the video, if you found the video helpful, please do share it with your friends. Please do share it. Please tell them what kind of content is being taught on this channel, what kind of content is being taught in the whole analog electronics. In the whole analog electronics, you will see a very different kind of analysis, a very intuitive, and you will put pressure on your brain, and in the examination you will be very happy once you come out of the examination hall, that we studied in that manner and that depth, and no one can beat us. That's for sure. So yeah, do share it with your friends and everyone. So let's meet in the next lecture. We will study further things. Okay, thank you. Hi everyone. So now we are slowly moving towards MOSFET amplifiers. We have seen questions on biasing. We have seen most physics. Now we are moving towards amplifier. So in the previous videos, what did I tell you? That when we are using MOSFET as an amplifier, we bias the MOSFET in saturation region. And I told you that I will tell you the region later on in the further part of the lectures. Now this is the lecture where I will tell you why do we bias the MOSFET in saturation region while using it as an amplifier. So now we are going to answer that, but before that let's solve a problem that will help us to understand the statement more clearly. So the given question is, this question is slightly based on network analysis only. The given question is, in a two-port network, find the condition of y parameter for which the voltage gain is maximum. Those who don't know y parameter, no need to worry. I will tell you what is y parameter here. I will tell you that. No need to worry about that. Okay. Yeah. So you have to find the condition of y parameter such that your voltage gain is maximum. So let's just assume we apply some source voltage, and that source voltage will have some source resistance as well. This is having Rs, this is the source voltage, and then at the load we are having some output. This is the load where we are having some output. This is a load RL where we are collecting the output. What do we need to do? We need to maximize V naught by Vs. This is what we need to do. Maximize. We need to maximize V naught by Vs. This is our target. What is Y parameter? Y parameter simply shows that your I1 is equals to Y11 V1 plus Y12 V2, and your I2 is equals to Y21 V1 plus Y22 V2. This particular box tells these things. What does this particular box tells? I1 is equals to Y11 V1 plus Y12 V2, I2 is equals to Y21 V1 plus Y22 V2. You have to maximize the voltage gain. You have to maximize V naught by Vs. Now you can replace this particular box with the circuit. How we will replace? Like this. We will replace this particular circuit like this. How did I replace it? Let's check it. What did I say? That your I1 is equals to Y11 V1 plus Y12 V2. Can you apply the nodal here? Can you apply the nodal analysis? If you apply the nodal analysis, what do you see? I1 is equals to V1 is the potential here. This potential is V1. This potential is V1. So what will be the current downward? That would be V1 into Y11 plus the current this side, that would be Y12 V2. Isn't it the same? And what about I2? What about I2? I2 will be Y22 I2. So this resistance is there. Y22 I2 plus this current Y21 V1. Sorry, Y22 not I2, Y22 V2. The voltage drop here is V2. So the current in this direction would be Y22 V2, right? And the current here is Y21 V1. Here the voltage drop is V1. So what will be the current here? The current here will be Y11 V1. So directly you can see I1 is equals to Y11 V1 plus Y12 V2. I2 is equals to Y21 V1 plus Y22 V2. So that's how you can replace the circuit. Are you able to understand this? Okay. Now you need to maximize V0 by Vs. V0 by Vs. You need to maximize this. This is our target. Tell me one thing. If this complete if this complete configuration goes to infinite, that means if this complete configuration replaced with the open circuit, what will happen? If this complete configuration is replaced with open circuit, what will happen? Your V1 will be equals to Vs. Your V1 will be equals to Vs. And now this V1 is amplified with Y21 factor. And this complete current is going in the output. Are you getting this point? What I am saying? V1 is amplified with the factor of Y21. And now this Y21 current, Y21 V1, this current will be flowing through this 1 by Y22 resistance and the resistance RL. So first thing is that I need to maximize V1. If my V1 is maximum, then there is high chances that I will get V0 to be maximum, because this V1 is getting amplified. V1 is getting amplified by the factor of Y21. So I need to maximize V1. This is my primary target. Need to maximize V1. And V1 is coming from Vs. So how to maximize V1? If this complete configuration gives you infinite resistance, my target is to get infinite resistance from this complete configuration. How do I get that? How do I get infinite resistance? So my first step is maximize V1. Maximize V1. And for maximizing V1, what do I need to do? So here I was having 1 by Y11, right? 1 by Y11, and this was Y12 V1, I guess. Y12 V2. Y12 V2. And from here, whatever that was coming. So if I make this resistance as infinity, what will happen? V1 will be equals to Vs only, right? V1 will be equals to Vs. If R is infinity, V1 will be equals to Vs. How you can make R equals to infinity? Tell me. How you can make R equals to infinity? Y11 goes to 0 and Y12 also goes to 0. If Y11 goes to 0, what will happen? This resistance value will be infinity. What do you mean by infinite resistance? What do you mean by infinite resistance? Open circuited. If Y12 goes to 0, that means this current will be 0. What do you mean by 0 current? Open circuit. In open circuit, there is no current. In short circuit, there can be current. But in open circuit, there will be 0 current. So if Y12 is 0, that means there will be 0 current. That means this is open circuited. So from here you see infinite resistance. Are you getting this point or not? So my desired condition came out to be Y11 and Y12 should be 0, or you can say both should be minimum. So Y12 should be minimum and Y12 should be minimum. If not 0, they should be minimum. So this is the desired condition. So first condition we have found, that is, or Y11 and Y12 should be minimum. Did you understand? My target was to maximize V1 because V1 is getting amplified here. So how do I maximize it? By making the resistance infinity. How do I make the resistance infinity? If I put Y11 equals to 0, that means the resistance will be infinite. And if I put Y12 equals to 0, the current source will be 0. If current source is 0, that means infinity resistance. So infinite parallel with infinite is equals to infinite only. So I made Y12 equals to 0 and Y11 equals to 0. Or this is the ideal condition. Practical one is that both should be minimum. So then only you will get V1 equals to Vs. Now what is my second target? My second target is this Y21 V1 current is going in two resistances, that is RL and 1 by Y22. This 1 by Y22 resistance, this particular resistance is eating up some current. This particular resistance is eating up some current. This is eating up some part of Y21 V1. If this resistance is infinity, then what will happen? If 1 by Y22 is infinity, what will happen? The complete current will be flowing through RL. Are you getting this point? If 1 by Y22 is infinity, or if Y22 is 0, that means the complete current will be flowing through RL. Say yes or no. right? Then what will be your V naught? V naught will be Y21 V1 into RL, and minus sign will be there because this current will be flowing like this. Did you understand this point? So my second target is maximize V naught. Maximize V naught, or you can say minimize Y22 V2. Minimize Y22 V2. This current you need to minimize, or minimize Y22 V2. Then what is the target? That your Y22 should be 0. From here we got to know that Y22 should be 0 or Y22 should be minimum. So we got to know about Y11, Y12, Y22. Now the only thing left is that is Y21, Y21, Y21. So now what is your V naught? Your V naught is simply this current, Y21 current. This resistance is infinity. So the complete current is flowing through RL. So what is your V naught? V naught is Y21 V1 into RL and minus sign. Y21 V1 into RL and minus sign will be there. That is your V naught, because this current is flowing like this, right? Y21 V1 into RL and minus sign will be there. That will be your V naught. This is first equation I can say, and one more thing I can say is that V1 is equals to Vs. So what is your gain? Gain is minus Y21 RL. This is your gain. To have the maximum gain, what should be the condition? To have maximum gain, Y21 should be maximum. That's it. We have found all the condition. What are the all the condition? Y12 minimum, Y21, okay, Y12 minimum, Y11 minimum, Y12 minimum, Y22 minimum. Only maximum is Y21. Y21 is maximum. That's it. These are the condition. Are you getting this point? When you see this structure, you don't need to think much. How you will think? You will think that okay, the I1 current is coming. I1 current is coming. Forget about I1 current. I need to maximize V1. So how do I maximize V1? That Y11 is 0, Y12 is 0. If both are 0, that means we will see infinite resistance. Then V1 will be equals to Vs. So Y11 and Y12 has to be minimum. Now this V1 is being amplified by the factor of Y21. Now if this is amplified, the amplification should be large. V1 is being amplified with the factor of Y21. If it is being amplified with the factor of Y21, that means the amplification will be should be large. If amplification is large, that means I will have more output. So for that, Y21 should be large enough. So Y21 should be maximum. Y21 should be maximum. And what about Y22? This Y21 current is flowing through two paths. The two paths are the resistance 1 by Y22 and the other resistance RL. So now this current should flow through only RL. This Y12 1 by Y22 resistance should not eat up any current. So the complete current will be flowing through RL. So for that, your Y22 should be equals to 0. That means Y22 should be minimum. So by this we have found all the condition. This is the most important part. This is the most important output that we have received. Now let's copy those equations again and find out what is our Y11, what is our Y12, what is our Y21 and what is our Y22. So tell me what is Y11. What is Y11? Y11 is delta I1 by delta V1 with V2 being constant. Do you agree with this? Y11 is delta I1 by delta V1 with V2 being constant. If V2 is constant, then what will be your Y11? That would be delta I1 by delta V1. Just differentiate it. Delta I1 by delta V1. This will be 1 and V2 is constant, that will be 0. So what you will get? Y11 only, right? So I will make a small two-port network here. This is our V1. This is our I1. This is our V2. This is our I2. So what is our Y11? Y11 is V1 by I1 by V1. I1 by V1 with V2 being constant. What is our Y12? Tell me. What is our Y12? Y12 is I1 by V2. Delta I1 by V2. Delta, I should put delta here. Yeah. So that is Y12 is delta I1 by delta V2 with V1 being constant. If V1 is constant, this differentiation will be 0. This will be delta I1, this will be delta V2. So delta I1 by delta V2 is equals to Y12. Delta I1 by delta V2 with V1 being constant. What about Y21? What is Y21? Y21 is delta I2 by delta V1 with V2 being constant. Delta I2 by delta V1 with V2 being constant. You can write it. What will be Y22? Y22 will be delta I2 by delta V2 with V1 being constant. Very easy, very simple. Okay, let's not do it. These are the input parameters only, delta I1 by delta V1, delta I1 by delta V2. What do you think this is? What do you think? What is this? If I say this is my output port, if I say this is my output port and this is my input port, right hand side is output, left hand side is input. So if this is my output, this is my input, then what does delta I2 by delta V1 represent? Everyone should be able to answer. What does delta I2 by delta V1 represent? This represents transconductance. Output current, change in output current with respect to the change in input voltage. So this is transconductance. This is GM. I will simply write GM. You will be able to understand. What is delta I2 by delta V2? What is delta I2 by delta V2? That is output, not output resistance. It is 1 by output resistance. 1 by output resistance. Are you getting this point? Delta I2 by delta V1, delta I2 by delta V2, delta I2 by delta V2 at output only. We have calculated both of the parameter for MOS. GM also we calculated, output resistance also we calculated. For saturation region we calculated, for triode region also we calculated. Now this thing only we have to use because a MOSFET is also a two-port network only. This is also a two-port network only, right? I guess I can give a light color. इतना भी नहीं जाना भाई, ठीक है. Isn't it a two-port network? What is the input parameter? That is VGS. What is this output parameter? That is VDS. We call this as I gate. What is I gate? 0 ampere always. I gate is 0 ampere always. And what is this? We call this as I drain. I drain. So for both triode and saturation region, for both triode and saturation region, delta Ig by delta VGS. Here I should write capital VGS, not small. delta Ig by delta Vgs. What is delta Ig by delta Vgs? That is delta I1 by delta V1. Delta I1 by delta V1. What is delta I1 by delta V1? That is Y11. Y11 is equals to 0. Why it is 0? Because Ig is 0 ampere. Ig is 0 ampere. So no point of differentiation. If the current itself is 0, there is no point of differentiation. So Y11 is 0. And what about this factor? Delta I1 by delta VDS. That means delta Ig by delta VDS. Input current and divided by output voltage. This is also 0. That means Y21. What is this? This is Y12, sorry. Y12 is also 0. And this is what we needed. We needed Y11 and Y12 to be minimum. And this is what we needed. And that is satisfied for both of the region. For both of the region, it is satisfied. This is also we needed. This is also we needed. Now talking about GM. Now these two are the deciding one. Whether we should go for triode region or saturation region. So these two are the deciding one. So what do you need? You need Y21 to be maximum. Y21 to be maximum. That means you need transconductance to be maximum. So now we are going to compare the transconductance of triode region and saturation region. So delta VDS versus output current divided by input voltage. So delta ID by delta VGS for saturation and triode. We are basically comparing the GM. So GM of triode. What is the GM of triode? GM of triode is mu n COX W by L VDS. This is the GM of triode, right? You write down the current expression. You need to differentiate it with respect to VGS. So VDS square by 2 will be 0 only because differentiation will be 0. VGS minus VT will be 1 only and VDS will remain there. So this is the GM of triode region. In case of triode region, VDS is less than VGS minus VT. That means VDS is very low. Also you can see by curve as well that in case of triode, this is our triode region. So this was ID versus VDS. So in triode region, VDS was very low. Here was your VDS. So VDS is very low. So if VDS is very low, that shows that GM will be very low. GM will be very low. So GM of triode region is lesser than the GM of saturation region. Now why the saturation region GM is high? GM will be very low in triode region. In triode region. Right? Let's give this line a highlight because we are comparing both of the values. Now what about the GM of saturation region? GM of saturation region. What will be the GM of saturation region? Mu n COX W by L VGS minus VT. That's it. Just a second. So this is the GM. Now how can you comment whether this will be a large value or low value? How can you comment? How will you comment? Let's write down the ID saturation current. What is your ID set? ID set is mu n COX W by 12 VGS minus VT whole square. So here ID and VGS follows square law relation. Here ID and VGS follow square law relation. Square law relation. That means the slope will be high. Slope, what is the slope? That is del ID by del VGS will be high. How do I comment on that? Let's make a graph. ID versus VGS. So in case of saturation region, ID versus VGS follows the square law relation. So this will be the slope. This will be the slope. So let's just assume if one is y equals to x and the other function is y equals to x square. What is the differentiation of this? What is the slope here? That is 1. And what is the slope here? That is 2x. Now what if my x value is 2? So my slope will be 4. So if it is following square law relation, there is high chances that slope will be larger. If it was following cubic relation, what will be the square? 3x square. If my x value is 2, then what will be the slope? Slope will be 2, 4, 12. So if it is in the higher power, that means the slope will be larger. Are you getting this point? So ID, in case of saturation region, the relation between ID set and VGS is square law. But in case of triode region, what is ID? In case of triode region, what is ID? Some Kn, then VGS minus VT into VDS minus VDS square by 2. So here the relation is not square, here the relation is linear. So that's why the slope will be lesser. But in case of saturation region, the relation is square. The relation is square law. Okay. And follow square law relation, or you can say square relation, whatever you can write. So in case of saturation region, the relation is square. In case of triode region, the relation is linear. So since it is square relation, the GM of saturation region will be larger. So here you conclude that GM of saturation region is larger than GM of triode region. So this is concluded. And what do we need? We needed high GM or lower GM? Let's check. We needed this value y21 to be larger. We needed y21 to be large. We needed this one to be large. So we needed GM to be large. And where are we getting GM large? We are getting in saturation region. So this is one of the advantage. If we are running our transistor in saturation region, we get large GM. If we are getting larger GM, that means we can have higher gain. So this is one of the advantage. Now let's check the final parameter. Here we checked these two parameters. Here in both of the region, both of the parameters were same. So we cannot conclude. Then we checked this parameter, GM we checked. So by checking the GM, we got to know that we have advantage in saturation region. Advantage in saturation region. Now let's check the final parameter, that is del ID by del VDS. Del ID by del VDS for linear and saturation region. Linear and triode are one things only, right? Both are same. I have told this thing again and again. Linear and triode both are same only. So what is del ID by del VDS for linear region? That is del ID by del VDS. That is linear. In linear we can check, or in deep triode we should check. Deep linear we should check, right? Because we wrote the expression for deep linear, not for linear. So we can write the expression for deep linear. That is mu n Cux W by L VGS minus VT. Right? Yeah, correct. And what about del ID by del VDS in saturation? So there were two answers. One was lambda ID set if lambda is not equals to 0, and if lambda is equals to 0, it was infinity. If lambda is equals to 0, it was infinity. So there were two answers. Or by simply by the waveform also you can check what was your ID versus VDS. We are checking at the output only. So now we will draw ID versus VDS. ID versus VDS. So we have drawn the ID versus VDS previously as well. How does it look like? It looks like this. Or there are two chances, it can go something like this as well. This is linear, this is saturation. Here you can directly see that this is the slope. Let's call this slope as theta 1 and let's call this slope as theta 2. Theta 2. So here you can directly see that theta 1 is larger than theta 2. That means in linear region the slope is larger. The slope is larger. And in saturation region the slope is less. The slope is less in saturation region. That means the output resistance is high. What you are saying that delta ID by delta VDS is less. This is less. That means delta VDS by delta ID will be high, right, for saturation. So in saturation region you are getting high value of output resistance. What you can conclude? Here you can see for saturation region output resistance is high. And what did you need? You need output resistance to be high or low. Let's check here. You needed Y22 to be 0. You needed Y22 to be minimum. That means you needed Y22 to be 0. That means you needed output resistance to be high. Did you understand this point or not? In case of saturation region, what did we get to know? We get to know that our GM value is larger. In case of saturation region, GM value is larger than triode region. If GM value is larger, then that is our advantage because we wanted GM value to be large. We wanted that current source to be large, but output resistance to be as minimum as possible. We wanted our output resistance to be as minimum as possible. And output resistance should be as maximum as possible. Sorry for that. We wanted GM to be large and output resistance to be large as well, so that the output resistance doesn't eat up any current and all the current goes into the load. If output resistance is large, if this resistance is large, it will not eat up any current and all the current will go into the load. This is what we wanted. And in case of saturation region, we got output resistance to be large, also we got GM to be large. That's why we conduct a MOSFET in saturation region while we are using it as an amplifier. When we use the MOSFET as an amplifier, we use it in saturation region. So this is the answer. What will be your answer if in the interview they ask you why do, like in the interview they are not expecting you this much of analysis. This much of analysis was there just to make you understand. So in the interview you can directly say that, sir, for an amplifier I will need a higher GM value, a higher transconductance and lower output resistance. So in case of MOSFET amplifier, when we are running in saturation region, we get to see that our GM value is also higher and our output resistance is also higher. So in case of saturation region, GM value is higher than the triode region, and in case of saturation region, output resistance is also higher than the triode region. So that's why we use MOSFET as an amplifier in saturation region. That's it. So why we use MOSFET in saturation region for amplification? Because in saturation region we get higher GM and higher output resistance. That maximizes our voltage gain. That's it. Understood? So this is the reason why we use MOSFET as an amplifier in saturation region. So this was a very famous interview question. Even in the even in GATE 2023, this kind of question was asked, but in this form, in this Y parameter form. Although every time when I deal this course, whenever I teach analog electronics, every time I deal this question, and this kind of question was asked in GATE 2023 as well. They wanted to test your concept that if you know how to find the maximum gain. So for getting the maximum gain, the resistance here should be the minimum. So Y11 should be 0, Y12 should be 0. And now it is being amplified, so amplifying factor should be large. Y21 should be large. Now it is going into two resistances, so the other resistance should be large so that it doesn't eat up any current. So Y22 should be 0 so that the resistance becomes larger and all the current goes into the load. The same thing is happening in the MOS. In the MOS, for both of the region, for both triode region and saturation region, the input parameters are 0 only. So no worries about that. Let's talk about the output one. So let's talk about the GM. So GM in that triode region was lesser than the saturation region. So in triode region, GM was less, but in saturation region, GM was more. So this was one of the advantage. Then in case of linear region, your output resistance was lesser, but in case of saturation region, your output resistance was more, because here the slope is larger. If the slope is larger, that means output resistance is low, but in case of saturation region, output resistance is larger. So if output resistance is larger, that means the output resistance will not eat up any current, and most of the current will go through the load only. So that's it. So that's why we use MOSFET in saturation region for amplification. This is one of the most important answer for your interview and even for the GATE examination, because they can ask any question, right? Let's move on to the next concept. Now we have understood that we have to bias the MOSFET in saturation region. We have understood we have to bias the MOSFET in saturation region. Now how we will bias it? This is our target now. I have the MOSFET device with me, I have resistances, I have the battery. Now how will I bias it? So we are trying to bias the MOSFET. This is our first try. So will this try work? Let's check that out. Let's check out, will this try work? So what I have done here, I have given some DC voltage and superimpose AC there. I told you we will give DC supply as well, we will give the biasing as well, and then we will give the AC. So both I am giving here at the gate, and at the load I am having V naught. So here I am expecting my output. This is the output I am expecting. So this is my try one. Will that work? Let's check. Let's assume my VG is 3 volt. This Vs can be anything. It can be 20 millivolt sin omega t. Okay. Let's assume my Vt is 1 volt. This is I am assuming. So for saturation region, what do you need? 1 volt. For saturation, what do you need? Your VDS should be greater than VGS minus VT. So your VDS should be greater than, what is your VGS? VGS is 3 plus 20 millivolt sin omega t. 3 plus 20 millivolt sin omega t. This value will be nearly 3 volt only, right? Nearly 3 volt only. 3 plus minus 20 millivolt. 3 plus 0.2 and 2.98. So it will be nearly 3 volt only, right? So no need to worry about it. This is nearly 3 volt only. Minus Vt, that is 1. So you need your VDS to be greater than 2 volt. This is what you need. Now let's just assume if my transistor turns on. If my transistor turns on, what will happen? There will be some ID current flowing through it. If my transistor is on, there will be some ID current flowing through it. Then what will be your VDS value? VDS value will be minus ID into RL, which is negative. VDS value will be minus ID into RL, which is negative. You needed VDS to be greater than 2 volt. You needed VDS to be greater than 2 volt, but here you are getting VDS to be negative. So this is not desired. Not desired. So if you use this configuration, what will happen? Your transistor will not even turn on. The transistor will be in cutoff. So MOS will be in cutoff. If you use this configuration, MOS will be in cutoff. So it will not even turn on. So this is the disadvantage here, that you are not able to turn on the transistor. Are you getting this point? So now we have to make another try. So now what I am doing, I know one thing, my VGG is 3 volt only. My Vs is 20 millivolt sin omega t, right? So what VDS I need? VDS should be greater than 2 volt for saturation region. By this condition, I found out that my VDS should be greater than 2 volt. This I know. This I know my VDS should be greater than 2 volt. So what did I thought? I thought that, what did I think? I thought that I should fix VDS value. I need VDS value to be 2 volt. So I will fix it here. I will connect a battery of 2 volt. So I have fixed this. This is 2 volt battery I am connecting. So here, okay, you need greater than 2 volt. So let's assume I am connecting a battery of 2.5 volt. Here VDS is greater than VGS minus VT. So saturation is there. Saturation is there. But what is wrong happening here? What is wrong? We needed saturation region, and here I have ensured that I get my saturation region. But what is wrong here? In this configuration, what is wrong? Output is fixed. V0 is equals to 2.5 volt, which is fixed. Output is fixed, bro. But you needed the amplifier, you needed the MOS as an amplifier. So how you are saying that it is working as an amplifier? If output is fixed, how it is an amplifier? Output is fixed. That means it is not working as an amplifier. Not working as an amplifier. So this biasing is also not considered. This biasing is also wrong. In the first one, what did we get to know? We got to know that VDS is negative. And if VDS is negative, your MOS will be in cutoff. So this biasing is eradicated. This biasing is also wrong. This biasing is wrong. Why this is also wrong? Because here you have fixed the output. So what happened to this 20 millivolt sin omega t? Is that amplified? No. At output you are having fixed voltage, that is 2.5 volt. And already you are having a battery of 2.5 volt. So why do you need this MOSFET? What is the use of this MOSFET here? There is no use of this MOSFET, right? You are not even amplifying the voltage. You needed the MOS as an amplifier. So you are not even amplifying the voltage. So now I did this thing. I tried the third one. So here my output is not fixed. Here my output is this one. So this is my output. But tell me, what is the value of VDS here? Let's just call this one as 3 volt again, 20 millivolt sin omega t, with VT being same 1 volt. Now in this one, what is my VDS value? VDS value is VDD minus IDRL. Now you can adjust VDD. You have the liability to adjust the VDD such that your MOSFET works in saturation region. You can adjust VDD such that your MOS works in saturation region. Works in saturation region. So now you have the liberty to change your VDS value. So now you can change your VDS value. Also, your output is not fixed. Also, output is not fixed. So this biasing technique can be used. But again, there are some issues with that. What is that issue? That we will learn when we are studying common source amplifier. But here briefly I can tell you what is that issue. The issue is two batteries. One battery is VDD, the other battery is VGG. So you don't want to use two batteries. You have only one supply. With the help of VDD supply only, you have to bias the gate voltage as well. For drain voltage, you are using VDD. But it's not that for gate voltage I will use another supply. When you make a chip, only one of the supply will be given. You either have 5 volt or 2.8 volt or 1.2 volt or 1.6 volt, but you will have only one supply. With the help of that supply only, you need to generate other supply. Let's assume I am having 5 volt. I am having 5 volt supply. I am having 5 volt supply, but I need 2.5 volt somewhere. How will I generate that? Voltage divider. I have 5 volt, R and R voltage divider, I will get 2.5. If I need 3 volt, how will I do that? I need 3 volt. So I will do 2R, 3R. Voltage divider again, 2R, 3R. And on upper side, I am having 5 volt. So 2R, 3R, here I will get 3 volt. So with the help of one supply only, you have to generate other supply. Are you getting this point? So again, this biasing has some issue, but for now, let's just accept it. When we study deep analysis of common gate and common source amplifier, we will see that biasing technique. But for now, let's just accept this biasing technique. Well and good. So this biasing technique is accepted for now. So we have biased the MOSFET now. Now we are going to do the small signal analysis of a MOSFET amplifier. So basically, now we are going to study the small signal analysis of MOS amplifiers. So this structure cannot this structure can be replaced with something like this. Can't it be replaced with something like this? इसको ऐसे लिख सकता हूँ ना मैं. This is VDD, then I am having RL, then I am having the MOS. Look, this potential is 0, this potential is VDD. Then from VDD, RL is connected. Then at RL, here you are having the output. This is your output V0. Then you are having the MOS. The source is grounded, and here this is the input. This input we can call Vi. Vi is equals to VGG plus Vs. VGG plus Vs. So generally you will get this kind of configuration, not this kind of configuration. They will not make this big structure. They will just show it something like this. VDD, RL, V0. At Vi you are having VGG plus Vs. That's it. So this is how they will make it in the examination or in the question paper. You will see this kind of circuit only. So we will also deal this kind of circuit only. So this is our circuit. Simply VDD, RD, V0, VGG plus Vm sin omega t. So this is our input. So what is our input? This is the DC supply and this is the AC. This is DC and what is AC? AC I am calling small VGS. The AC input that I am having, this I am calling small VGS. Basically, my small VGS is Vm sin omega t. Small signal AC input. Now I will generate some ID. Now this ID is DC quantity or AC quantity, that I don't know. I will just simply write down the expression, then you will get to see something very interesting. So just hold on to the video till the last. So I will write the ID expression now. What is the ID expression? Mu n Cox W by 2L. Also, I am considering MOS to be in saturation region. I have adjusted my RD value and VDD value such that my MOS is working in saturation region. So I am considering MOS to be in saturation region. So I will apply the current of saturation region only. So mu n Cox W by L VGS minus VT whole square. So what will be my ID? Mu n Cox W by 2L. What is my VGS? VGS is VGG plus Vm sin omega t. VGG plus Vm sin omega t minus Vt whole square. So can I write it down something like this? ID is, I will again write down the expression mu n Cox W by 2L VGG minus Vt square. I am writing VGG minus Vt plus Vm sin omega t plus Vm sin omega t. Can I take out this much expression? If I take out this much of expression, what I will get? Mu n Cox W by 2L. I am taking out VGG minus Vt whole square. VGG minus Vt whole square. So I will be left with 1 plus Vm sin omega t divided by VGG minus Vt whole square. Till this point, are you guys able to understand? You guys are able to understand, right? VGG minus Vt I took out. You can take it inside as well. You will get the same thing, right? Well and good. ये एक्सप्रेशन समझ में आया ना? VGG minus Vt को बाहर लिया, यहीं पे बाहर ले लो तो 1 plus Vm sin omega t by VGG minus Vt. So VGG minus Vt whole square is getting out, and this is what we are getting. So this is the ID expression we are getting. Now one thing I know, this is very small. This is very small, right? Why it is small? Because this is a small signal. Vm sin omega t is a small signal. So this particular quantity is very small. And one thing I know, that is 1 plus x square, x whole square can be approximated to 1 plus 2x if x is very small. If x is very small, this we can do. So ID is equals to mu n Cox W by 2L VGG minus Vt whole square into 1 plus 2 Vm sin omega t VGG minus Vt. Now people will say that sir, why you are doing the derivations? This is not important for gate. But if you just understand the small signal analysis, okay, just short circuit the DC bias, just open circuit what do you say, just short circuit the capacitor, do this, do that. There is no meaning of that. There is no meaning of learning the things like that. Here I am not eating up your time. There can be other irrelevant things too, but that I am not teaching. But this is relevant to gate. If you don't know these much of concept, like from where small signal analysis is coming, then some other day they can frame a very good question where this concept will be used. From where the derivation of small signal analysis is coming. Why do we short circuit the DC bias? What is the actual need? Here I did not short circuit anything. I am just applying the simple formula. That's it. Nothing I am doing. Simple formula I am applying. We have VGG, we have Vm sin omega t. Simple formula we are applying. That's it. We are going with the simple analysis, right? So what is the ID expression you are getting? What do you think what this is? Mu n Cox W by 2L VGG minus Vt square. What do you think what this is? If in the input I only had the DC supply, if I only had the DC supply, what would be my current? If in the input, if I only had the DC supply, what would be my current? My current would be mu n Cox W by 2L VGG minus Vt square. So I can write down this is DC current, right? This is DC current if my input had only VGG supply. If my input had only VGG supply, my current would be mu n Cox W by 2L VGG minus Vt whole square. So I will write down this is IDC. This much expression is IDC. Current if only VGG was applied. VGG, or in bracket I can say DC was applied. This is my IDC, and then I am having 1 plus 2 Vm sin omega t VGG minus Vt. Now what I can write, ID is equals to, now this IDC can go inside, IDC into 1 plus IDC into this factor. So it will be IDC plus 2 into IDC VGG minus Vt, 2 into IDC VGG minus Vt Vm sin omega t. Now tell me, what is this expression? Those guys who have studied seriously, they will be able to tell what is this expression. What is this expression? This is GM. This is transconductance. What is transconductance? Transconductance we have studied 2 IDC by VGS minus VT. If I did not apply any AC signal, if I did not apply any AC signal, my VGS would be VGG only. If I did not apply any AC signal, then this VGS would be VGG only. So this will be my transconductance. So this expression 2 IDC by VGG minus VT is transconductance only. Are you getting this point? So now what you are able to replace with, that ID is equals to IDC plus, this is the transconductance GM, into VGS. Why VGS? Because at the first page I wrote that small signal Vm sin omega t, I am replacing it with the VGS. GM VGS. VGS is Vm sin omega t, which is small signal AC input. Small signal AC input. So here I got to know that in my ID expression, what I am getting? I am getting a DC component. I am getting a DC component, and along with that, in the addition, I am getting AC component. Are you getting this point or not? And what about V naught? What will be your V naught? Tell me. What will be your V naught? V naught will be VDD minus IDRD. V naught will be VDD minus IDRD. That would be VDD minus, what is ID? ID is IDC plus GMVGS into RD. What do you get here? VDD minus IDC into RD minus GMVGS into RD. Again in the V naught, what do you see? This much expression is DC component and this much expression is AC component. So what did you understand? Why this is DC component? If I had not applied any AC signal, if I had applied only DC signal, that means if my current was only DC, then what would be my output? Output would be VDD minus IDC into RD. So every small signal I am denoting by small value, GS. VGS is small. So that's why I am saying this is small signal. Like at many times you will find this VGG as written as VGS, capital VGS. But here I have wrote VGS only, VGG only. Yeah. So what I was saying, if there was no AC signal, this would be my output. And this I can say my DC output. So this is my DC output. And what is my AC output? But here I have applied both signal, DC and AC. What is my AC output? My AC output is coming out to be minus GM VGS RD. In my final AC output, my AC output is, what is my AC output? V naught AC. V naught AC. That is minus GM VGS RD. And what is my IDAC? IDAC. That is GM VGS. Now both of the expression does not have any DC component. Are they having any DC component? Are they having VDD? Are they having VGG? VGG is a DC component, VDD is a DC component. Are they having those components in their final output? Here, both of them are, I can replace it somewhere here. Here what we see is that both of them are not a component of DC, or we should not write, we should write like that, not a component of VDD or VGG, not a function of VDD or VGG. That's why we say that while doing the AC analysis, we can short circuit the DC supply. Why so? Because by the detailed analysis, what did we get to know? We got to know that in the final current, there are two expressions, DC current and AC current. In the final output as well, there are two expressions, DC voltage and AC voltage. Both AC voltage and AC current doesn't have any AC component. And what about DC component? This is the DC component. DC component is IDC, and this is the DC component. DC component is also not having any AC component. So here you got to know that both AC and DC components are independent. Although they are dependent, how they are dependent? Because if you are not even biasing, if you are not even giving the DC supply, there is no meaning of applying the AC signal. If you are not giving the DC supply, there is no meaning of applying the AC signal. This we covered in lecture 1 only. Because if you just apply AC signal, you will not get any output, because transistor will not even turn on. So for turning on the transistor, I have given the DC signal. Once the transistor is turned on, once the transistor is working in saturation region, now I can apply my AC signal, and that will be amplified. So here we are not actually applying superposition, but it is acting as if we are applying superposition. So what is the conclusion of this? That you can apply superposition. How you can apply superposition? So we will come on to this part later on, but let's just see this. So by whatever that we have done previously, from here you can break your MOSFET in two components, DC and AC. So this we call actually DC analysis, and this one we call actually AC analysis. So in DC analysis, what do? We will only consider DC sources, because in the DC output, what we have seen, in DC output only we are having DC component, and here also we are only having DC component. So we will not consider any AC component here. So VDD is the DC component. Okay, VDD will be there. RD is the simple resistance, no meaning of DC AC. Then this is the simple MOS we are having. Then at the input, I will only consider VGG, and this is my output. That's it. And in AC analysis, what I will do? Will I make VDD here? Will I make VDD here? No. Why I am not making VDD here? Because in the output, I am not getting any VDD component. Then this is the MOS I am having. Here I will write Vm sin omega t, only the AC signal, and this is my output. I will have a small id. This I am calling small id only. No, this GMVGS I can call it small id. Okay, I generally call it small id. Small id. This is the AC current. So small id. What will be my V naught? V naught will be minus small id into RD. What is small id? Small id is GMVGS. GMVGS into RD. So finally, I made this circuit, and what did I get to know? That simply using this circuit, I can do my circuit analysis. But this biasing will not work. If I am not giving any DC supply, this will not work as a transistor. This will not work as an amplifier. If I am not giving any DC supply, it will not work as an amplifier. We have to give DC supply. But after giving the DC supply, after imposing the AC signal, we did the current domain analysis. We wrote the expression of current, then we did the analysis, then we got to know that we can break down our circuit in two parts. So for analysis purpose, this is done only for analysis purpose. Only for analysis purpose. So I will write for analysis purpose. So this is how you can analyze for analysis purpose. So every time you cannot write current expressions, right? every time you cannot write these current expressions. So how will you analyze the circuits? The circuit will be given. First you will do the DC analysis. After doing the DC analysis, what you will get to know? You will get to know the value of GM. You will get to know the value of GM, because what is GM? GM is 2 IDC divided by VGG minus VT. So from here you will get to know GM, and then you will do the AC analysis. From AC analysis you will get to know the final output V0, and that is minus GM VGS RD. So VGS you already know, VGS is, this is your VGS. VGS is Vm sin omega t. GM also you know, GM is 2 ID by VGG minus VT, that you got to know from DC analysis, and RD value also you know. So then you can write down your gain. Are you able to understand this complete analysis? This everything that we have studied in MOSFET amplifier till now. What we studied? Let's start from the beginning. So in the beginning, we saw that why we use the MOSFET in the saturation region for amplification. Then once we got to know, then we bias the transistor. We tried biasing. This was our first try. Here the transistor was turning off. This was going into cutoff region. We tried this one. Here we fixed the output voltage, which is not desirable. Then we tried this one. Here we can change the VDD value as per our requirement. VDD value as per our requirement, so we can bias the transistor in saturation region. So this we have accepted. So once we accept it, then we do the small signal analysis. That large and small signal analysis both we are doing. Actually, I should not write small signal analysis. I should write large and small signal analysis. Both analysis we are doing. We are also considering the DC source. We are also considering the AC source. Then we consider both of them. Then we got to know this is the ID expression we are getting. Then in the ID expression we are having both DC and AC component. So then we got to know that AC component is not having any DC part, and DC component is not having any AC part. So you can break down your transistor for analysis purpose. You can break down your transistor in two parts like this. If you can break down your transistor in two parts like this, so in AC analysis you will not consider any DC source, and in DC analysis you will not consider any AC source. By DC analysis, first you will find the value of GM, and then by using this GM you will get to know the V0 values. Are you able to understand this complete analysis? Now everything we did here, this much of equations we have applied, all these things we did here, we could understand it with the simple graph as well. How could we understand? This is our input, VGS is our input, VGS is our input, this is VGS, which is our input. Input is some DC supply plus superimposition of AC. So this is the DC supply plus superposition of AC. Let's assume my input was VGS was VGG plus Vm sin omega t. So let's assume it was some 2 plus 20 millivolt sin omega t. So this is what we were doing, and with respect to this we will get this output. This is the ID we will get. This is the ID we will get. So in this is the final ID. In this ID, what you can see? In VGS we have DC signal and AC signal. In the final ID, what you can see? It has some DC. This is the DC. This is the DC level, and it has some AC as well. So in the output here you can see this is a combination of DC plus AC. DC plus AC. How can you find the AC signal? AC signal, and this I am calling as VGS. How you can find the AC signal? What you will do? You will find the slope at operating point. What do I mean by operating point? You will find the slope at operating point. This is the slope that you will find. This slope. Let's call this slope as theta. So your theta will be del ID by del VGS. At operating point you are finding. What is operating point? Operating point is this DC value, VGG. This point is VGG only. This point is VGG. So at operating point, at VGG, you will find this value. That is your GM only. So you will find this GM. If you multiply GM with VGS, what do you get? GM with small VGS, what do you get? ID. You will get AC output current. What I am saying, you find the slope and then you multiply that slope. That slope is GM only. You multiply that slope with VGS. What do you get? You get the AC output signal. Look, this ID is having IDC, which is DC, plus some AC signal. DC value you will get by VGG, you can get the DC value. But the thing is how we will get AC output. So for AC output, you get the slope on this point, because this point and this point all are very nearer. All these points, these 3 points are very near. 20 millivolt is a very small quantity, so all are very near. So at that particular point, you find the value of slope. That slope gives you dial ID by dial VGS, that is GM. If you multiply GM with VGS, if you multiply GM with small VGS, this small VGS, you will get the AC signal. So this AC signal would be GM into this small VGS. You find the slope and then you multiply this magnitude. This is VGS. This is your VGS. You found the slope and you multiply with VGS. That will give you the AC output. Are you getting this point? And this we call small ID. If you did not understand by this analysis, there is no need to worry. This analysis is also good enough. But you don't need to remember this analysis. Just you need to understand one simple thing, that is, if you see any configuration, you can break it down in two parts, DC and AC. Now you will not call this as superposition theorem. I have seen many educators calling this as superposition theorem, that you are applying superposition theorem. That is completely senseless. This is not superposition theorem. When we write down the expression, we got to know that we can break it in two parts, DC and AC part. So for analysis purpose, I can separately treat DC analysis and I can separately treat AC analysis. So in DC analysis, I will not consider any AC part, and in AC analysis, I will not consider any DC part. So this is how I can break it down. Are you able to understand? And this analysis, I will again tell, at one particular point you find the slope, that is GM. If you multiply the GM with VGS, what do you get? You get the output AC current. That's it. Are you getting this point? The slope into the y-axis value. Sorry, the slope into the x-axis value. What it will give you? Y-axis value. Slope into x-axis. What is slope? Slope is y by x into the x value. It will give you y-axis value. That's it. So slope into the AC signal will give you output AC signal. Slope into input AC signal will give you output AC signal. This is what we are getting. So your output current is GM-VGS. That you need to remember. Your output current is GM-VGS, where your VGS is small signal AC input. Are you able to understand this point? Now we will see the small signal model of MOSFET. So then we will see the small signal model of MOSFET, and then we will see the small signal model of NMOS and PMOS. And then we will see the concept of port impedance, and after that we will move on to common source amplifier. So these things are left to study. I thought I will be able to cover it up in this lecture only, but I don't think I will be able to cover it up. So in the next lecture, we will see the small signal model of MOSFET in case of PMOS as well, in case of NMOS as well. And in one line only, you will be able to solve every configuration in one line. This is my guarantee, in one line. So just you are watching the lectures from beginning. So I hope you are understanding what kind of depth we are covering. So in one line only, you will be able to understand all the circuit. You will be able to understand the complete language of the question, right? So let's meet in the next lecture. We will study a lot of things. Thank you. Hi everyone. So in the previous video, we have seen the DC and AC analysis of our MOSFET amplifier. So we saw that when we are analyzing our MOSFET amplifier, we can break it into two parts, DC analysis and AC analysis. When we are doing the DC analysis, we will not consider any AC sources. And when we are doing the AC analysis, we will not consider any DC sources. That's it. So that we are going to write. So now we are going to study small signal model, but before that I will tell you what we need to do. So when you are doing the AC analysis, what you will do? You will nullify all the DC sources. What do you mean by nullifying? If you have studied the network analysis, what do you mean by nullifying? Nullifying means your voltage source will be replaced with the short circuit. Voltage source will be replaced with short circuit. So voltage source is shorted. Better I should use this line. So by this you will understand, right? Voltage source will be short circuited, and what about current source? Current source will be open circuited. Nullifying means zero. So if voltage is zero, that means short circuit. If current is zero, that means open circuit, right? So voltage source will be short circuited, and if current is zero, that means open circuited. This is current, it will be open circuited, right? and generally the coupling capacitor will be shorted. Generally this happens, the coupling capacitor gets shorted and parasitic capacitance are open circuited. We will study about it when we study the frequency response. We will study about it deeply. So generally coupling capacitors, if you see any capacitor in the circuit, that will be shorted while doing the AC analysis. While doing the AC analysis, the capacitor will be shorted generally, but when it will not be shorted or when it will be open circuited, that we will see when we study frequency response. So for now you have to consider that whenever you see a capacitor, while doing the AC analysis you will open circuit it. Sorry, while doing the AC analysis you will short circuit it. So coupling capacitor will be shorted. So simply a capacitor will be replaced by a short circuit. This is the capacitor. This will be replaced by short circuit. Well and good. And while doing the DC analysis, what you will do? You will nullify all the AC sources. We have seen here when we do the DC analysis, what we do? We nullify all the AC sources. So voltage source is shorted. Here voltage source is shorted. AC voltage source is shorted. That means it is 0. So only VGG is left. And in this one, DC voltage source is shorted. That means this VGG is 0. So only AC source is there. That's it. This is what you need to do. While doing the DC analysis, AC voltage source will be shorted. While doing the AC analysis, DC voltage source will be shorted. And while doing the DC analysis, what you will do? While doing the DC analysis, coupling capacitor will be open circuited. The capacitors will be open circuited, not short circuited. It will be open circuited. The coupling capacitors will be open circuited. These are the capacitors. So they will be open circuited, not short circuited. Open circuited. So this coupling capacitor is shown by CC. CC. Here this will be shorted, it will be open circuited. Well and good. Let's see the small signal model now. So what we are seeing the small signal model. Small signal model. So we will see 3 kind of models and then I will tell you what kind of model we are going to use. So 3 kind of model we will see one by one. So this is an NMOS. Listen to me very carefully. What we are seeing? Small signal model. That means we are going to consider only small signal. Now we are studying small signal model. So we are going to consider only small signal. So I am assuming I have applied a small VGS. I am assuming I have applied a small VGS across gate to source. This is my small signal voltage, small signal input, small signal voltage. I can say small signal voltage. We are doing the small signal analysis. Even this VDS will also be a small signal. Although I will not write it, but if you are doing the small signal analysis, every signal present in the circuit will be small signal. Your current will also be small signal. Your voltage will also be small signal. So if you apply a small signal voltage, what is the current that flows? Tell me. What is the current that flows? If you apply a small signal VGS voltage, what is the AC current? Here we have seen the magnitude. That was GM VGS. That's it. This is you need to remember. This is what you need to remember. Very, very important. If you apply a small signal VGS voltage, what is the current that flows? GM VGS. That's it. If you apply a small signal VGS voltage, there will be a current that is GM VGS. So this is what we are going to show. If you apply a small signal voltage between gate to source, there will be a GM VGS current flowing from drain to source. If you apply a small signal voltage VGS between gate to source, there will be a current flowing GM VGS that will be from drain to source. Say yes or no. And this current will certainly be 0 because I have told you gate current is always 0 ampere. So this is what we need to show and this is how we show it. I am applying a voltage from gate to source. This is my gate, this is my source. I am applying a small signal voltage that is VGS. My current flows from drain to source. This is my drain and since I have shorted them, so this will be source only. So current flows from drain to source, that is GM-VGS. Now go to the first page of our MOS physics. Now we have connected it. Go to the first page of our MOS physics. What did we want? We wanted a dependent current source and this is what we have got. If you apply a VGS, you are getting GM VGS. That's it. This is what we wanted. Say yes or no, right? Yeah. Screen lag नहीं करना ना. I don't think screen is lagging. Is it lagging? Not lagging. Yeah. Okay. So GM VGS current we are getting. One thing we are forgetting. What is that? Output resistance. We should not forget output resistance. R naught. Our op-amp is working, not our op-amp, our MOSFET is working in saturation region. In saturation region, there is a R naught. If lambda is not equal to 0. So that R naught we should not forget. So R naught also I will put here. Just a second. This is the R naught. Here lambda is not equal to 0. If lambda is 0, this R naught will be infinity. Why we are putting this R naught? Because our MOSFET is working in saturation region. If it was working in linear region, we would have put a capital R on. The value is different. What is the value of this small R naught? If you remember, never forget this value. This is very important. What is the value of this small R naught? That is 1 upon lambda ID set, but ideal one. 1 upon lambda ID set, but ideal one. That's it. This is the value of this R naught. Well and good. So this is what we are saying. This is the first model, which is known as pi model, and we are not going to use this one. This is generally used by a lot of aspirants, but once you see the big circuit, this will create complexity. So we are not going to use this one. So which one we are going to use? T model. No, we are not going to use T model as well, but we will see it because that is important. So what do we see in T model? Here I am drawing drain. So one thing I know, that from drain GM-VGS current is flowing, that I know. So I can say that from drain GM-VGS current is flowing. From drain to it is going towards source. So but I know this thing that from drain GM-VGS current is flowing. GM-VGS current is flowing. Let's assume I call this one as gate. From gate there is no current, I know one thing. And let's assume this is my source. This is my source. So let's connect this. So tell me one thing. This is my small VGS voltage, right? Between gate to source. This is my small VGS voltage. And I know one thing, that is here GM-VGS current is flowing. Here GM-VGS current is flowing. I have applied VGS voltage and I know the current GM-VGS. What will be the resistance here then? The resistance will be 1 by GM. And the current in the complete path, this is the complete current, that is GM-VGS. The complete current flowing is GM-VGS. And one thing we cannot forget, that is between drain to source we will have an output resistance. Between drain to source we will have an output resistance. इसको थोड़ा छोटा करना पड़ेगा एरो को. हो जा भाई. ओके, दूसरा ही ड्रॉ कर देते हैं. So this was the current GM-VGS, and between drain to source we are having a resistance which is R naught. This we cannot ignore. So what did you understand here? That drain, gate and source, I have VGS. Between gate to source I have VGS potential, and I know there will be GM-VGS current flowing. So what will be the resistance? That would be 1 by GM, because voltage upon resistance is the current. So current is GM-VGS. Voltage upon resistance is the current. So the resistance would be 1 by GM. And from drain I know GM-VGS current is flowing. That's it. This is what I did. And between drain to source I have a resistance R naught. So this is the second method. We are also not going to use this one. So what we are going to use? We are smart. We are not going to draw any model. We are never going to draw any model in the examination, even in the interview. So what we will do in the interview or in the examination? The MOS will be there. So I will keep MOS as it is. Here there is gate. There is this source. I know there will be some potential here. Whatever the potential is there, the potential is VGS. Whatever the potential is there, we are going to make a current GM VGS like this. Because we know whatever the potential is there between gate to source, the current flowing would be GM VGS from up to down. That's it. And one R0 resistance we will connect. That we will remember. And we will also remember one thing. What is that? That this current is 0. This current is 0 ampere. We will see gate to source. We know if VGS potential is applied, GM VGS current will be flowing. Between drain to source, I have R0 resistance. That's it. No model, nothing like that. There will be big circuits. Nothing will happen. I know one thing. If I am having VGS potential, GM VGS current will be flowing and R0 resistance will be there. Tell me one thing. If gate and source are shorted, then what will happen to the MOS? If gate and source are shorted, somehow gate and source are shorted, then what will happen in the MOS? Tell me. MOS will be open circuited. Why so? Because VGS will be 0. If gate and source are shorted, then VGS will be 0. If VGS is 0, that means current is 0. So this GM VGS current will be 0. So only R0 will be left. Only R0 will be left. So this complete MOS will be open circuited. Are you getting this point? So like that we are going to analyze. We are not going to draw these kind of complex circuits. We are not going to draw anything. We will just remember, okay, this potential, current, GM VGS, that's it. And R0 resistance at the outside. Same thing we are going to do for PMOS. So what do you do for PMOS? Between source to gate you are having a source will be the common one. Source will be the common one. So here source is at higher potential and gate is at lower potential. So VSG potential we will have. Whatever VSG potential you are having, whatever, this is source, this is gate. So whatever VSG potential are having, based on that potential, between source to drain you will be having a current. Between source to drain you will be having a current. That is GMVSG. GMVSG. Look, from where the arrow is getting out now, that is at higher potential. Or wherever the arrow is, that will be at lower potential. Here where the arrow is at gate, so that will be at lower potential. Here where the arrow is, this is at source, so source is at lower potential. That's it. So GM VGS in case of PMOS and GM VSG in case of GM VGS in case of NMOS and GM VSG in case of PMOS. Source to gate, GM VSG, this potential. So current will be from source to drain. The current will be from source to drain. And the resistance is R0. Between source and drain, the resistance will be R0. That's it. What will be the second model? Here I have the VSG potential. That means if I have the VSG potential, that means here the resistance will be 1 by GM. This is source. So here I am having VSG potential. This is gate. Let's assume this is gate. This is gate. So here I will be having 1 by GM potential. This is gate. The current I know is 0 ampere. Why the resistance is 1 by GM? Because I am having VSG potential here. And from source to drain I am having GM VSG current. Now some people may get it out. Some people may get it out. Sir, why are you not drawing 1 by GM resistance here? Why not that? Think about it. Why I am not drawing 1 by GM resistance here? Sir, you can say, sir, 1 by GM resistance can be here as well because GM VSG current is flowing. Why did I make this 1 by GM resistance here? Because I am having VSG potential here. Here you are not having VSG potential. You can't say this potential is VSG. No, this potential is VGD. So if you are having VSG potential, then only you can draw 1 by GM resistance. Here you know one thing that in gate, here you know one thing that is in gate GM VSG current is flowing. That's it. This is what you know. Nothing else you know. You don't know any potential or anything. Are you getting this point? And why it is GM capital VSG, it is small VSG. Are you getting this point? GM VSG current is flowing. Now you can't say, sir, I will get to know some potential here, GM VGD. If I know the potential, then I can draw some resistance here. But the current is depending on VSG, not VGD. If the current was depending on VGD, you could have drawn the resistance. If the current here, this current would have been GM VGD. If this current would have been GM VGD, then you would have drawn 1 by GM resistance here and GM VGD current source here. Are you getting this point? If the current was GM VGD, then across VGD potential 1 by GM resistance would have been there, and from source GM VGD current source would have been there. But here we only know the VSG potential, and the current is depending on VSG potential. So my current is GM VSG. So VGD potential has nothing to do. So you can't make it as a resistance. So some people may have a doubt. Although whenever teacher explain this model, they don't give this much of logic. They directly make, okay, 1 by GM will be there, GM VSG is there. But here now you have understood all the complete logic, why we are making a resistance, why we are making a current source. Well and good. And between source to drain, I will be having a resistance R naught. But is that the model we are going to use? No, because we are smart enough. What we are going to use? We are simply going to use the given MOS circuit only. Look, if you are studying for the first time, it may seem like very much difficult or anything. Okay, how will I remember all these things? But once you solve the problems, you will be habitual. You will be very much habitual with all these things. Like this is gate. By the arrow sign only, you will write, okay, this will be source. So from source to gate, okay, so there will be this current GM VSG. That's it. And this is the potential VSG. And this is R naught. This is R naught. This is drain. That's it. This is what we are going to use. I know one thing, based on the potential applied, I can write down the current, and if the current I know, then there is a resistance R naught connected to that. That's it. Understood? Well and good. So these are the two models which is very important. Based on these models only, your complete next chapters are based. So this is the most difficult part of MOSFET amplifier. As per the student, we will make it very, very easy, that within seconds you will be able to answer a lot of big circuits, right? So yeah, let's move on to the next. Like we are going to solve the questions now, but before that I want to give you a concept of port impedance. Like if you haven't studied the network analysis, then it will be used. If you have studied the network analysis, you already know what is Thevenin resistance. What is Thevenin resistance? Considering all other sources shorted, we find the resistance at a particular node. That is Thevenin resistance, and this is what we are going to do in the port impedance. Like they will give you a circuit, like in the examination, what you will see, like this circuit will be given, and they will ask you what will be the resistance from this side. They can ask you these kind of questions. What will be the resistance from this side? So how will you find those? So what you will do, you will first put all the independent sources to 0. That means you will nullify all the independent sources. Current source will be open circuited, voltage source will be shorted. That's it. Current source open circuited, voltage source shorted. Then you will apply Vx here. Let's assume I was supposed to find resistance at this side. So apply Vx here and get Ix out of it. My resistance would be Rx by Vx. That's it. Did you get it? Let's assume in this question I was asked to find Rx here. I was asked to find Rx here. So what I will do, I will put all the independent sources to 0. Then I will apply Vx here and get Rx out of it, Ix out of it. So my Rx would be Vx by Ix. That's it. Understood? So these kind of questions will be asked. Let's understand it with an example. It will be more clear to you. They are asking you Rx from here. What will be the Rx? What will be the Thevenin resistance? Rx port impedance is same as the Thevenin resistance only. So what will be the Thevenin resistance? R1 parallel R2. But let's solve it with that method. So what we are doing to do? What we are going to do? This will be shorted. All the independent sources will be shorted. I should not put it as Vx. V is fine. So all the independent sources will be shorted. So this will be shorted. So R1 will come in parallel to R2. R1 is parallel to R2. Now you are asked to find the resistance from here. Here you can directly see it is R1 parallel R2, or what you can do, you can apply Vx potential. You can apply Vx potential and get Ix out of it. So Vx by R2 plus Vx by R1 is equals to Ix. So Vx by Ix, which is Rx, is equals to R1 parallel with R2. That's it. Right? Now in this question they are asking you Rx from here. What you will do? You will apply Vx here and get Ix out of it. Okay, let's make it more interesting. Let's make this question more interesting. This question was given to you and you were asked to find Rx from here. Now people will have a doubt, sir. What we will do? First we will short circuit this V. If the V is shorted, then what we will do? What did I tell you? What is the first step? Make all the independent sources equals to 0. The V should be shorted. Then what was the second step? That apply Vx and Ix. Wherever it was asked to find, apply Vx and Ix. If this is shorted, then how do I apply Vx and Ix? So yeah, this is the thing. Like if you are finding the resistance at the input side, you have to consider the Vx source input only. The Vx source that you are going to apply, that will be the input only. Because if input is shorted, if input is gone, then how will you apply any voltage source here? Did you understand this point? So if I short circuit this, I am not able to apply any input source. So this is the input source only. This I can make as Vx. So this will be my Vx, and from here I will be getting Ix out of it. Or just think that simply forget this. There was no voltage source, nothing was there. If you are asked to find at the input side only, forget about any other source. There was no source. Just apply Vx and Ix. That's it. Or just consider the input as a source only. Input as the applied source only. You are going to apply Vx and Ix. You consider the input as the applied source only. Got my point? So Vx and Ix is flowing out of it. R1, R2. So Rx would be, what will be Rx? Vx by Ix, that is R1 plus R2 only. That's it. Right? R1 plus R2. Let's come to this question now. Now these kind of questions are considered to be tough as per the gate aspirant. They think, okay, what kind of amplifier it is? Do I remember the expression? Nothing, no need to remember anything. We know simple concept. What we are asked to find? We are asked to find the resistance from here. What we will do? Short circuit the independent sources. Vin is the independent source. I will short circuit it. So if I short circuit it, what I will get? This is shorted. and VDD will also be shorted. VDD will also be shorted, right? No sources are there. VDD is the DC supply, okay? VDD is the DC supply. And you needed to find Rx from this terminal. So what you will do, you apply a Vx here and get Ix out of it. You apply a Vx here, get Ix out of it. Now people will have one doubt, sir, you have short circuited the gate. Now the transistor will not even turn on. This is the doubt people may have. But you don't need to think about it. You don't need to think about it. Why so? Because you have applied this Vx. You have applied this Vx. This potential is 0, this potential is Vx. So what is your VGS now? VGS is minus Vx. VGS is gate to source is minus Vx. So what was the current? GM VGS in this direction. This was the current. The current that was supposed to flow was GM VGS. And VGS is minus Vx. So what will be the current? Current will be flowing upward. The current will be flowing upward. That would be GMVX. Did you understand this point? Now people will say, sir, how the current can flow from source to drain? It cannot flow. In an NMOS, how the current can flow from source to drain? It cannot flow. I know that. It cannot flow from source to drain. But this is the small signal analysis. Here I should have written small signal resistance. Small signal resistance. Small signal resistance. Find the small signal resistance. This we are doing the small signal analysis. In the MOSFET, there are VDD, there are VGG as well. Here also VGG is also given. So this is just the analysis. It's not that VGG is gone. VGG is there, but for the analysis purpose we are doing this. Are you getting this point? They asked us to find the small signal resistance. In the Vin, you are having VGG as well, even the AC signal as well. What was the AC signal? Vn sin omega t. Both you are having. But for the analysis purpose, what did you do? You short circuit them. But now it's not that if you short circuit them, the transistor will be in cutoff. No, the transistor will be there as it is. But for the analysis purpose, we are doing. So you don't need to think that transistor will be in cutoff now. No, the transistor will not be cut off. You are doing the small signal analysis now. What you need to think only? You just need to think that there will be VGS current here and R0 will be there, which I have already drawn. That's it. This is all you need to think. VDD is shorted, Vin is shorted. So what will the current? Current will be GMVX, upper side. Did you understand this point? The current was supposed to flow GMVGS like this, GMVGS, GMVGS. But what is happening? VG is 0 and source is at Vx potential. So the current is in the downward direction, the current is minus GMVx. So in the upward direction, current would be GMVx. That's it. So the current is flowing GMVx in the upward direction. And this current flow is flowing like this. Now you can apply nodal analysis here. Nodal analysis at this point. So I am applying nodal at Vx. Nodal at Vx. So Vx by R0, this current Vx by R0, upper side, Vx by R0. This current is upper side Vx by R0 plus GMVx is equals to Ix. Are you guys agreeing to this point? Vx by R0 plus GMVx is equals to Ix. Say yes or no. Now tell me one thing. People can think that, some people can think that, sir, this GMVx current will be flowing through this R0. So why cannot you say GMVx is equal to minus Vx by R0? Are you guys having this doubt? If you are having this doubt, what I will say, forget it. You should not have this doubt. Why so? Because this current will not be equal, because here there is ground. So even the ground can eat up some current. What is the current ground is eating up? That is GMVx plus Vx by R0. The ground is eating up this much current. So there is ground. Okay, if this ground was not there, then the current would have been the same. But there is ground mentioned. So the ground can eat up the current. So how much current the ground is eating up? That is GMVX plus Vx by R naught. So do not have these kind of doubts. But I have seen some people having these kind of doubts. So that's why I am taking all the doubts here. Right, since the course is recorded. So if you are having the doubt, you can comment down. Certainly I will answer, or you can ask in the Telegram group by screenshot or anything, or you can note down. We can have the session. So we can certainly answer all the doubts, but here I am addressing all the common doubts which I have already faced from the students. Right. So yeah, GMVX current, Vx by R naught current is equals to Ix. So what is the resistance you get? 1 plus Gm R naught by R naught is equals to Ix. Is equals to Ix. So Vx by Ix, that means Rx we are getting R naught upon 1 plus Gm R naught. R naught upon 1 plus Gm R naught. Right. Okay. This is the Rx we are getting. Now tell me one more thing. First let's remove this. If this was the scene, that R1 was here, R2 was here, and I was applying Vx here and I was getting Ix out of it. So what did I write? Vx by R1. I knew one thing, answer would be R1 parallel R2. Here the answer would be R1 parallel R2. I can directly see. But what did I write? Vx by R1 plus Vx by R2 is equals to Ix. So my answer was this resistance parallel with this resistance. R1 parallel with this R1 parallel R2. If I am writing Vx by R0 plus Vx by 1 upon Gm is equals to Ix. Isn't it the same? Vx by R0 plus Vx by 1 upon Gm is equals to Ix. So what will be my resistance? R0 parallel with 1 by Gm. Say yes or no. Right? So you can call this resistance as R0 parallel 1 by Gm. So the resistance that you have wrote, that would be R0 parallel 1 by Gm. So the other answer would be Rx, that would be 1 by Gm parallel R0. That's it. This is the answer. First thing we got to know, sir, gate is short there. That means the current will not be zero. Why the current will not be zero? Because we are doing the analysis, we are doing the AC analysis, we are doing the small signal analysis. It's not that we have eradicated the VDD, we have eradicated the VSS or VGG. We are just doing the analysis for the analysis purpose. Like we have to find the resistance. They are there only. But if they are asking the small signal resistance, this is how we need to do it. So Ix, Gm Vx, Vx by R0 current, right? And Ix current is flowing there. So Vx by R0 plus Gm, Vx by R0 plus Gm Vx is equals to Ix. So Vx by Ix is R0 parallel with 1 by Gm. Now you will remember it for the rest of the time. How will you remember it? So if in the NMOS, if you see from downward, if you see this arrow, this arrow will be replaced by 1 by Gm. This is grounded. Here this is grounded. This arrow will be replaced by 1 by Gm. So 1 by Gm parallel to R0. That's it. What I mean to say, if this is the scene, what you need to remember, let me write it down. Whatever that you need to remember, here I will write. If this is the scene and they are asking you, what do you see from here? What do you see from here? You are doing the small signal analysis. What do you see from here? You see from here that is 1 by Gm. That's it. If they are asking from the arrow side, you are seeing 1 by Gm. That's it. The resistance will be 1 by Gm. So this is what you need to remember. You can remember this small thing, right? Because again and again it will be used again and again in your analysis. That you need to see from downward, you see 1 by Gm. The condition is this should be shorted. That is the condition. This should be shorted. The complete analysis I have given here, and if this is also shorted, so from here you see 1 by Gm parallel with R0. Right? So let's not write it here. So what do you see? What you will say? Sir, I will say from source to ground I see 1 by Gm. What do you say? From source to ground I see 1 by Gm. That's it. From source to ground I see 1 by Gm. This is what you will say. From source to ground I see 1 by Gm. Right? From here 1 by Gm, or you can simply derive it as well, because if you are applying Vs potential here, what will be the current flowing upward? That would be Gm Vx. So Gm Vx is equals to Ix. So what is your Vx by Ix? That is 1 by Gm. But the condition is this gate should be grounded. Then only you can see 1 by Gm. Right? Or in the small signal model as well, here in this small signal model, from here we are asking. So what is that? 1 by Gm only. Right? So only the basic thing that you need to remember, that is from source to ground you are seeing 1 by Gm. Say yes or no. Agreed? Very good. Now find the resistance from looking from this terminal. Small signal resistance. Again, this is small signal resistance. This you need to answer on your own. What do you think? What will be the answer? This is PMOS. This is not NMOS. This is PMOS. So what will be the answer? 1 by Gm parallel with R naught only. Why so? Because what will be the condition now? This will be the condition that this will be shorted. This will be shorted. This is also grounded. This is R naught. What you need to do? You need to apply a Vx and get Ix current out of it. So this is Vx. This Vx will also go here. The potential is, what is the current downward? The current downward is Gm Vsg. The current downward Gm Vsg. From here to here. Potential is from here to here. Here what is the potential? From here to here. Right? The side at which the arrow is given, which is at lower, that is at lower potential. So Gm Vgs and here Gm Vsg. So the current was Gm Vsg. So Gm Vs is at potential Vx and gate is at 0. So what will be the current? Gm Vx. So the current flowing downward is Gm Vx. The current flowing downward is Gm Vx. Right? And what is the current flowing here? This potential is also Vx. The current flowing downward is Vx by R naught. So Gm Vx plus Vx by R naught is equals to Ix. Tell me what will be the answer? Rx will be 1 by Gm parallel R naught. This is the same circuit, same as PMOS. Nothing different is there. Same as NMOS, sorry. This is the same circuit only, but here you feel like something different is there. This is the same circuit only. So here what did you understand? That if an PMOS is given and they are asking you for a resistance. A PMOS is given and they are asking you for a resistance from here. So what do you see? You will say from source to ground I see 1 by Gm. That's it. From source to ground I see 1 by Gm. And if there is parallel R naught, then that will also be included. From source to ground I see 1 by Gm. That's it. Here from source to ground I see 1 by Gm, 1 by Gm, and then R naught is also there parallel with R naught. Here what do you see? From source to ground I see 1 by Gm, 1 by Gm parallel with R naught. If you remember only this much of thing, your problem will reduce to very small part. Otherwise you will have to make very complex circuit. Just from source you need to see the resistance. From source you always see 1 by Gm. That's it. The condition is gate should be grounded. From source to ground you always see 1 by Gm. That's it. From source to ground you always see 1 by Gm. Well and good. Let's move on to the next question. So I know I have not teach you common source amplifier, common gate amplifier, common drain amplifier. Nothing has been taught. But only by using the concept that we have studied till now, we can analyze any kind of amplifier. So this kind of circuit is given. Here there is Rs, R naught, 3 volt, minus 3 volt, Vs is given, V naught is given. So Vs is the small signal source. The DC supply are plus 3 and minus 3. R naught is also there, W by L given, Vt is given, mu n. You have to find the R naught value such that quiescent drain voltage is 0. Quiescent drain voltage. What do you mean by quiescent drain voltage? That is known as actually Q point, or you can say DC. Whenever quiescent is given, that means they are talking about DC. DC. Quiescent drain voltage is 0. So DC drain voltage should be 0. So only you are going to consider DC source. Vs is the small signal source. There is no VGG is applied. There is no VGG. In case of input, what we were applying previously, we were applying V in. V in was our VGG plus small signal voltage. But here there is no VGG. But will the transistor turn on? Yeah, it will turn on. Why so? Because minus 3 is there. So your capital VGS would be 3 volt. Gate is at 0 potential, but source is at minus 3. So first you need to find the DC drain voltage. So first we will do DC analysis. So in DC analysis, I will not consider any AC source. I will only consider DC source. So DC source is 3 volt. That is connected to R naught. R naught is simply an element. So nothing it has to do with DC or AC. Then I have the resist. I have this, which is minus 3 volt. This was our V naught. And here I was having RS. And Vs is 0. Small signal, because this is small signal source, that means it will be AC. If they are writing small signal source, they need not to mention AC. You have to consider by your own that it will be AC only. It's not necessary that they will write it is going to be AC. You have to consider by your own that this is AC only. So consider this is AC only. So this is shorted. Right? What is the current here? 0 ampere. The current in the RS resistance is 0 ampere. So there is no meaning of this RS, because RS will have 0 voltage drop. Right? RS will have 0 voltage drop. So there is no meaning of RS. You can remove the RS. Now what will be the current here? That will be capital ID, or you can write IDC. Capital IDC. What that current will be? Capital IDC would be, here one thing should also be written, or is that necessary to be written? No, that is not necessary to be written, because they are asking the drain voltage should be 0. If drain voltage is 0, that means this potential is 0. Then what will be your VDS? This potential is 0. So VDS will be 3 volt. What will be your VGS? VGS will also be 3 volt only, because this potential is 0. Here you can see, or okay, on next page I should write. What is your target? What is your target? Target is your V naught should be 0 volt. So if V naught is 0 volt, then what will be your VDS? What will be your VDS? 3 volt only. What will be your VGS? This is gate which is at 0, source is at minus 3. VGS is 3 volt. What is VT? VT is 1 volt. So what is V overdrive? That is 2 volt. So here VDS is greater than V overdrive. That means this is in saturation region. So you will apply the saturation region current equation only. So that will be mu n. Have you forgot the equation? No, we should not forget the equation. VGS minus VT whole square. So what is the value of mu n CX W by L? That is 100 micro by 2. VGS, what is the value of VGS? 0 minus 3, 3 minus 1 whole square, that is IDC. So IDC you get is 4 200 micro ampere. This is the IDC we are getting. Your target is to make the V naught equals to 0. So what is your V naught? V naught is equals to 3 minus IDC into R naught, and that should be equals to 0. So IDC into R naught should be equals to 3. So R naught should be equals to 3 by IDC, which is 200 micro. From here R naught will be equals to what? This will be 10 to the power minus 4. So 10 to the power 4 will go up. 35. 15 kilo ohm. R naught will be 15 kilo ohm. Say yes or no. Did you understand this point? Did you understand this question? So in the first question, they asked us to make the DC drain voltage equals to 0. Coefficient drain voltage equals to 0. So we have to do the DC analysis. They have mentioned that Vs is a small signal AC source. So Vs is gone. 3 volt and minus 3 volt will remain there. So RS will have 0 current. So 0 voltage drop. There is no meaning of RS. So forget about RS as well. Our target is to make V0 equals to 0. So V0 is 0, then our MOS is in saturation region. Then we found out the current was 200 microampere. We needed to make VDS equals to 0, 3 minus IDC into R0 equals to 0. Now people will say, sir, it will have some AC component as well. Yeah, it will have AC component, but they are talking about DC only. So we have done that DC analysis only. In the next question, they are asking small signal voltage gain. They have mentioned small signal voltage gain. Small signal, that means small signal means AC. Whenever you find small signal, they are asking AC. So now we are going to do the AC analysis. So in the AC analysis, we will not consider any DC source. AC analysis. We are going to do the AC analysis. So this 3 volt will be grounded. 3 volt is gone. Then you are having the R0 here, which we have already found 15 kilo. Then you are having this MOS. Then you will be having Vs here. Okay, I will make it like this. Vs Rs. Now since Rs is having 0 ampere current, so this particular node will be Vs only, right? And this 3 volt minus 3 volt will also be grounded. Here it was 3 volt, here it was minus 3 volt, both are grounded. And this is your V0. You need to find V0 by Vs. This is you need to find, right? This is what you need to find. This potential is Vs only. Well and good. So what will be the current here? Tell me. The current will be Gm VGS. What is the value of VGS? Small signal analysis we are doing. What is the value of VGS? That is Vs only. Vs. This potential. You are finding VGS. What is the potential of VG? Gate voltage. That is Vs. What is the potential of source potential? That is 0. So Gm Vs current is flowing. Now this Gm Vs current is flowing here as well. The same Gm Vs current is flowing here as well. So what will be the value of V0? V0, this I am calling, this was R0 only, no? This was R0, right? This was R0. So what will be the value of V0? That will be minus Gm Vs into R0. Current into resistance, that's it. Minus Gm Vs into R0. So your V0 by Vs is, since this is 0, this will be negative, right? Current is flowing, current always flow from high to low potential. So this V0 is low potential. So V0 by Vs. Current always flow from high to low potential, but in a resistance. I need to make the statement clear. The statement that current flows from high to low potential, that is wrong. I hope you have studied this in network analysis. Since we are discussing this just as small topic, like if this is 5 volt, this is 5 ohm resistance. What is the current flowing? 1 ampere, right? Now people say the current flows from high to low resistance. Sorry, high to low potential. What is the potential difference here between these 2 points? 0 volt. What is the current flowing? 1 ampere. Even if there is 0 volt potential difference, current is flowing, that is 1 ampere. The current flows from high to low potential in a resistance, in an element, right? Yeah. So this was not a matter of concern, just I explained a small point. So V0 by Vs is our minus Gm R0. This is our answer, but we know the value of R0. R0 we have, but Gm value we don't have. How we will find? What is the formula of Gm? Gm is a DC parameter. What is the formula of Gm? The formula of Gm is mu n Cox W by L V capital Gs minus Vt. Here you cannot do the mistake of writing small VGS. It is capital VGS because GM is a DC parameter. I did not even talk about small signal model when we were studying GM, right? I told you even during the derivation. Let's see the derivation. Let's get back to the lecture and see the derivation. So when we derived it here, what we replaced with GM? What we replaced? We replaced this one as GM, right? IDC is a DC parameter, VGG is a DC parameter, VT is a DC parameter. Complete GM is a DC parameter. Although it is used in AC analysis, but it is a DC parameter. So while finding the GM value, you have to do the DC analysis. So for finding the GM value, you have to do the DC analysis. Are you getting this point? But on the previous page only, we have done the DC analysis. So from there, we can pick the values. So what is the value of mu n CXW by L? That is 100 micro. What is the value of VGS minus VT? VGS was 3 volt. Because we have to pick the values from DC analysis because GM is a DC parameter and VT is 1. VT is 1. So GM would be 200 micro Maho. 200 micro Maho. So GM is the opposite of resistance, transconductance it is. Opposite of resistance. So GM is 200 micro Maho. So here we can put the values now. Minus 200 micro is 10 to the power minus 6 into 1.5 into 10 to the power 4, right? This would make V0 by Vs equals to minus 3. R0 is 15 kilo ohm actually, 15 kilo ohm. So I put 1.5 into 10 to the power 4 because this will be 10 to the power minus 4. This will be cancelled. 1.5 into 2 will be minus 3. Minus 3 volt per volt. This is the gain. That's it. Say yes or no. Did you understand this complete question? Without even studying common drain, common gate, those terms, nothing you have seen, but still you are able to answer the amplifier question, which will not be which a lot of gate aspirant cannot answer, or even in the interview or in the written test. Just the circuit was given, they have made the biasing like this. We studied different kind of biasing, but any engineer, any designer can make his own biasing. So this is the biasing he has used. Is that biasing correct? Yeah, this is correct because we have seen here, we saw here that it is perfectly working in saturation region. The current is also coming. He wanted to make drain voltage to be 0. So R0 is 15 kilo ohm. If he had said that I want my drain voltage to be minus 2, I want my drain voltage to be minus 2, then what will be VDS? If he wanted drain voltage to be minus 2, then what would have been your VDS value? That would be 1 volt. And if it was 1 volt, then it would not go into saturation, it would go into linear region, then it would not work as an amplifier. Are you getting this point? But he has made the question smartly. He has made the question smartly, making sure that V0 is 0, so that your VDS is higher than V overdrive voltage. Then everything is matched. Then if the transistor is working in saturation region, we know the model. We know the model that now we are going to do the AC analysis. Vs is there, Vs current is flowing. So V0 will be simply GMVS into R0. That's it. V0 by Vs is minus GM R0. Now R0 values we are having, but we are not having the value of GM. GM is a DC parameter, we know, mu n CXW by L, VGS minus VT, 200 micro we got, right? You can find the value of GM by some other formulas as well. There were 3 formulas. What were the formulas? Let's revise it once again, then we will end the lecture. So what was the formulas of GM? One formula we have already used. What was the other one? These are very, very important, so always remember it. 2 into mu n CXW by L ID. Everything is under the root. 2 into mu n CXW by L ID under root. This was the one formula. And let's use it for finding the value. So that would be 2 into, what is mu n CXW by L? That is 100 micro. And what is ID? ID we have already found. That came out to be 200 micro. 200 micro. So micro will come out. That would be micro only. This would make 100. And this is 2. So GM is 200 micro only, no? Yeah, 200 micro Maho. So if you solve this, you get 200 micro Maho. Well and good. Or what was the other formula? The other formula was 2 IDC by VGS minus VT. DC current 2 into what is the DC current? That is 200 micro. DC current was 200. What is VGS minus VT? That is 2. So GM is 200 micro mho. So anytime you need to use any formula, by all the formulas you will get the same answer. But even in some question, you will have only the value of ID and VGS minus VT. Then what you will do? You will apply this formula for GM. In the some question you will have only these two values, then you will apply this formula. And in some question you are having all the values, so you can apply any formula. So collectively it will be used. So I hope you are understanding the lecture. I hope you are enjoying the MOS physics. Not MOS physics, now we are moving to amplifier. So I hope you are enjoying the MOSFETs, and just keep on studying along with. Otherwise you will be forgetting everything. Just keep on studying, and I will give you n number of question in MOSFET amplifier, n number of question. A lot of question will be there, and you will be able to answer within seconds. Once you are done with the complete course, you will be able to answer within seconds. So just keep on studying, right? Okay, thank you. Let's meet in the next lecture. In the next lecture, we are going to study common source amplifier. Okay.